Hello, check. Hello,
Hello, hello, check.
hello, 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 check. पर इसमें आपका
Yeah. Oh, okay, I think I can. Okay, I logged in. Okay. Okay. Yes, I'd like to. How do I share? How do I share the slide? Okay,
Hello.
hello.
Tanaka, if you can just scroll down a little bit.
Hello.
Yeah, yeah.
can you hear me?
I can hear you.
We can.
Okay, can you see my slide?
Yes.
Yes.
Can you please scroll down, go to the next slide, for example, just to see that it's running proper? Next slide.
I can't.
In the
Just
up down, if you can do some up down keys of your keyboard.
how about this?
No, it's the same slide that we are seeing.
Same slide.
We are just seeing the first slide with the
I can't advance the page. How about this? No. Hello. Hello? Can you hear me?
Sir, have you shared your screen, sir?
I'm sharing my slide, but I
Can you, move to the next slide, please, if you can? Are you able to go to the? Yes, yes. Now we are able to see, sir. One more slide, sir. Yes, sir. Thank you. You can stop sharing, sir.
hello.
Hello, everybody. A very good morning to all of you. I welcome all the dignitaries and participants on the second day of NLS-30. Today, we have 4 sessions followed by ELA General Body Meeting. The first session is on advanced laser technologies and applications. This session will be chaired by Dr. K.S. Bindra from RRCAT. Dr. Bindra is outstanding scientist, associate director, laser group, and is head laser technology division at RRCAT, Indore. He joined laser division of Bhabha Atomic Research Center, Mumbai, after graduating from training school in the year 1986. And since 88, he has been working at RRCAT, Indore. He did his PhD from Devi Ahilya Vishwavidyalaya, Indore, and postdoctoral study at Heriot-Watt University, Scotland. At present, his major area of work is applied research on laser physics of different types of lasers, namely high-power solid-state lasers, fiber lasers, ultra-fast lasers, and laser additive manufacturing. He has published more than 120 research papers in international journals. He is a recipient of Department of Atomic Energy Group Achievement Awards for year 2014, 2016, and 2018 on development of lasers and deployment of laser cutting technology in nuclear power reactors. I request Dr. Bindra to please take this session forward.
Thank you, madam, for the introduction. Good morning to all of you and welcome to the second day first session, that is Advanced Laser Technologies and Applications. There are 3 talks. The first talk is by Dr. B.N. Upadhyay. Dr. B.N. Upadhyay, are you there?
Yeah.
Okay. Good morning and welcome. I gave a brief introduction to Dr. B.N. Upadhyay. He received his MSc degree in physics from Allahabad University and MTech degree in optoelectronics from Delhi University in 1997. And he received his PhD in physics from IIT Delhi in year 2011 in fiber lasers. He joined RRCAT in 1988 as scientific officer, and he is involved in development of high power CW pulse ND-YAG and fiber laser for material processing applications. He has published 47 journal papers and has international patent to his credit. He received several scientific and technical excellence awards from Department of Atomic Energy. His current interest includes analytical and experimental studies on high power continuous wave and pulse ND-YAG and fiber lasers along with their material processing applications. So today he will present recent development on high power CW fiber lasers at RRCAT. Over to Dr. B.N. Upadhyay. So Dr. Upadhyay, the talk will be of 30 minutes and 25 minutes for the talk and 5 minutes for the discussion. So maybe
Okay,
2 minutes before your time, I will give you a call to wind up your talk.
Okay. So my slides are visible?
Yes.
Okay. So very good morning to all of you. And I am thankful to organizing committee for giving me the opportunity to speak on our work on high power CW lasers at RRCAT. And the outline of my talk is like this. I will first introduce high power fiber lasers, then fiber laser configurations, then what are the various challenges in development of high power fiber lasers, and the fiber laser development activity at RRCAT, in which we are working at in YB doped CW fiber lasers near 1 micron for material processing applications, and then RBM doped CW fiber laser near 1.55 micron, which is eye safe and have low loss in long distance fiber transmission. So it has various applications in defense as well as in oil well drilling or concrete drilling. And then thulium doped CW fiber lasers near 2 micron, which is also eye safe, and water absorption peak lies at about 1940 meters. So it is very useful in surgery, urology, lithotripsy, and most of the medical applications. And it is also useful for welding of transparent plastics as well as engraving on plastics. If you look at the various applications of fiber layers, it is growing day by day, and it is being used in material processing and medicine like cutting, welding, additive manufacturing, and surgery. And then it has also various applications in mining and defense. Nowadays, about 20 kilowatt fiber layers are being used for 4 times faster drilling through hard rock in case of oil well drilling or for mining applications. And here you can see a slide in which a picture in which for defense application, a target is being destroyed by using a 20 kilowatt fiber laser. And we are also developing high power fiber lasers. And recently we have developed 500 watt, 1 kilowatt, which will brief in my talk. And then we have also used it for drilling through concrete, but it is at a limited depth, about 100 mm. To look at the various fiber lasers which are being developed worldwide, it provides a very long wavelength tunability by using various dopings like YB, ND, erbium, thulium, then holmium, and it has a wide range of wavelengths. We can generate starting from even 400 nanometer to about 2.8 micron, more than 2.8 micron. But we are mainly concentrated on development of ytterbium, which are nowadays have developed more than tens of kilowatt output power. Then erbium doped fiber lasers, which provides wavelength in the range of 1.5 to 1.6 micron. And then thulium also we are working on, and it has a wavelength in the range of 1.7 to 2.1 micron. The basic advantages which high power fiber lasers provide, or fiber lasers provide as compared to bulk solid state lasers, are its high beam quality, which is close to diffraction limited, m square value near to 1 we can get. So its focusability becomes very good. And there are lower thermal problems because of large surface to volume ratio as compared to bulk solid state lasers. And because of inline fiber bracketting mirrors which are written in fiber itself and is completely integrated with the fiber components, so there are no mechanical misalignments. Now we'll go through various the configurations which are being used for fiber laser development. So first we'll look at the YB doped fiber laser, in which we have 2 basic energy levels, which is split into 4 levels: ground state, 4 split levels, and there are 3 levels in the upper state. So we can pump either by 915 nanometer or 975 nanometer. And here it shows the absorption and emission peak. So 915 nanometer absorption peak is nearby this, and here 975. So absorption at 975 is very high as compared to 915 nanometer. And 915 nanometer, you can see it is quite broad. So any wavelength shift at 915 nanometer will not any fluctuation in the output or any degradation in the output. But at 975 nanometer, if there is any shift in the wavelength, it will provide lower output or efficiency will become poor. And if we look at the quantum defects, it is about 15.3% at 915 nanometer, while it is at about 11% at 975 nanometer. And here you can see the absorption cross sections at 975 nanometer is very high as compared to 915 nanometer, about 3 to 4 times higher. And emission at 1035 nanometer, which is peak, but it has a very broad emission. You can say around 1030 nanometer to about 1140 nanometer. So even there is a small absorption at lasing wavelength also. So it will give in result in like cell pulsing kind of things, which I will explain later. So the main configuration which is being used in fiber lasers, it is the double clad rare doped fiber structure, in which basically we use a double clad fiber which has a core. There is the inner clad, there is the outer clad, and core has a higher refractive index as compared to inner clad and then outer clad also. But in case of single clad fibers, which are being normally used for communication purposes or power delivery purposes, which has a core which has a higher refractive index, but outer cladding has a lower refractive index, and then jacket has a further higher refractive index. So only the guidance can happen here in core, but here the guidance can be done in core as well as in the cladding, because all the 3 are guiding structures. So in case of fiber lasers, we have a core which is doped with rare earth ions, and then we have inner clad. We launch the laser light or pump light into the inner clad. So while propagation through the inner clad, this pump light gets absorbed in the core, and the outer clad guides the pump light, whereas the inner clad guides the laser light, and laser light is emitted through the core only, and this inner clad, it acts as a guidance only. So we need that there should be a large mode area and low numerical aperture for the core to have a good beam quality. And inner clad should have a large diameter and high NA for efficient pump coupling. And lasers can be generated in the range of 1.1020 to about 1140 nanometer for case of YP. So major configurations which are used for monolithic fiber lasers are only either it is directly oscillator, where we use Bragg gratings as feedback mirrors, and then another configuration is master oscillator power amplifier, in which we amplify a low signal to very high signals using either single amplifier stage or double amplifier stages. And then to generate much higher powers, we combine several beams from several fiber lasers together in like in oscillator from oscillator or MOPA configurations. This is one of the figures in which you can see that earlier in about 2012, people have generated more about 1 kilowatt of signal power using a monolithic configuration in which there is a doped fiber, YB doped fiber, and then there is a 100% about Bragg grating mirror. There are several pump diodes like 200 watt, 7 pump diodes which are combined together to pump into the YB doped fiber. And then there is a cladding mode stripper which removes the pump light, which is residual pump light after absorption. And then at the output, there is a 10% OC FBG, and they have achieved about more than about 1 kilowatt power, and by pumping with a 14-18-5 nanometer as a pump and with 71% efficiency. So here you can see that at the output power, there at the output end, there is enormous density of power. And if we use only 20 micron as a core, at the fiber tip, power density will be very high, which is about 318 megawatt per centimeter square. But if we use a end cap, which has a maximum length of about d/2 n into Na, which is the maximum length in which mode degradation will not take place or beam quality will not degrade. Only is in a single pass, it will there will not be any reflections at the end. So beam quality remains intact. And by using a end cap of 400 micron, we can reduce the power density to by 0.79 megawatt per centimeter square. So fiber has a damage threshold of about 1 gigawatt per centimeter square. So we have to remain below 1 gigawatt per centimeter square. And this is another configuration in which about 3 kilowatt all fiber monolithic laser has been developed in MOPA configuration, and it was reported in 2018, in which they have used a ultra low Na YB doped aluminophospho-silicate fiber of about 25 meter length, and again it has a 20 micron core diameter. Then in the oscillator stage, they are generating about 260 and then amplifying by using several diodes as at the input pump, and about 42 diodes have been used to pump it, and about 3 kilowatt of output power they have achieved. And here again, the pumping, you can see that pumping is at 976 nanometer, not at 915 nanometer. But at 976 nanometer, there will be a lot of heat generation, which I will explain in the next few slides. Nowadays, fiber laser engines have been developed by various firms like IPG Photonics and other firms, and about 500 watt, 1 kilowatt, 2 kilowatt are commercially available, in which they use just input as a pump, and that everything is integrated in a like a box in which there is a doped fiber, pump combiner, Bragg grating, everything is there. Just we need to add pump inputs to generate higher output, but it is like a black box, we cannot do anything. So generate higher powers, further higher powers beyond kilowatt level, we combine several inputs from fiber laser modules by using a signal combiner. Like here you can see a signal combiner in which about 3-to-1 combiner, 2 kilowatt input from each input we can provide, and 6 kilowatt output can be generated at the output. But output will be multimodal, because here when we are combining or tapering the 20 micron fiber from fiber lasers, it will provide a more diameter, more larger diameter, and about 100 micron we can generate. So there was a recent report on about 100 kilowatt fiber laser from 300 micron fiber from IPG Photonics, and they have used 90 lasers per combination using these kind of signal combiners, and beam quality is also not very bad. It is about 25 milliradian, which is deliverable through a 300 micron fiber. So the major challenges in development of high power fiber lasers are basically the self pulsing, heat removal from doped fiber and fiber components, nonlinear effects, low loss splicing and reliable splice joint recoating, damage of fiber end surfaces, fiber fuse effect, photo darkening, and transverse mode stability at kilowatt level of power. These are the various problems which are faced during the development of fiber lasers. If you look at the cell pulsing, it is basically when we are, although we are pumping with CW, but what happens even with pumping with CW, because we are pumping from the one end of the fiber, other end remains unpumped or slightly lower pumped. So reabsorption along the fiber length also takes place, and it lacks like a sexual absorption effect in which passive quenching kind of pulses appear. And if it has a very high peak power, nonlinear T's will also generate, and we will get SRS Stokes peaks. So what happens? These high peak power pulses, which are in the terms of cell pulses, without doing anything, and we are just pumping in CW and we are getting a pulsed output, then what happens? Peak power becomes very high. It can damage the fiber components. Like here you can see a fiber break getting damaged because of this kind of cell pulses. So we have to be very careful while doing splicing and other things, so that these kind of cell pulses are not generated. We have much earlier reported this kind of thing in applied optics. And the next issue is like heat dissipation in fiber laser. Although we say that it has a very large area, surface area as compared to volume, so it should not have very heat load. But also there is quantum defect, and fiber diameters are very small. It has also a outer cladding which is made of like plastic, or you can say polymer. So its heat dissipation capacity is very poor. So because thermal conduction from the coating and glass, it is very poor. So what happens if the low index polymer can only stand up to about 150 to 200 degrees centigrade temperature, but 80 degree we have found that is a safe limit at which we can operate without any damage to the fiber at any point. So upper limit on heat dissipation density in the core is decided by onset of coating damage. And if you look at the various heat inputs equations from the basic fundamental heat convection equations, then temperature of the core, temperature of cladding is given by heat dissipated in the core and which gets transmitted to the cladding and then out at the outer cladding. So we need to heat sink these fibers, tiny fibers, in basically some metallic groups, so that heat dissipation can take place very rapidly. Otherwise, what happens if we took about 100 watt of heat, like 10% as a quantum defect, then 10 watt in a 10 meter length of the fiber, about 10 watt per meter will be dissipated. And for air, if there is no cooling, just it is kept in air, then temperature of the core will rise to very high temperatures. And if we have a forced air cooling, then convective heat coefficient will become larger towards 10 power 3 order, and temperature will get down very rapidly. So in case of high power lasers, we need to cool the fibers, because even at low quantum defect also, it will requires cooling of the doped fibers. Then another effect is nonlinear effects, which also get dominant at very high power lasers. Then stimulated Raman and Belloni scattering thresholds are given by these basic equations, which are available in literature. It depends mainly on the core area as well as effective length of the fiber. Then if we look at the line width of the various lasers, if you want to generate a 0.01 nanometer, very narrow line width, then SBS threshold becomes dominant, and which needs to be much taken care of much before. But when the line width is larger, we need to care about the SRS thresholds. And what happens because of these nonlinearities, if there is any SRS as SBS, then conversion of laser signal to progressively longer unwanted wavelengths will happen, and heat disposition in the core also increases due to longer wavelength generation. Then another effect is fiber. Even if we apply all these things and take care of all these effects, what happens even if the fiber fuse effect is basically a catastrophic effect that occurs when an imperfection in the fiber precipitates heating and the local temperature approaches about 1000 degrees centigrade. Means what happens if at any point of the fiber laser, if temperature is very high, then a laser radiation propagating to the fiber is strongly absorbed, and the temperature increases to about 10 to the power 4 Kelvin. So a plasma-like formation will take place, and a bright white spot propagates along the fiber in the backward direction at a very high speed, which is uncontrollable, and damage is manifested by periodic like bullet-shaped cavities in the core, and it is filled with oxygen. So SiO2, basically the core composition gets dissociated in silica oxide, and oxygen is filled in the cavities. Like here we have observed in our lab that in case of fuse effect, what happens, it initially damages the core, and it bullet kind of propagation takes place inside the fiber. And here you can see the cross section of the core. So there is a cavity in the core here. And if you look at this movie, that how fast it is propagating, and it damages the whole components. Although outer coating is not damaged, only in the core this kind of thing happens. So even if you control the cell pulsing, then photo darkening is another effect in which there is an increase in transmission loss with time in the fiber, and there is a fast degradation of doped fibers with a high fractional ytterbium excitation density in the fiber, with a high doping concentration and poor homogeneity due to formation of ion clusters. So the rate at which transmission losses at 1 micron grows appears to be like proportional to 7th power of density of excited ytterbium ions. And photo darkening effect, it can also be reversed because it is a lossy thing. It can be reversed by radiation with ultraviolet light, but it requires to remove all the doped fiber components and to reverse it back. So although the regions for this are not very clear, but people say that formation of YB ions plays an important role. And when YB ions are generated in the fiber, YB2 plus ions, but how it has been generated is not yet clear. So then this photo darkening will take place in the fiber. And now people are mitigating from this photo darkening effect by using a YB2 phosphate fibers and phosphosilicate fibers, and by co-doping with cerium. And one more effect at kilowatt power level people are experiencing nowadays, and last 1 decade people are suffering from a transverse mode instability, in which what happens at the output power of kilowatt level, it starts fluctuating. Output starts fluctuating from a stable mode of TMG0 mode, and it is basically a transfer of power from stable transverse single mode to higher order modes. And suddenly power stops increasing and gets down, and efficiency also decreases very rapidly. These are various reports in literature. And basically what happens, this occurs due to coupling of power from fundamental to higher order modes. And TMI in all fiber layer configuration can be mitigated by higher order modal loss. Means if we increase higher order modal loss by coiling the fiber into a tight loop, then these effects can be mitigated. But even we cannot very much tightly loop the fiber, there are certain other problems. So looking at these challenges, we have gone through the development of YB2 CW fiber laser development at RRCAT, and initially we developed about 100 watt all fiber YB2 CW fiber laser, in which we used a 35 watt fiber cooled laser diode 975 nanometer. We combined together several other things like pump combiner. Then there is a 98% FBG at 1090 nanometer. Then it is a 10 meter of YB2 fiber. And we generated initially, it was air cooled system. Here you can see it was air. There is it is wrapped on a mandrel of aluminum, and we got about 57% efficiency, which was very initial result in about 2012. Then we moved on to developing further higher power and scaling these output power, and we reached about 700 watt single transverse mode output power from fiber laser by using 150 watt diodes at 975 nanometer. But here you can see the fiber length which has been used about 20 meter, and it has a core and clad diameter of 20 and 400 micron. We are generating laser output at 1080 meter. These are the two FBG mirrors which are making the resonator, and we have a monolithic kind of thing. And here you can see the splice joint of double clad fiber, which is an octagonal shape, and then FBG, which has a circular shape. This splice joint has to be very good. Otherwise, losses, if there are losses in the cavity, then cell pulsing will take place, and it will damage most of the components. So here you can see it is a clumsy setup in which we are using doped fibers, double clad fibers, and there are various heat sinks which has been deployed for generation of this much output power. And here efficiency we have achieved about 77%, because pumping is at 975 nanometer. And but here we observe that the temperature of the initial gun portion of the fiber, because here the maximum pumping takes place and maximum absorption takes place at the input end of the double clad fiber. So its temperature rises more than 80 degrees centigrade, which is very unsafe. Otherwise, it will lead to this this kind of fuse effect, and it will damage the whole fiber components. So here we observe that SRS threshold is about 2.6 kilowatts. So from a 20 micron fiber, we can generate more than about 2.6 kilowatt of output power. But we got limited to about 700 to 800 watt power because of this temperature rise.
Dr. Upadhyay, few more minutes, 2 more minutes.
Okay. So now we try to package this 500 watt fiber laser by coiling it onto a spool. Like a fiber laser engine we have made, in which most of the components like IB doped fiber, double clad fiber, and brake grating are coiled into a single heat cooling block. It has become very compact, so that by pumping at 158 watt of output. But here we have used 950 nanometer pump diode. So 950 nanometer, basically absorption becomes lower, and here the heat per unit length in the fiber becomes lower. Here we have used a 35 meter because absorption is less, so longer length of the fiber has been used. So heat per unit length has become lower, and we are able to generate more than about 500 watt of output power with a efficiency of 75%, similar to that. And M square value is again here single mode, and the line width is about 1.28 nanometer. Here wavelength you can see 1080 nanometer, and we have packaged to a single box like this kind of thing, and we have tried it for various material processing applications also. Here we have operated it up to about 1 kilowatt, about 1 hour of continuous operation with a power stability of about 1.5%. And we have used it for cutting of SS up to a 5 mm thickness, and at a speed of about 500 mm per minute. You can see just a slide how the cutting takes place. There's a very high speed of cutting, and we could cut about 5 mm thickness of steel. And this is one of the welding applications in which we welded about 2 mm thickness by using this laser. And this laser we are also utilizing for laser additive manufacturing applications. Then we moved on to development of kilowatt level of YB doped CW fiber laser, in which we have used about 200 watt, further scaled the pump input at 950 nanometer, and by splicing, good quality splicing and management of heat from the fibers, here we have used 7:1 pump combiner. So input is about 1370 watt, and we are generating 1014 nanometer. Here we have also used a cladding mode stepper, so that whatever pump residual pump is there, it is removed from the fiber. And delivery fiber is also a QBH, quartz block holder delivery fiber, and we are generating a single mode output. And now we are trying to package it. Here's efficiency, you can see it is 24%, and line width is about 1.5 nanometer. So then RBM doped, we also tried RBM doped fiber lasers, in which about 2 micron, 1.55 micron wavelength can be generated. Although in literature, people have reported more than 600 watt of output power by using a 146 micron RBM doped dual cat fiber. But RRCAT, we have used a 20 micron core diameter fiber, and generated about 25 watt initially at 1600 nanometer with efficiency of about 28%, and by using a 12 meter fiber, and it has a clad diameter of 125 micron. Further, by using oscillator amplifier configuration, we have generated 5 watt from the oscillator and amplified into a oscillator amplifier stage, in which we are pumping with 976 nanometer, and 25 micron core is there, and we are generating about 50 watt of output power. So it has efficiency of 22.5%. Here efficiency is less because of the quantum defect is more, very high quantum defect, and we need to heat sink the doped fiber in a very good manner, otherwise it will damage the components. Then thulium doped also we tried, and in thulium doped fibers, basically the quantum defect is again very high, about 61%. But because of cross relaxation, when we are pumping by 780 nanometer, it goes to 3H6 to 3H4 level, and it comes down to here 3F4 level. This whatever photons are generated from here to here, it can be reabsorbed by a nearby thulium atom. So 2 to 1 photon gets excited, and that's why its quantum efficiency can be achieved more than 50%. Here it is a 1 kilowatt already reported in literature, in which they have used a 20 micron core diameter fiber and about 12 meter length, and then oscillator amplifier, and it has been reported 53% efficiency. At RRCAT, we have initially generated by using a 12 125 micron fiber, similar combination in which we are using a pump combiner, then grating, then output. And we have generated more than 43 watt in backward pumping configuration. We are pumping backward here, 100% grating is here, and we are generating at the output here. Here, 4% reflection from the fiber end acts as a grating mirror. And this laser has potential
Dr. Upadhyay, Dr. Upadhyay, you may please wind up your talk.
Okay. So all fiber laser at 100 watt we have generated by using this at 1940 nanometer, which is useful for lithotripsy, and this shows the experimental setup. And then finally, we have also observed cell pulsing in thulium job. If it is not controlled very well, splice joints are poor. And this is how it looks like. It has a 53% efficiency at 1940 nanometer. It is useful for, and we communicated in applied optics. Then the critical issues are various. There are several, about 10 splice joints, which must be made to have low loss. There are, if there are any irregularities and high loss at splice joints, which causes scattering and absorption of light, that results in increasing temperature of the splice joints, may cause damage. So dust-free coating of all the splice joints should be done for reliable operation. Low index polymer can withstand about 150 degrees centigrade temperature, but 80 degrees temperature. So temperature of the outer cladding has to be retained below 80 degrees centigrade. All the splice joints, diodes, pump combiner, FBGs, and doped fibers should have proper heat sinking mechanism. So I will conclude my talk by saying that we have generated up to 1 kilowatt of single transverse mode output from YV doped CW fiber laser with all fiber integration. And then we have generated up to about 50 watt of CW power from RBM doped fiber at 16 nanometer. And then we have also generated about 100 watt of CW power from thulium doped fiber laser at 1940 nanometer for various medical application. Then we are scaling it to further higher powers by using a single combiner, signal combiner. So thank you, and I acknowledge my seniors like Sri S.V. Nake, our director, Dr. K.S. Bindra, head LTD, for their continuous support for this activity, and my colleagues, Dr. Usha Chakravarti, Ravin Singh, Adesh Kumar, Pushkar Mishra, Antony Kovilla, R.K. Jain, and Sirajpal Singh for their help in doing all these work. So thank you very much.
Thank you, Dr. Upadhyay. There are a couple of questions which have come into the chat box. Although you have described CW fiber lasers, there is a question from Dr. Alok Ray. He wants to know what are the challenges in making multi-kilohertz rep rate pulse fiber lasers.
Multi-kilohertz pulse fiber lasers are basically either in Q-switched mode we can generate, either otherwise it can be as mode locked also. So if we go for Q switching, also Q-switched mode. So in Q-switched kilohertz repetition rate pulses we have generated, and about 20 watt of average power from Q-switched fiber laser using all fiber integration we have already achieved. And this has a pulse frequency of about 10 to 100 kilohertz, and pulse duration is about hundreds of nanosecond order. And in mode locking, the different group from our lab is working, Dr. P.K. Upadhyay, and they have generated in megahertz region picosecond and then femtosecond pulses also. So in high power, high frequency pulse lasers, actually the other challenges are like non-linearities are the major problems. So non-linearities you need to control so that the pulse duration and other things remain at the desired level.
I just want to add one more thing, that one can easily generate multi-kilohertz or very high rep rate pulses from the fiber laser. There is absolutely no problem. Only issue will come that since the core diameter of the fiber is very small, one cannot get very large energies. So if one wants to get more energy, then you have to go to the bulk case. Okay, there is another question that from Shri Praveen Agarwal. Which are the parameters of the fiber laser is dominating and limiting the output power stability?
Output power stability is basically the core size and then non-linearities. Then also if the output mode quality has to remain the single mode, then what happens because of the temperature rise in the core, and there is a change in refractive index. So it acts like a long period FBG. So because of long period FBG, the mode remains confined to the core, and it becomes shrinkage, means there is shrinkage in the fundamental mode, and the power gets dissipated to higher order modes. So that's why it becomes unstable. So you need to control basically the temperature of the fiber so that it remains single moded. And even though after controlling this temperature, but still at very high power levels, this will it is going to happen. So temperature is the main cause for this change in mode quality.
Yes. There are two more questions. One from Dr. Anirudh Kumar, that what is the typical life of high power fiber laser?
Typical life is basically decided by diodes. So diode lifetime is mainly about 10,000 hours. So if the diodes are operating for 10,000 hours, then you can say that the operating lifetime of these fiber lasers will be 10,000 hours. If there are several few things like if we are going to use a single emitter diodes, then lifetime people claim that it will be 100,000 hours. So if single emitters, but single emitters have limited power of 10 watt. So low power fiber lasers of about 100 watt can be made to have a 100,000 hours lifetime, but high power fiber lasers will have mostly about 10,000 hours lifetime.
And then there is a question on self-focusing effects. How does it affect the laser output power? I believe the lasers that you are using, they are all single mode, and there is no question of self-focusing coming over there, correct?
Yes, yes. At present, it is not there. Yeah.
And the last laser pulses to increase the peak power. Of course, this is more pertinent to the pulse lasers. Of course, you have been talk has been concentrated on CW fiber lasers. So, would you like to say something? I think
no, it is basically related with mood lock and other things.
Yeah,
it will be
if you have
covered
a
in the
mood lock
other
fiber
talk
laser,
something.
so if of course if there is a chirping of the laser, the peak power will come down, and that is the standard practice also. In the case of the fiber lasers, typically the fiber length is very long and it is a nonlinear media. Automatically chirping comes into picture. So in general, the pulses that you get from the fiber lasers, they are chirped, and then externally the pulses are compressed to get a high peak power. Okay, thank you, yes. Dr. Upadhyay. There are no more questions in the chat box for your interesting talk. Okay. You can unshare your slides, and I would request Professor Kazuo Tanaka to share his PPT. Professor Kazuo Tanaka, are you there?
Oh, I'm here.
Oh, thank you. Welcome and very good morning. I'll just give a brief introduction to Professor Kazuo Tanaka from Extreme Light Infrastructure for Nuclear Physics. He is current scientific director at Extreme Light Interaction Nuclear Physics Infrastructure Facility at Romania. He did his electrical engineering in 1976 and PhD in plasma science in 1982. His research interest in is nuclear physics, relativistic, laser plasma nonlinear interaction, laser fusion, plasma physics, and high density physics in the area of laser plasma interaction, equation of states, cryogenic implosion, and fast ignitions. Professor Tanaka is presently Professor Emeritus at Osaka University, Japan, and he has also been a professor at Osaka University. He has been Director of Center for Nonlinear Science and Engineering at Osaka University, and he has received many prestigious awards like Award of Ministry of Education and Culture Japan 2005, APS Dawson Award from USA, Daiwa Award UK, Progress Award, Laser Society of Japan in 2011, to name a few. Over to Professor Tanaka.
Thank you. Let me share my screen.
And just for the viewers, I think the laser that Professor Tanaka will be describing is one of the most powerful lasers at present in the world.
Okay, can you see my screen?
But your PPTs are not visible yet.
Is it coming?
No, it is showing starting to share, but still not visible.
Okay.
Now, yeah, it have come.
Okay, good. So, good morning, our Indian colleagues. It's a great pleasure for me to be invited here to the very prestigious conference. And today I'd like to talk about this extreme light infrastructure nuclear physics, which is located, actually you are not so familiar if Romania is so good about the laser, but this is located in Bucharest, Romania. And this huge project is funded by European Commission starting in 2012 with a budget of more than 360 million euros. So this is one of the largest laser and gamma beam actually facility. I'll talk about this in Europe. And two other similar laser facilities emerging in Hungary and Czechia. And today I talk about what's going on in ELI-NP. And in my talk, I talk about ELI-NP as a user facility because this facility is supposed to work for the world users, including you Indian community. And we are now doing extremely successful in starting the experiments, especially in the commissioning phase. And I talk a little bit about another major facility, gamma beam system. It's called Vega, Variable Energy Gamma System. Can you see my slide changing?
We can see that.
Yes. Okay. So ELI-NP is a user facility. And as I said, we have two major systems. One is a hyper laser system. Actually, right now, we have a world record of 10 petawatt, which can deliver 250 joule in 25 femtosecond. Beam diameter is 50 centimeter. And if we focus it properly, we can exceed the focus laser intensity more than 10 to the 23 watt per square centimeter. And of course, this focus intensity has never been achieved anywhere in the world. So we are very curious, what kind of science we can, open up. And the Vega versatile gamma beam system with the highest photon number. This is gamma beam photon energy is 19.5 MeV, and the spectral density reaches 5,000 photons per electron volt per second. And the linear polarization is better than 95%. And so gamma light will interact directly with the nuclear for excitation and fission. And we already started receiving a kind of a preliminary proposal. It's called a letter of intent. And we had the first user workshop in 2019. And we received this series of letter of intent from Queen's University, UK, Oxford University, University of Rochester, University of California, San Diego, GIHC, Russia, and KPSI, QST, Osaka University, and so on. So second user workshop is planned in early 2022. And I'd like to invite all of you to join this, brilliant, user facility, which can run the, 100 terawatt and 1 petawatt and 10 petawatt laser output. And as I said, the two other laser facilities are emerging, ELI-Alps in Hungary and the ELI beamlines in the Dolny Bezanini in the Czech Republic. And we coordinating together with these three ELI pillars. And we have running this Impulse project to get a common headquarters in Brussels. And, this is one of the flow chart, how the user proposal is accepted and evaluated for the technical feasibility and the scientific merit. And we will decide yes or no for the submitted user proposal. And this user proposal format is being prepared in details. And these will be also announced very shortly in the ELI-NP webpage. And this time schedule, you can see that we have, as I said, 100 terawatt, 1 petawatt, 10 petawatt. All these laser output is running, successfully. And however, we are doing the 100 terawatt and the 1 petawatt experiment for the ion and electron acceleration and etc. And we have to wait for the large optics installation for 10 petawatt line, beam line. And that will happening this month. And we will tune this, largest peak power 10 petawatt up to the summer. So we can start shooting this 10 petawatt laser to some experiment later this year. So we are very successful to start doing the experiments in the commissioning experiment. What is this commissioning experiment? This is actually, we have to test our laser performance. And you are looking at now is a 40, 70 meter, large clean room with two arms of, 10 petawatt beam lines. And on the right, we have 80 centimeter vacuum pipes running around to carry this 10 petawatt laser beam to the experimental chamber area. And as I said, this 70 meter, 40 meter or optics table is isolated from the building walls and with 1,000 dampers in below this floor. So this huge optical table is extremely stable. And as you can see it in the table, this hyper laser system can deliver 230 joule, and the central wavelength is about 825 nanometer, and the spectral bandwidth is 130 nanometer. Pulse duration is 23 femtosecond. Large diameter is about 50 centimeter, and the straight ratio, that is focusable spot size compared to the ideal diffraction limit size, it's 95%. And to demonstrate our robustness of this laser system, we did an international symposium on November 17, 2020. And Gerald Morrow and Dana Strickland, if you know, they got the 2 Nobel Physics Prize in 2018. They joined and they gave opening speeches, and about 230 scientists all over the world, as you can see on the right-hand side, US DOE, Livermore, University of Texas, UC San Diego, University Bordeaux, Osaka University, University Polytechnic Madrid, and the GEST Korea, Weizmann Institute Israel, and so on. They all joined. So we did see a major players of high energy density physics, and also, TIFR, Ravindra Kumar joined here. And on the final point, Professor Gianluca Sari gave a memorial speech on the quantum electrodynamics potential for using the 10 petawatt laser system. And this graph actually showing how reliable and robust this 10 petawatt laser beam line. And on this day, we started with 75 joule energy. That's on the right and the vertical axis. And the horizontal axis, you see the time steps about every 1 minute. And we kept shooting about 75 joule and ramping up to 175 joule. And finally, we're ramping up to 230 joule in front of 230 participants from all over the world. And actually, we consider this excellent laser system is a first generation of a turnkey system. As you may know, these high peak power laser system takes a lot of tuning and adjustment. But of course, we have to do this, but reliability makes us possible to turn on the key and the laser just coming out. And on this day, on the right-hand side, department head of Ion Dankas and with Olivier Tales, they are smiling each other after finishing up this, demonstration. They had a lot of, pressure on their shoulders. And on the right-hand side, we have question and answer session from the audience. And this graph shows also at the 100 terawatt level, the horizontal axis is the time of the month, and vertical axis is working hours, and the color bars showing a different experiment this laser system is given to. That's like a four-wave mixing and jitter measurement and laser wake field acceleration and blah blah. So for each experiment, the laser has to tune, with some detailed conditioning, and they did it, and they kept supplying these beams very reliably. And also 1 petawatt laser beam line is operating and used for the experiment, commissioning experiment in the chamber areas, and the number of the pulses and the vertical axis and the pulse energy to about 20 joule to 25 joule. That's in the 1 petawatt level. Most of the laser shot of the more than about 1,000 laser shots were given to the 1 petawatt experimental area successfully. And so 100 terawatt experiment, laser gamma and experiment department has started the preliminary phase dark matter search, and this is collaboration with expert users from Japan, Hiroshima, and Kyoto universities. And the laser-driven experimental department has started the electron acceleration experiments. And this dark matter detection system setup is shown on the right-hand photo. And basically this one is 100 terawatt laser is focusing into the vacuum. And the left-hand side, this wave diagram showing omega, which is at 100 terawatt laser beams, 2 photons start stimulating the dark matter, and with triggered by the green light U omega, then we're supposed to get a 4-wave mixing, which is supposed to give rise to some scattered light as a signal. And Professor Honma and Professor Sakabe have participated in this experiment already. And as I said, this is already a collaborating experiment with Japan, and successfully, and still it's a preliminary phase. And what I say preliminary is we're shooting into some poor vacuum. And in poor vacuum, we have some residual atoms, and we can excite a 4-wave mixing through these residual atoms, which was observed in this graph. So on top, we have a 23 femsecond 100 terawatt laser beam pulse, and the NDR triggering the 4-wave mixing. And on the bottom part, actually 4-wave mixing from the residual gas is observed. So basically, this preliminary experiment shows that our measurement system is working, and we are now gradually evacuating the vacuum to the much higher vacuum. And once we lost this noise signal, we are ready to start searching the axions and dark matters. And the electron acceleration at 100 terawatt was also very successful. On the right-hand side, the beam configuration in the chamber is shown. And on the left, you see, a gas jet target was shot by the 100 terawatt laser, and the clear laser channeling was observed. And in this laser channeling, laser wake field is excited, and the electron is accelerated. And on this experiment, we can differentiate electron energy spectrum. Top on the left shows the broadband spectrum up to 300 mega electron volt, and the bottom it's a monochromatic electron spectrum is about 180 mega electron volt. So we can have a very good control, how to broaden the energy spectrum or make it monochromatic in this experiment. And by increasing 10 times laser power to 1 petawatt, we already started a commissioning experiment. In phase 1, led by the Mikhail Cherniano, we observe the target normal cis acceleration, TNSA proton acceleration as a commissioning experiment. And this is also collaborated with UCSD and Ohio State University, United States. And also second phase is led by Petr Genuke, laser wake field acceleration commissioning experiment. And this one is collaborated with Giannico Sari, Queen's University of Belfast, and the Legizzi in Italy. And the beam configuration is shown on the left. And while we are shooting at the solid target, the proton spectrum was obtained. Proton was accelerated by the target normal cis acceleration. And in this experiment, we have seen that 12 mega electron volt proton was observed. And we try to increase the signal to noise ratio of the main pulse. As you may know, before the main pulse, we have a pre-pulse or some noise pulses. And to get rid of that, we can increase signal to noise ratio of the pulse, laser pulse itself. And to do that, we introduce a plasma mirror. And this plasma mirror's idea is to shoot into this plasma mirror before the main target. And so plasma mirror start making a plasma by these pre-pulses, and the main pulse is reflected by the surface by removing these pre-pulses by creating this plasma. And we suppose to shoot this target with a very good signal to noise ratio. And by doing this, certainly we increase proton energy up to 30 MeV. And also on the right-hand side, the energy spectrum, you see that about 38 MeV, 40 MeV. So we are waiting to, extrapolate this experiment from 1 petawatt to 10 petawatt sometime this year. And, very simple, linear extrapolation tells us we could get about 400 MeV proton energy. That's the highest. And I understand, of course, experiment is not so easy to apply this kind of linear extrapolation, but we'll see. And electron acceleration is also conducted at the 1 petawatt level. This is the beam configuration, shooting it to the gas target by using this 5-meter long focal length mirrors with a 1 petawatt laser coming into this target. And here you can see that in this small inside diagram, we get about 2 giga electron volt to electron beam energy successfully from the first series of this electron acceleration. So again, with a simple-minded extrapolation tells us what's going to happen in 10 petawatt in the near future. We may get the 20 GeV electron beam. That will be also highest energy. We'll see. And other than that, we are expecting some very interesting laser matter interaction can happen at 10 petawatt laser pulse. And recently, we published this physical review research by Jianfu Wong and Petr Genuke and me, telling that once we shooting this 10 petawatt laser beam into the nano, structure targets, it's called nanowires. For example, these are kind of foam targets, low density. And laser can couple very well with these low density foam targets or nanowires, but we've revealed what is this physics, why this laser can be coupled into these nanowires so, efficiently. And this shows that, why this laser is coupling efficiently into this target. And I cannot turn on the, okay, here you can see that. This is one single nanowire hit by the 10 petawatt laser, 10 to the 23 watt per square centimeter from the left to right. And the top and the bottom, there is a blue wavy structure. That's electromagnetic wave laser, brushing up this nanowire, but inside you can see another wavy structures, which is a wake field, electron waves driven by the fast electrons, which is running in this nanowire. And there is a very good energy feedback loop created by this electromagnetic wave into the laser wake field inside the nanowire, and laser wave keeps supplying the electrons into laser wake field, and that is the reason why we can get a very high efficiency of the coupling from laser to the absorption into these nanowires. And as you can see it at the end, this nanowire is getting pinched by the return current magnetic field, and by this pinching, we can get a 10 terabar of the pressure. That's is supposed to be the highest on the Earth. As you know, Sun core is the central pressure is 240 gigabar, and the National Ignition Facility Livermore can get a 350 gigabar in the implosion, laser fission implosion. And right, if we shoot these nanowire structures with temperature laser, we can get a 10 terabar. That's highest in the pressure. And our PIC simulation shows that peak pressure can reach up to 400 terabar actually. But I don't want to say overstatement. So we average this graph, and at least we should be able to get a 10 terabar with the plasma pressure in these experiments. And we'll do this experiment. And even at the 1 petat level, we have started test shooting these nanowire targets. And we have another major facility. It's called the gamma beam system, variable energy gamma system. And it's getting ready and getting installed. And this is actually consisted of the linear electron accelerator up to 300 MeV here, and a ring cyclotron strange ring, and emitting electrons up to here. And this electron beam is collided with a green laser light, and this green laser light experience a huge Doppler shift of inverse Compton scattering, and that gives rise to the 19.5 MeV gamma rays with 5,000 photons per second per electron volt. And the completion is expected in 2023. So this Vega system, as I said, the commissioning is expected in February 2023, and the system acceptance is expected in after March of 2023. And full system acceptance is expected in May 2023. So for gamma system experiment, diagnostics is getting ready. For example, this elegant, huge, neutron detector arrays is already built up, and we are conducting calibration of these detectors. And the area there on the right-hand side, it's another gamma ray detectors, and this one is already constructed, and we're doing the calibration. So while we are waiting and start doing the commissioning experiment, or we start writing some scientific outputs, and these three papers in the report on progress and the matter and the radiation extremes and the hyper lasers is our overall review of our systems. If you're interested in, you can download. And also, yes, we are writing more than 300 papers in the last 3 years, but for example, 80 papers, in some notable journals, Nature Physics, Nature Communication, Scientific Report, and Physical Review journals coming out. And some of them actually are under the collaboration with expert users, and some of them with only ELI-NP peer authors. So summary, At the ELI-NP, all the laser systems are up and running, and the experiments started using a laser output with 100 terawatt and 1 petawatt. Expert users participated at 100 terawatt, 1 petawatt experiments already. Commissioning experiments continue this and next years with meaningful physics results. 10 petawatt full power target shot will start in late 2022. Second user workshop will be scheduled in spring of 2022. And user experiments can start as early as in late 2022 this year. And 20 MeV gamma beam Vega will be completed in 2023. Thank you very much.
Thank you, Professor Tanaka, for the very excellent talk and hearing the most powerful laser in the world. There is a question from Professor Ravindra Kumar. He wants that could you comment on the physics phenomena that you might see at 10 terabar?
Okay, one of the interesting physics I'm interested in is I introduced today in my talk. We can get a very high energy pressure of 10 terabar to 400 terabar. And this actually pressure we are doing continuing the PIC simulation and should produce a huge energy of electrons and protons. And that is actually a very different acceleration mechanism. And also, as you can see that wake field is driven in the solid density. And usually this laser wake field acceleration is done in the very low density gas of 10 to the 19 atoms per cc. But solid is 10 to 23 per cc. It's 4 times higher. So if we can drive this kind of wake field in a solid, I think we can obtain a huge acceleration field for the particle acceleration. So there are many new phenomena, and yes, Ravi Kumar, you are welcome to join us to explore this kind of new horizon of the physics. Thank you.
With these kind of intensities, many new phenomena in the fundamental science will going to come up. I just wanted to know that instead of using nanowires, if you go for nano dots, will it make any difference? Would you get much higher pressures?
That's an interesting question. These nanoparticles, people already started finding some, Coulomb explosion, because when the nanoparticles is brushed by these intense laser, electrons escape fast, only ions left out, and that's caused the Coulomb explosion. And I think we have not done yet, but somebody has to do this PIC simulation. What will happen in these extreme conditions of Coulomb explosion? Yes.
And finally, I just interested to know what kind of pre-pulse, the ratio of main pulse to pre-pulse you have in when you are dealing with this kind of intensities.
Okay, that's a very interesting question. Right now, the ratio is about depending on from main pulse to few 10 picoseconds before the main pulse. I think it's extinction ratio is 10 to the 7 or 10 to the 8. It's not so good, but we planning to introduce a plasma mirror to get rid of these pre-pulses, and partly we are already successful, as I showed you, in the proton energy in the 1 petawatt. It's improved to the 40 mega electron volt to the 12 MeV protons, and we keep continuing this development of plasma mirror. And also, what your point is very interesting. In a focused laser beam of this 23 femtosecond with a very broad band of 130 nanometer, nobody knows what's going on in the temporal spatial characteristics. And that's another interesting physics in optics is still waiting for us to be understood. Yes.
Okay. Thank you. Thank you, Professor Tanaka, for the very interesting talk. And with the kind of laser you have, many more interesting phenomena will going to come in near future, and with the new facilities that you are going to add. Thank you once more.
Thank you.
We come to the last talk of this session, which is by Professor Sivarama Krishnan. Professor Sivarama Krishnan, are you there?
Yes, Dr. Bindra, I'm here.
Oh, thank you and welcome. Professor Sivarama Krishnan is an associate professor in physics at IIT Chennai, and he specializes in quantum dynamics with variety of photon sources, including femtosecond lasers, synchrotron sources, free electron lasers, and he currently co-leads a Max Planck partner group on scaling electron dynamics. His research interest includes light matter interaction with advanced photon sources, tabletop femtosecond sources, synchrotrons, and free electron lasers. So today, Professor Sivarama Krishnan will speak on photoelectron imaging and multi-coincidence spectroscopy of doped quantum filled helium nanodroplets with extreme ultraviolet photons. Over to Professor Sivarama Krishnan.
Yeah, thank you, Dr. Bindra, and the organizers of the National Laser Symposium. But I must begin this presentation with a mild apology for changing the title. This was just to keep my talk in line with the session I was moved to from an earlier session on spectroscopy. So I hope that's okay. This talk is going to present not only what I had earlier intended, but also another piece of science which would resonate with using large-scale facilities to do intense laser matter interaction. But I will begin with modest intensities and single photon interactions to start with, very much in contrast to Professor Tanaka's fascinating talk, but towards the end possibly have something to say about rejoining the spirit of this session in the sense of using large scale complementary facilities. So of course, for Indian colleagues here, whom I wish good morning, IIT Madras in the city of down south in Chennai is no stranger. You know this institute very well, a cluster of now 25 Indian institutes of technology. We are of course among one of the older set of institutes, and share very nice connections, early connections with Germany. And now a highlight of our institute may also be considered this research park where translational research takes place, and I'm sure my institute administration is happy that I advertise this in especially to this vast community. And we are doing pretty well in terms of national rankings and so on, but we really take pride in the fact that we have a growing not only undergraduate student strength, but now masters and PhD student strength as well. And for younger folks here, especially in India, you're welcome to come to IITM and interact with us, especially in the laser community. I'll be very happy to sort of be a liaison with the people here. This work is done largely in collaboration with prominent colleagues here from IISER Pune. If my audio is fine, Professor Dr. Bindra, is my audio okay? Hello? Dr. Bindra? Okay, I will just continue presuming it's fine. Just a moment, please.
Professor Shivram Krishnan, we can hear you very clearly. Please.
Okay, thank you. I just had it out. Okay, thanks. Okay, so I was just thanking my collaborators from IISER Pune, from TIFR Hyderabad, IIT Hyderabad, and also colleagues from the Electra Synchrotron Center in Trieste, Aarhus University, Marcel Mudrisch, MPIK, Heidelberg, and University of Connecticut, and more recently with the Leibniz University in Hanover. And we're also thankful for the funding from the Department of Science and Technology, Ministry of Education, which was earlier Human Resource Development, the Max Planck Society, Electrosynchrotron themselves, ICTP, and Daisy Germany for the work carried out at the international centers. This talk may be viewed as three short stories, one on or a couple on single and multi-electron processes at synchrotrons, and the last one may be more in the spirit of the session, which concerns imaging of collective dynamics in nanoplasmas using single shot coherent diffraction imaging at X-ray free electron lasers. Okay, but the host system for this talk literally are helium nanodroplets. These are helium clusters into which we can sink in other atoms or molecules like rare gas atoms or molecules of almost of any choice. I'll have something to say about the location of these dopants in or on these droplets, but these have been rather fascinating systems for doing spectroscopy to begin with, especially in the UV visible, infrared, and even vacuum ultraviolet, owing to the fact that helium has a very large first electronic excitation energy. But then these
Professor Sivarama Krishnan, your
Yes.
volume is very, I'm not getting the volume. Would you be close to the mic?
Yeah. Is it better now, or I could also do something about that?
Dr. Bindra,
Is it-
okay here. It is okay here in our auditorium. We are able to hear clearly, loudly. Thank you.
Okay, then I will just proceed. I hope it's also fine now. I just took off my headphones.
Okay, maybe you continue. I think maybe there may be problem somewhere on my side.
Okay, so yeah, so these are essentially clusters of helium into which we can dope other atoms or molecules. The process of doping itself, I will not go too much into the details. It's the clusters are made by supersonic jet expansion, and the dopants are picked up from a vapor doping cell as shown in this schematic here. And these helium clusters require that we use rather high backing pressures and low cryogenic nozzle temperatures, all the way from 6 Kelvin or maybe even 4 Kelvin upwards. We use closed cycle refrigeration technology, very standard Sumitomo cold heads to do this. And the interesting thing is that these helium clusters, which have an internal temperature of about 400 millikelvin, are in a superfluid state owing to the fact that the lambda transition is at 2.1 Kelvin. So this also has a bearing on target preparation, if you wish, for these experiments. The location of the dopants themselves, mostly rare gas dopants and molecules actually reside at the center, and we take advantage of this, as we also do in the case of alkalis, which are surface bound because of the nature of interaction between a helium atom and an alkali. This is also very well quantified and understood, and that's all I may want to say at this point. Of course, if there are things to discuss on this, we can always do at the end of this talk. A point to note is that neither the size distribution of these droplets for a fixed set of experimental conditions, nor is the doping level or the number of dopants per droplet a fixed number. Both of these follow earlier in the case of droplet sizes, a log normal distribution, and now in the case of doping numbers or sizes for a fixed droplet size, Poissonian distribution. So we need to live with this and learn to deal with this essentially in these kind of experiments. So the experiment itself we do consists of creating these droplets, then sending these droplets into a doping cell to pick up the desired dopant atom or molecule. We have also put in like large molecules like C60 or even like coronine and pentacene and stuff like that. So this is a very nice way to engineer a target, a molecular target, and we can also make aggregates of these atoms or molecules, which otherwise may be difficult to form, and put inside these droplets and use this as I said, a nanocryostat. We use a chopper in this experiment to distinguish between signals that we record in this what we call spectrometer chamber specific to the droplet jet and everything else that may be present in the background by blocking of the jet, and we typically run the chopper at about 70 to 100 hertz. The main workhorse of these experiments is a combination of an photoelectron imaging detector, which is called the classic velocity map imaging detector. All we need to sort of take home about this detector is that we can measure photoelectron kinetic energies and their angular distributions. And simultaneously, for every such photoelectron, we can also determine who the parent ion or maybe even a couple of parent ions which are formed by using the standard time of flight technique. This is just a Wiley-Maclaurin geometry. So we can do quite a few tricks and jigs here, which I will just briefly touch upon based on the relevance of our the experiments I'm going to showcase. This is just the steel version of this nerdy setup. We have the droplet source, we have the doping arrangement with a large turbo pump, and we have the velocity map imaging spectrometer. This workstation is of course available at the gas phase end station at the electrosynchrotron, which is where the first set of experiments I'm going to present were done. The velocity map imaging spectrometer, as I said, is essentially an imaging spectrometer which records following a photo ionization event the angular distribution of photoelectrons emerging out of this process, as well as it records the kinetic energy of these electrons by allowing this Newton sphere, which is essentially a momentum sphere of electrons that come out from such a process, to be projected in a well-defined way on this detector. So electrons, all electrons of a given kinetic energy would fall on the perimeter of a circle or a circular distribution. Lower the kinetic energy, the more close to the spectrometer axis or the center would an electron fall. Higher energy electrons would actually fall away and go towards the edge of the detector. That is to say, higher the energy, the larger the radius of the circle. And the angular distribution also can be measured because the entire sphere gets projected out. So obviously, when we want to recover the photoelectron spectrum, we need to do some kind of an inversion and unwrapping process. But then not only do we do this, we record the electron, which we use to start a clock. And on the other side of this spectrometer, we have ion optics, and the ions arrive at microsecond timescales. And using this sort of a tandem recording of the photoelectrons and photoions, we essentially do a coincidence measurement, what we call VMI, photoelectron photoion coincidence, and then we build up statistics in an experiment like this. So we essentially do the VMI and the photoion spectrometry in tandem. So we have, in one sense, more complete information than just recording electrons only or ions only, as I said, because we can determine the parenthood of each of these photoelectrons, as we will see later in this talk. So if we expose pure helium droplets to photons in the extreme ultraviolet between 20 and 26 eV, we get this kind of a yield curve for photoelectrons and photoions. Helium has an atomic ionization energy of 24.6 eV, so it's no surprise that we see electrons or ions prominently being produced above this ionization energy. But what may come as a surprise is that in the case of these helium clusters, ionization already begins well below the ionization energy of these helium clusters, right? All the way from about 23.2 eV, which is the atomic excitation going from the 1s2 configuration to the dipole allowed 1s3p configuration. So we can identify regions where direct ionization takes place, where this intermediate region where ionization, excitation and ionization can take place, and there is a region where no action seems to happen, but that's not really true. If we dope these droplets with suitable dopants, in this case alkali dopants, I request you to focus your attention on the bottom right panel of this graph. Here we have done the same measurement by putting in alkali atoms, that is lithium or sodium or potassium, on which are held on the surface of these droplets, and swept the photon energy from 20 to 26 eV and recorded the same kind of ionization curve. And you see prominent dopant ionization at 21 with a peak around 21.6 eV, which corresponds to the 1s2p atomic excitation of helium. If one records the fluorescence from pure droplets, the fluorescence curve seems to map almost the ionization curve for the alkali dopants. So this was, of course, the fluorescence was measured earlier by a group from TU Berlin. Now, in the case of rare gas dopants, which reside at the center of the droplet, the photoionization yield as a function of photon energy, which is shown for the case of argon clusters in the bottom left panel, seems very similar to that of pure helium droplets. So putting these things together, we concluded, and in 2013, using this coincidence technique, established the fact that the ionization of the dopants at the center, which is rare gases, is dominated by charge transfer. whereas the ionization of alkali dopants which reside at the center happens either because of excitation transfer or a more complicated process, which is not just charge transfer. And I will have more to say about this more complicated process in the slides to come. So this probably is the most important view graph for the first 2/3 of the stock. So what I call the Penning transfer, which is dominated in terms of the photon system interaction at excitation energies of 21.6 eV, is once again this. To reiterate, a photon comes, creates a dipole excitation. This excitation is then transferred to a dopant, in this case an alkali atom residing at the surface of this droplet, and the alkali atom gets photoionized. So this is what we call Penning transfer or an excitation transfer in the stock. So we did this experiment with not with rare gas, but alkali atoms doped on a helium cluster. But we have more than one alkali atoms, which is rubidium atoms doped on the surface of this helium cluster. This was a part of the PhD work of Sudha Sattva Mandal, a talented PhD student who's soon going to graduate. So he's available for postdoc positions. I must advertise that. We now dope the droplets with rubidium, and we look at this view graph on the right, which is an important graph where we sweep the photon energy again from 19 to 27 eV, and we see that rubidium ion signals which emerge from the droplet. As I mentioned earlier, we have a way to tease out the droplet specific signals using a chopper, so we have no doubt that this is coming in from the droplets. We have a very prominent rubidium monomer ion produced at about 21.6 eV. We also have other excitations being reflected in this process, but this is a very important photo line which we take forward for the next few slides in this talk. Okay, so how do we know that we have clusters of rubidium on these droplets? If you look at the droplet correlated signals, we see rubidium dimers and even trimers. It looks meager on this little plot because the signal is dominated by monomers, but because of the fact that we do coincidence measurements, we can get photoelectron spectra which is specific to dimers, trimers, or monomers of rubidium ions, which is what we do. And we did this is true at both photoexcitation energies, 21.6 eV and 26 eV. Now, the interesting part of the photoionization physics of this system is the fact that we essentially have three signatures in the photoelectron spectrum. One is the Penning structure, which we should expect will occur by producing photoelectrons at energies which are the helium excitation energy, which the excited helium atom can either be in the 1s2p state or in the 1s2s state, minus the ionization energy of rubidium, which is about 4.2 eV. So this bump here in the spectrum is due to that. We have a low energy structure between 0 and 2 eV. This is also seen with other rare gas, not rare gas, alkali dopants, lithium, sodium, or potassium. What is new to rubidium is this prominent intermediate peak structure, which I am calling the unforeseen peak structure, which I will explain in some detail later. So this is a typical VMI image, which we then Abel invert to obtain the photoelectron spectrum. Again, I'm not going to discuss this, but maybe something experts know and non-specialists could possibly discuss later, right? So is this intermediate peak structure between 6 to 10 eV robust? Yeah, we change the level of rubidium doping in the droplet, and by increasing the temperature of the oven that vaporizes rubidium, we increase the temperature all the way from 70 to 120 C. We see that the structure not only remains robust, it also grows at the expense of some of the other spectral features. So indeed, this is an important feature in this photoelectron spectrum. Okay, so what is the mechanism for producing these intermediate photoelectrons? So this is what we set out to do. And once again, the Penning process is this: photoabsorb, excite, transfer the excitation somehow, and ionize the dopant, right? So let's look at what happens in a multiply doped helium droplet. So we have conditions where we can dope the droplet multiply with more than one rubidium atoms, which is what we did in this experiment. When we dope these atoms multiply, once again in this coincidence measurement, we can not only tag one parent photoion. If there is more than one parent photoion due to multiple ionization, we can tag with every electron all its parent ions, because the times of flight of these ions are in the microsecond range, and we can do correlation measurements. Okay, so we build a correlation map. We look at electrons and both their parent ions, ion 1 in the horizontal axis and 2 in the vertical axis of this figure, and just count how many hits we get when this correlated ion production is produced, and these hits are nothing but electrons arriving at the imaging detector. So once we do this and build this correlation map, we can isolate islands of correlation and then build the photoelectron spectrum as we did earlier from these islands alone. And when we do that, the expected penning feature, of course, in a sense disappears, because that does not really lead to two ions being produced. It leads to only one rubidium ion being produced. In the case of rubidium and rubidium dimer plus coincidence, we see the other two spectral features surviving, telling us that these two spectral features, the one between 0 and 2 eV, the low energy, and the intermediate energies between 8 and 12 eV, are indeed consequences of multi-electron processes. So what are those processes which create multiple electrons? This is coming about because, and I will again be brief in the interest of time, due to interatomic decay process, and I hope that this little animated view will help us appreciate what happens. We have typically the one helium which is going to get excited, and this is attached by van der Waals bonds to rubidium atoms which are on the surface of the cluster. The 21.6 eV photon arrives, excites primarily the helium, and then there is a sort of long-range interaction in this composite system. And this, please note that the interatomic distances here are pretty large from the consideration of molecules. These are several angstroms, maybe even 10 angstroms and so on. The size of these droplets is typically large, about 10 nanometers to 100 nanometers, depending upon the initial conditions. Here it was about 15 nanometers. So this excited helium atom could be anywhere in the droplet. Nonetheless, we have a very efficient interaction between the excited helium atom and the dopant atoms, which are actually clustering together on the surface. And this triggers off a decay process of this excited system where rubidium atoms get multiply ionized. So this is an indirect multiple ionization of a rubidium cluster on a helium droplet. So this is a fairly new process. There are a lot more details to this, in which I'm again going to skip for most part. Whether this process happens sequentially, that is whether both the electrons come out simultaneously, or there is a cascade. This is something that we can actually figure out even from our experimental results, and we have done even that. So we can have two kinds of interatomic Coulomb decay processes. The one that I described and showed, which is a simultaneous double ionization, which we call double interatomic Coulomb decay process without a cascade. We can also have a cascaded process, which I will come to later on. And this is what this view graph is going to show. The helium atom is primarily excited, and then in the process of de-exciting the electron de-exciting in helium, an inner shell 4p electron is excited to the continuum, leaving in the first step an excited rubidium ion. This excited rubidium ion can again decay and sequentially ionize a neighboring rubidium atom. So there are three parties exchanging nodes sequentially in this process. Earlier, the helium rubidium atoms worked as a pair and emitted out 2 electrons. We can do the energetics of this and also identify peak structures within the same intermediate peak structure between 6 and 12 eV, which I show in this view graph. Again, in the interest of time, I would not be able to go through each and every detail. Molecular helium states also get involved, molecular rubidium states get involved, but the physics is what I just described, especially for the cascaded process. The double ICD process was already reported in an earlier work by our collaborator Aaron Lafarge. We believe that this is the first time we are observing such a cascaded process also from an inner valence shell in rubidium. So we hope to publish this in a good journal soon. Why do we bother to study all this at all? The reason for that is essentially that these kind of secondary processes were noted to be very important in DNA damage. This paper published in 2000 in Science probably has a few thousand citations, and this really told us that it's not just direct ionization, it's actually the secondary processes which are responsible for single and double strand breakages in DNA molecules, but also in an environment which is typically water. Water is too complicated a molecule. Actually studying and understanding these processes deeper in helium is a nice way to get insights into the physics of radiation damage of biomolecules as well. So now I come to the...
Professor, your time is up. You may please wind up.
May I just take 2 minutes?
Yeah, fine.
Yeah. Okay. So I will just conclude this talk with a slightly different topic being presented, but I will do it, of course, very briefly. We heard in the previous talk the importance of laser plasma interactions and the very hot and high energy density systems being created. And there was also a question about nanoparticles being ionized by such a laser. So in an earlier work, we put in a few xenon atoms which were doped inside a helium droplet and ionized them with a strong infrared laser pulse. And what we observed was a very efficient ionization of the whole nanodroplet to the maximally ionized helium-2+ state in a matter of sub 10 femtoseconds, which was also published in this work. So this is simply the yield of helium-2+ and 1+ ions as a function of the number of doped atoms, and we found that this sort of ignition based boom or in the ionization happens for such a small critical doping number as 7 for a droplet containing 10 to the 4. Now this was a picture that we painted in this paper and carried forward with investigating this further, but seeing is believing. Can I really image these nanoplasmas? And this is where X-ray free electron lasers, which are linear accelerators, come into the fore, and these are complements to the large-scale facilities like ELI. In fact, one of the goals of some of the ELI beamline at Prague, the MAC chamber, is to actually do this even with high harmonic generation from tabletop lasers. I'm sure that will happen in the near future, but for now we use long X-ray based accelerators. We did this experiment at the Flash facility in Hamburg. Once again, I will skip all the details related to that, but what we really need to just keep in mind for the next couple of minutes is that we diffract a single femtosecond X-ray pulse intense enough to produce a full diffraction image as is shown in these two depictions. And what we did was to essentially image these nanoplasmas which evolve in time. The nanoplasma itself can be imaged very, very nicely. Why is this important? We, again, like Professor Tanaka said, do simulations, then go to a facility and ask for beam time, which is what we also did. I will come to the main stay of this talk. When an intense infrared pulse ionizes a helium nanodroplet, there is a violent set of processes, but very well understood, which seems to go on, and the whole system absorbs energy and disintegrates, to put it very, very in very, very short words. Now, the point is, can we image this, right? So we did a combination of coherent diffractive imaging and took also the VMI technique to do energy domain or momentum space imaging with VMI and physical space imaging of these systems with coherent diffractive imaging. So we have an optical laser pulse serving as a pump, which initiates the plasma dynamics or nanoplasma dynamics, and the probe pulse is the FEL, which comes after that and images the intermediate state of these nanoplasmas, right? So imaging is the key. So the time evolution of these nanoplasmas can be depicted in this cartoon. You put a few ionization seeds inside the droplet, ionize the seed, drive the system, create the nanoplasma, let it then explode and disintegrate. Can we actually watch this process? This is the question that we asked, and this is indeed a high energy density system. So we did the experiment with a free electron laser to convince you that this experiment work. You can see nice diffraction rings. Any undergrad can understand what happens. These are sort of Newton's rings, you may say, that before the ionization takes place, the droplet is nice and spherical. The fringes are likewise having this symmetry. And then as the droplet starts to ionize, you can see that these fringes start to develop substructures. And finally, even on a rather long time scale, 6 picoseconds, the plasma disintegrates and the order in the system is disturbed. And you can you can visualize that on the coherent diffractive imaging technique. But every experiment should have some surprise, and ours did too. So these 3 steps that I described are fairly well known, but we simply delayed the arrival of the FEL pulse by several nanoseconds. Even after a whole nanosecond of time, there still seems to be some remnant nanoplasma. This is something relatively new. We also know that another group in parallel has similar observations made. So there seems to be also interesting nanosecond dynamics, but then seeing is believing. Now we have started imaging these systems, whereas earlier we measured the energies of the remnant particles. So with that, I will conclude and not even go into recapping what I said. And but thank you for your attention and the organizers for the opportunity. Professor Bindra, I'm done. For some reason, I'm not able to hear what Professor Bindra is saying. So if
I'm G.
yes.
Sridhar, I'll take
Oh,
over.
yes.
So, Bindra ji, can you speak? Your voice is not audible. So the few questions are there. One from Dr. Padma Nilayam about the van der Waals forces.
Yeah, the question is essentially how do these weak van der Waals bound systems remain intact after they are ionized by such an intense laser? Indeed, they don't remain intact at all. We just catch them in one of their intermediate states where the system is still sort of, you can say, close together nearly in its initial state, or perhaps when it's disintegrating, as we saw in the last few slides. So disintegration is essentially a part of the process. However, if we don't do anything to the system, this is a supersonic jet at very cold temperatures. The target that we prepared remains intact until it hits maybe a chamber wall and disintegrates. In fact, such deposition studies with rare gas clusters have also indeed been done, and they may actually be an attractive but expensive way to produce some exotic nanoparticle. Okay, Professor Bindra had a question. Do you mean why only one atom in the cluster is ionized? Yes, in the initial studies, we had the photon density was low enough that we have at most one photon interacting with the droplet. So helium has an absorption cross-section of about 25 megabarns in this 20 to 26 eV photon energy range. And so we expect that at most one helium atom is excited or photoionized in a small droplet or cluster with a size of 10 to 100 nanometers.
Okay, sorry, because I was having some audio problems. I was not able to hear. Maybe all you are able to hear Professor Ramakrishnan. I just small question. Then when you are talking of this excitation using the femtosecond sources, what kind of intensities you are talking about?
With the infrared laser, this was a little over 10 to the 14 watts per square centimeter. In the experiment that I described in the end, where we create a nanoplasma in helium, we deliberately kept the laser intensity such that the doped xenon atoms inside, which are called the seed atoms, they are ionized directly by tunnel ionization by the infrared laser pulses. And we chose an intensity where the helium atoms are not ionized directly. So the seed is ionized, the host is not ionized. We did this so that we can actually make the ionization progress from inside out, so that there is some structure and method to this avalanche happening going from inside out. In earlier studies, we also did this with surface resident dopants so that we have an outside-in process. We did this also with the FEL imaging, and of course, we are analyzing the data.
Okay. Thank you, Professor Sivarama Krishnan, for the interesting talk. And there are no more questions. And thank you very much. And with this, we close the session, and I hand over the stage to the organizers.
Thank you very much, Dr. Bindra, for chairing this session. So now we have exceeded the time of this session slightly, so we can directly go to the next session. This session is, the topic of this session is laser materials and devices. And this session will be chaired by Dr. Tarun Sharma. So Dr. Tarun Sharma, are you connected?
Hello, yes, can you hear me?
Yes, we can hear
Is
you.
Tarun here?
Yes. So
Okay.
we will start the session. This session, as I said, is about laser materials and devices, chaired by Professor Tarun Sharma. He is a professor and head of materials science section of Raja Ramanna Advanced Center, Advanced Technology, Indore. He joined RRCAT from the 30th batch of Bhabha Atomic Research Center Training School. Professor Tarun's primary research interests lie in the area of semiconductor physics related to quantum waves, quantum dots, heterostructures, and devices. He has worked at several prestigious institutions in India and abroad, like TIFR, Mumbai, Ferdinand Braun Institute, Germany, University of Surrey, UK, and Carnegie Mellon University, USA. He has received several awards, honors, including the prestigious Homi Bhabha Science and Technology Award, which is the highest individual scientific honor of the Department of Atomic Energy. He has published more than 250 papers in international journals and conferences, and also holds a US patent. So over to you, Professor Tarun Kumar Sharma.
Thank you for your introduction, and good morning and welcome. We have 3 talks in this session on laser materials and devices. And the first talk is going to be given by Professor Jagadish. Indeed, it's a great pleasure to introduce Professor Jagadish to you all. We need a
Please keep the introduction short.
And hello, yeah, I will keep it short. I will, I will try to keep it as short as possible. But certainly I have to do my job also. So let me please do that. So he's a professor and head of semiconductor group at Australian National University, Canberra. He's a noted alumni of Delhi University, joined ANU way back in 1990. He has published more than 1,000 research papers, holds 6 US patents, and many other things basically. He is editor-in-chief of Applied Physics Reviews and currently serves on editorial boards of 90 other journals. He is a fellow of 11 science and engineering academies and 14 professional societies. Professor Jagadish has an illustrious academic career and has received many awards. The list is too long, really long. To name a few, he has received OSA Nick Holonek Award, IUMRS SOMI Award, UNESCO Medal for his contribution in nanoscience and nanotechnology, and Lyle Award from Australian Academy of Science. In 2016, he was awarded the Companion of the Order of Australia, which is the Australia's highest civilian honor. And just to let you know, cricket legend Sir Don Bradman is another recipient of this award. And recently, he has been elected as President of the Australian Academy of Science, and he's the first Australian of Indian heritage in this role. Not to be forgotten that he, along with his wife, Dr. Upadhyay, have created an endowment fund to help undergrad and postgraduate students from the developing nations to visit ANU for a period of 3 months. Today in NLS, Professor Jagadish is going to talk on semiconductor nanostructures for optoelectronic devices, optoelectronic applications. Professor Jagadish, a very good afternoon, and over to you, please.
Thank you very much, Tarun, for that kind introduction. And so really, I'm humbled and grateful for this honor to have been invited to speak at this important conference. And I would like to thank the organizers, Dr. Padma Nilaya, and all my colleagues organizing NLS-30 for inviting me to this conference. So as been mentioned that I'm going to talk about semiconductor nanostructures for optoelectronics applications, and considering that it's a laser conference and I'll focus much more on lasers than other aspects of our work. And in addition to being at the ANU, I have honorary appointments in various parts of the world, and I want to thank various institutions for inviting me to be associated with their institutions. And also today's talk is really a collaborative effort within my group at the Australian National University and many groups in Australia, US, UK, China, and Sweden, Italy, Russia, Switzerland. The beauty of science is that there are no national boundaries. We can all work together. It's been a great pleasure for me to work with many students and postdocs in these research groups, and I want to thank all of them for their contributions to joint research. This is my group at the Australian National University, and then typically 10 to 12 nationalities at any one time, and then bright young people, and it's really a pleasure working with them. And I want to thank my senior colleagues in the group and also the funding agencies for their support for our research. So here is an overview of my talk, and I'll give you the motivation why we are interested in semiconductor nanostructures, and then I'll mainly be focusing on nanowire lasers and LEDs and infrared and terahertz detectors. But we also do all sorts of solar cells and photoelectrochemical water splitting of hydrogen, generation of hydrogen, nanowires for sensors, and nanowires for neuron growth and signaling measurements. But I will not have time to talk about these green things. And anytime, if you have any specific questions, you can always send me an email. And I'll draw some conclusions. And I also want to acknowledge many groups, those are working in this field, and I want to thank all of them for enriching our discipline and including India. So the World Economic Forum has identified in the future needs of the technologies needed for the next generation industry, particularly Industry 4.0, and in which they've identified holographic displays, wearable optical sensors, light navigation and communication, 3D vision and gesture recognition, and enhanced machine vision and augmented reality. And all these technologies require smart and miniaturized optical systems. And as a part of a center of excellence, which has been recently funded by the Australian Research Council, we are really working towards developing nanoscale lasers and nanoscale beta optics for manipulating light of amplitude, phase, and polarization, and also using nanostructures for detection of light. And I'll be covering these two aspects here in this particular case. This particular center has been led by my colleague, Professor Dragomir Nishev, and 5 universities and 15 CS are involved in this particular center. So the optoelectronics, and I don't have to tell about optoelectronics for this group, and 3-5 semiconductors are widely used in terms of making lasers and LEDs and solar cells, and also used for internet and for infrared imaging applications for night vision and large area displays or so. And so I'll be really confining myself to this talk to the 3-5 semiconductors, which we mainly work on. So nanowires are seen as building blocks for the next generation electronics and photonics. And one of the unique things with the nanowires is that the lattice mismatches are no longer an issue. That means it doesn't matter what's the lattice constant. That means the unit cell of the crystal, which repeats itself in the material. And so irrespective of what's the lattice constant differences between the two, then you can be able to grow high quality nanowires. And that's what really opens up opportunities because of their nanoscale and 3-dimensional architectures. You can also make axial heterostructures. These green materials are different than the red materials. You can all make PN junctions, radial heterostructures, and the branch nanowires. We've in fact demonstrated a wide variety of structures of the highly lattice mismatched structures and branch nanowires, nanotrees, and most recently we are moving from nanowires to nanomembranes also, which I will be covering in this particular talk. So in view of the fact that this particular topic is on laser materials and devices, and I'll be covering both, and then in this case, I'll just share with you how do we make these nanowires. So we typically use some metal nanoparticles and then gold nanoparticles, for example, and then or otherwise we use selective epitaxy, and then either of these techniques which we can make use of. And then though gold has got a high melting temperature when reacts with gallium or aluminum or indium, its alloy melting temperature of gold, gallium, or gold, aluminum, or gold, indium is as small as 350 degrees Celsius. So if introduce the gases needed for the growth of gallium arsenide, for example, trimethyl gallium and arsen in an MOCVD reactor, these gases get incorporated into this liquid alloy, it gets supersaturated, crystals start precipitating out. In fact, this is a work of about close to 15 years back, and my former student, Dr. Hannah Joyce, during her PhD, who has demonstrated state-of-the-art gallium arsenide nanowires. These are about 50 nanometers in diameter. They're atomically perfect. Essentially, you can see the transmission electron microscope image. The diameter of the nanowire is essentially determined by the diameter of the nanoparticle. We made nanowires as small as 10 nanometers, as big as 300 nanometers using this particular technique. And she's now at Cambridge University as an associate professor. And another technique which we use, selective epitaxy. In this case, we don't use any metals, and we deposit some silicon dioxide, put some photoresist, and do electron beam lithography, and create patterns of holes. And we transfer those holes through silicon dioxide to the semiconductor substrate. In this case, I'm showing an example of indium phosphide. Then you really put this one in the MOCVD reactor, heat it up to somewhere between 650 to 750 degrees Celsius, introduce gases needed for the growth of indium phosphide, trimethyl, indium, and phosphine. These gases dissociate and then nanowire starts growing. You can see you can create ordered patterns of these beautiful indium phosphide nanowires, which are about 200 nanometers in diameter. This is the work of my former student, Dr. Chian Gao, who is now a research engineer in Blue Glass in Sydney. So we've gone off and looked at these indium phosphide nanowires and excited them with the laser pulse and look at the light emission. And we quantified the quantum efficiency of the light emission of these indium phosphide nanowires, which are in the red curve here as a function of the excitation power density of the laser. And then you can see that they can compare this with the epitaxial layers or the two-dimensional layers which we normally grow, and they are very much comparable, indicating in the case of indium phosphide, surface non-radiated recombination is not a problem. But whereas in the case of gallium arsenide, that is not the case, and which I'll come back to. But indium phosphide nanowires are very good for making lasers and solar cells and photodetectors and a range of devices, which we have been exploring, including making metamaterials also. So then let me come to the gallium arsenide. If you go and look at the gallium arsenide, in fact, even at low temperatures of 10 Kelvin, and then the photoluminescence intensity is extremely weak. And so we need to really think about it. Atomically, they are perfect nanowires, but you really get a very lousy light emission. That means you cannot make use of these things for making lasers, for example. It turns out that surface states, which really create a lot of deep level defect states in the band gap of the semiconductor, if you excite the electrons from the valence band to the conduction band, and then the electrons will be captured by these defect states, then falling down and emitting light. So in fact, you can estimate whatever the non-radiated lifetimes of these nanowires, diameter divided by the 4 times of the surface recombination velocity, and you expect it to have picosecond lifetimes, and that's what we have measured, in fact, at Oxford University using terahertz conductivity measurements. Bulk gallium arsenide typically has got nanosecond lifetimes, but these particular nanowires have got picosecond lifetimes. That means we got about 3 orders of magnitude worse performance from these particular nanowires, which we need to address that one if I want to make nanowire lasers. In fact, that's what we have done, and we've taken these gallium arsenide, grown these gallium arsenide nanowires, and then increased the growth temperature to 750 degrees Celsius and grown aluminum gallium arsenide shell. And then you finish off with the gallium arsenide shell because of the fact that aluminum gallium arsenide, aluminum oxidizes very easily. So this aluminum gallium arsenide has got a larger band gap than gallium arsenide. In this case, if you excite electron hole pairs in gallium arsenide, they cannot go to the surface. Recombination takes place in gallium arsenide. You can see the cross-sectional TEM of the structure, gallium arsenide core, aluminum gallium arsenide shell, and gallium arsenide capping layer or so. So is because of this potential barrier, it is really confined to this gallium arsenide core here. This is what's a barrier potential profile, which I'm showing you here. You go on and looked at the light emission, and again, you can see once if you introduce this shell of this aluminum gallium arsenide, suddenly the light emission increases quite significantly, and you also start measuring the nanosecond lifetimes. And this is work of my former student, Dr. Jenny Jiang here. And you can show that these are now ideal for making nanowire lasers and solar cells based on the gallium arsenide system. So then, of course, we've also been making some ask ourselves, instead of making nanowires, and what else we can really make. Instead of opening a hole, what will happen if you open a slot or a ring? This is the work of my former student, Dr. Nayan Wong, who is a postdoc in the group now. He's looked at a wide variety of growth parameters, which I will not have time to go into the details. And then what I could show essentially is that by opening a slot along a particular crystallographic orientation of this particular orientation, you can really create a beautiful nanomembranes. And if you really open the same slot in another crystallographic orientation, you create also membranes, but they end up having a slightly different facets than these sidewall facets which you've got here. They're also thicker membranes because of this more of the sidewall deposition is taking place, lateral growth is taking place. You open the slot in between these two orientations, so you create these beautiful diamond-like structures with these alternating facets or so. So now we can see, instead of making just nanowires, we can really make a wide variety of nanostructures as well. And in fact, we've gone off and looked at these nano rings. And if you open the rings, and again, you can really create these ring-like structures, again, with these alternating side facets, which I've shown you earlier. If you keep on growing and this gap gets filled up, and then you create a nanomembrane, which is in this case in the horizontal direction now. If you keep on growing further, you end up finishing off these beautifully hexagonal facet structures because crystals likes to be in the lower edgy facets, and that's what you end up having here. So in fact, my student, Dr. Nayan Wong, who has really looked at the light emission from these structures and then using cathode luminescence in this case and exciting the electron hole pairs by using electron beam rather than laser beam, for example. And look at the light emission. You can see you can get a beautiful, very uniform light emission, very bright light emission, indicating that 4 years of hard work of 9-1 really paid off. So now let me move towards lasers. And of course, I don't have to tell this community, you need to have a gain medium, you need to have a laser cavity, and then you need to pump the gain medium to create population inversion, as and when the model loss is equal to the optical losses and the lasing starts taking place. If you take a nanowire, you excite it with a laser pulse, and then the light start propagating to this nanowire because nanowire acts like a waveguide, because nanowire has got a high refractive index with respect to the surrounding medium, and both ends of the nanowire acts like a mirror. So that means in principle, each nanowire should act like a laser. So that means you don't need to put any other cavities and mirrors and all these things. So in fact, we have demonstrated a wide variety of lasers over the years, and I will not spend huge amounts of time, but I'll share with some of them. And this particular work has been led by my young colleague, Dr. Sudhama Kapati, who is an associate professor in Monash University now. And so Dr. Drew Saxena has demonstrated gallium arsenide nanowire lasers, and Dr. Tim Burgess has demonstrated zinc dope nanowire lasers and also quantum well lasers as well. So we've gone off and looked at the simulations of looking at the light propagation to these nanowires, and then you see if you got a TM01 mode, which has got the field intensity at the core of the nanowire. Your T01 mode means it's like a ring-like structure. And for quantum well structures, these are much better. And then depending on what particular nanowire, we end up really designing the cavities in order to be able to get the right kind of devices. To cut the long story short, and based on Drew Saxena simulations, and Dr. Jenny Jiang has grown these structures, and this is about 6 microns long nanowire, about 280 nanometers. And the Drew's simulations have shown that the two small diameter nanowires are not very good in terms of light propagation. They got very high losses, and that's why we had to go for larger diameter nanowires. You can see the below threshold, you see a very broad light emission. Above threshold, you see a very sharp light emission. And threshold-like behavior, output versus pump intensity. Log-log plot shows that the S-type behavior, spontaneous emission here, amplified spontaneous emission, and lasing taking place here. And in fact, these were the first gallium arsenide nanowire lasers operating at room temperature, which we demonstrated about 15 years back or so. And then again, you can see beautiful interference fringes coming from these nanowires. In fact, Drew Saxena has simulated, and then we're able to compare these ones very nicely. Also, that we have been thinking about, how do we really be able to improve the quantum efficiency of these lasers? And also, we wanted to make a doped structures to be able to make PN junctions or so. And when zinc doping is a P-type dopant in gallium arsenide or indium phosphide, and Dr. Tim Burgess during his PhD has really found that once you start doping zinc, you create this something called thinning superlattices, and also bare gallium arsenide nanowires end up having a much brighter light emission, and with respect to the undoped ones with no surface coating or any passivation or anything of that sort. So in fact, we were able to use these zinc doped gallium arsenide nanowires and able to show lasing behavior, again, above threshold sharp light emission and S-type curve or so. And again, this work has been published about, in 7 years, 6 or 7 years back or so. So now we asked ourselves, can we be able to do quantum well lasers? So again, this is a work of Jenny Jiang. And so again, I mentioned to you T01 mode means because quantum wells means they're really like a ring-like structure. And then you really mode also overlapping with this ring-like structure very nicely. You want to have the gain medium and then the optical mode to be overlapping with each other. And again, based on simulations of Drew Saxena, we have grown these structures. And again, Jenny Jiang has spent a lot of time, who is now a postdoc at Cambridge University, and where she has shown that you can really grow these uniform quantum well structures. And so really it required quite optimization of the growth time and other things to be able to get uniform these quantum wells. You see the close-up of these transmitter electron microspectrometry in these ones. So again, to cut the long story short, and then you take these nanowires and transfer them onto a glass slide and excite them with the laser pulse and look at the light emission. And initially see the spontaneous emission from these quantum wells, which are emitting at a shorter wavelength at the higher photon energy. That's what you would expect. And if you keep on pumping, you get the amplified spontaneous emission. You keep on pumping, you end up getting the lasing. And again, the S-type behavior showing these at the room temperature and gallium arsenide multi-quantum well lasers. And then again, we found that the threshold power needed for making these lasers to work is about half of that of the bare gallium arsenide, because quantum wells typically have got a higher gain also. We've also shown both side indium phosphide nanowire lasers, again, which I will not go into the details. And then what are we doing with these lasers? So this is a work which we jointly with the University of Strathclyde, Professor Martin Dawson's group, where they developed a nanoscale transfer printing technique. We can really come up with a PDMSM and then be able to transfer these nanowire lasers wherever you want them to be. Really beautiful work, which collaborative work. You can see that there's a Y junction, which is for the multiplexing and demultiplexing applications of this SU8 polymer waveguide. And then they located these nanowire lasers in front of this waveguide, and we pumped them and we were able to couple the light, and we started looking at the light coming at the other end. We were able to show that you can really get a beautiful propagation of light through the waveguides, and by locating these nanowires precisely where you want them to be. Particularly, these are very useful for polymer optoelectronics applications and flexible optoelectronics applications where you want to be able to multiplex and demultiplex signals. So we asked these guys, whether we can be able to really locate them into the nano antennas. This is the work of my young colleague, Professor Font Wang Ren, and then she has been really designing the terahertz metamaterials where she's creating these aluminum antennas, and there was a gap in the middle, and that's where we wanted them to locate these nanowires in the middle here. You can see the close-up of these ones. You can see these ones, they're able to locate them very nicely. The close-up shows this one here. We do not have the nano antenna. When you pump these ones and the light is coming from the both ends of the nanowire, because nanowire acts like a Fabry-Perot cavity, which I've shown you from these other so-called edge-emitting lasers. But we once put this one to the nano antenna, suddenly light starts coming from the vertical direction because of the radiation pattern has been engineered by using this nano antenna. And then we would, again, these are the first room temperature operating vertical emitting nanowire lasers, which we demonstrated about 4 years back or so. Again, depending on what you're using for, if you want to couple the light to an optical waveguide into an optical fiber, you make use of these ones. If you want to use these things for example, facial recognition applications or meta-optics applications, you make use of these lasers. Depending on the applications, we make use of these ones also. Again, this collaborative effort really led to these wonderful results. And most recently, I told you about ring resonators, which we have been growing. And then this is the work of Wei Wong, and who designed what should be the diameter of the ring, what should be the height of the ring, what should be the width of the ring. And based on designs, he's done grown these structures, and then you pump these ones and look at the below threshold, you see a broad light emission. Above threshold, you start seeing beautiful whispering gallery modes, and here's the experimentally measured ones, and here's the theoretically simulated ones. Again, below threshold, you see a broad light emission, above threshold, narrow light emission, and again, this threshold-like behavior and S-type plot again. In fact, this work has been published late last year or so. And again, hard work of Nine Wong and plus Wei Wong has really paid off. And so again, these are very useful for photonic integrated circuits, and where you can put a waveguide, couple the light to other parts of the photonic integrated circuits also. That's what we're exploring at this stage. So ultimately, what we want to do is that we want to make electric injected lasers. But the challenge is that you make a PN junctions, and you may make good electrical contacts and all these things. And in fact, this work of my former student, Dr. Insoo Kang, who is now at Samsung, and where he spent a lot of time in optimizing the P-type doping of indium phosphide using selective epitaxy, has grown indium gallium arsenide quantum well. Here, this is the yellow one here, and then the N-type indium phosphide with silicon doping of indium phosphide here. Again, to cut the long story short, and you can see that he is able to mimic these ones and be able to grow these structures and made these contacts on both ends of the nanowires as well. And then you measure the IV characteristics, showing like a nice diode-like behavior, showing that the hard work of Insoo really paid off. Then he injects the current into these nanowires, and then look at the light emission. You can see higher the amount of current you're injecting, higher the amount of light coming out of these ones. And then you also see two peaks, because a quantum well which is sitting on the top has got a different composition and thickness, and then emits at a different wavelength than the lateral quantum well on the sides, and this emits at this wavelength also. You can see despite pumping large amounts of current, you are really not able to really get any lasing from these ones, only you're increasing the light intensity. You don't see also threshold-like behavior. Again, this work has been led by my young colleague, Professor Lan Fu. You ask the question, why? What's the problem? You make PN junction, you're making contacts. Why you're not able to get lasing? But it turns out you need to make metal contacts to be able to inject current into these nanowires. But then, metals have got optical losses. Then you create a lossy cavity. That lossy cavity leads to, and of course, then you need to pump harder. If you pump it harder, it creates a lot of heat. That means gain comes down, and it becomes like a vicious circle or so. So now I got a student, Nikita Gagrani, who has been spending the last 4 years replacing these metals with indium tin oxide, aluminum doped zinc oxide, and transparent conducting oxides to minimize the losses and still be able to make good ohmic contact. It's been a really challenging problem. Despite her hard work of more than 4 years, we still have not been able to demonstrate it. And I'm hoping that in the next 6 months also, she's able to solve that particular problem. INSIC also made this array of nanowires LEDs, And so then he's able to show that he can really get again bright light emission. And we embed this some polymers in the between so that you can make thumb contacts in this case. So advantage of that one is you can peel these nanowires, particularly for flexible LEDs, particularly Samsung and Apple and others want to create a foldable phones, foldable computers or so. So you need to have the foldable displays, and that's where INSU can spend a lot of time in optimizing these conditions also. So again, using this resonant behavior of these nanowires for photo detectors as well. And in fact, is a case of this work of my young colleague, Dr. Jian Lee. And where it turns out that changing the diameter of the nanowire, the resonant wavelength of this particular nanowire could be shifted. So by choosing the right kind of sets of nanowires of various diameters, and you're able to really make a multicolor detectors, and that's what we're aiming for. And in fact, we demonstrated last year dual band multi-wavelength detectors also, and where these resonances really play an important role. And here's a case where we actually simulated ones, and here is experimentally measured ones. They really match very well. And in fact, using these ones with my colleagues with the University of Western Australia, we're able to in fact image these ones, and they worked out really well. And again, Zion Lee's hard work really paid off from that point of view. Let me finish off with the last topic of terahertz radiation. And terahertz radiation, all of you know about it, and particularly this is important for security applications and wireless communications and biomedical imaging applications or so. And 1 terahertz is about, just to remind you, 300 microns in wavelength. This is a work of jointly with Oxford University, where this work of my former student, Dr. Kun Pang, who is now a postdoc at Oxford, transfers a nanowire and makes contacts using electron lithography on a quartz substrate. You excite this nanowire with a laser pulse to generate photocarriers. You come up with a terahertz pulse, and then the electric field of the terahertz pulse separates these carriers. You measure the photocurrent as a function of time. And again, to cut the long story short, and during her PhD, she's demonstrated gallium arsenide single nanowire terahertz detectors with a broad bandwidth, as well as indium phosphide terahertz detectors. And she needs to design these bow tie antennas, and then where the nanowire is sitting in this bow tie antenna here. That's how we're able to demonstrate this bulk reference here, simulation expected here, nanowire detector here. We're able to show the compact detectors as good as that of the bulk reference samples, which are very good for terahertz imaging applications also. That most recently, and we've demonstrated the polarization resolved terahertz detectors, which are operating at room temperature. You can measure the amplitude and phase as well as the polarization state. The challenge has been to be able to put these nanowires in the 90 degrees to each other without making any physical contact between the top nanowires and the bottom nanowires. In fact, she spent about 3 years in optimizing these particular structures also. And then we're using these ones to measure terahertz metamaterial. So send a terahertz pulse to this metamaterial. It changes the polarization state. Use the detector to be able to measure the X and Y polarization. And you can see that she fabricated these structures, and then the theoretical simulation show that the horizontal polarization should have this particular transmission, and vertical polarization should have this transmission, and experimentally measure ones really look out very well. And again, this work has been published in Science in 2020, and then her hard work really paid off. In conclusion, nanowires open up opportunities for manipulation of light matter interaction at the nanoscale. I demonstrated to you nanowire lasers and LEDs, and nanowire infrared detectors and terahertz detectors, and the integration of optoelectronic devices on various platforms as well. And so I'll leave you with some information about the journal which has been mentioned, our Center of Excellence, and also our endowment with that. And I'm happy to answer any questions you may have. Thank you for your attention.
Thank you, Professor Jagadish, for an excellent talk. And there are so many, nice things that you have presented. Really wonderful. The talk is now open for any question. Yes, there is a question in the chat box. I'm reading it for you.
Yeah, sure. Thank you.
Excellent talk. What are the main benefits of nanowire LEDs, particularly for large-scale fabrication and deployments?
Okay, the nanowire LEDs, two advantages. One is that whenever you want to have a nanowire, small laser light source, for example, if you want to use it for sensors, disposable sensors, and all these things, single nanowire LEDs were very useful from that point of view. The nanowire LED arrays, and most importantly for flexible display applications, because I told you that we're embedding these things in a polymer, then we're in fact demonstrated that we're able to peel these things off. That means they could be very useful for flexible display applications, and that's why we're making use of these ones. Our original aim was to make nanowire lasers, and which we are still working on, But then meanwhile, we found a new opportunity for to be able to make use of these ones for making LEDs, which Samsung and others are interested as well.
Thank you. There is another question by Dr. Vinod Singh Rao. What is the laser damage threshold of nanowires? Optical pumping. So that's what probably asking.
So this is typically they're about microjoules. They're optically pumped. They're not electrically pumped. And in fact, as I told you, that we are not able to make electrically pumped nanowire lasers yet. And that's been a major challenge for the entire community. And so we've been working on this project for about 5-6 years to be able to really solve these metal-related optical losses and other things. Typically they're in the tens of microjoules per cm square or so. We make use of the pulse lasers to be able to look at these things, because you don't want to create too much heat. So that's why it is important really to be able to not use CW lasers to pump these lasers. And then that's why we end up using pulse lasers.
Yeah.
And of course, the quantum wells have got about half of that with the gallium arsenide nanowire itself, because quantum wells have got a higher gain.
Okay. But I think the damage threshold should be similar to bulk, which is, I think, megawatt per centimeter square for all these materials in that range, basically.
Of course, that's where the challenge is. That's where I think you really need to heat dissipation is a major issue, Tarun, and that's something which we need to always keep in mind when you're dealing with nanostructures. And then how do we be able to extract the heat out very efficiently? And that's what we're exploring. And in fact, we're trying to also really put these ones onto diamond coated glass structures and other things, and to really dissipate some of that heat. But then diamond has got a higher refractive index than glass. So that means the optical field starts pulling into the diamond as well. So that's something which you need to worry about as well.
Yeah. There is another question from Professor Shobha. How to discriminate between pump wavelength and emission wavelength, because they are different intensity at nano or micro scale.
So generally, what we do is that we use the pump wavelength at a shorter wavelengths or higher photon energy, and typically the emission wavelengths are at smaller photon energies at the longer wavelengths. And we try to what we end up doing is that we try to take essentially split the beam and then try to measure the only allow one particular beam to go through the system.
Another question: how to
notch filter? Essentially, put a notch filter.
Yeah. How to remove a single nanowire from a bunch of nanowires and place it on another substrate. Anyway, that's
Okay. So this is something, but there are two ways you can do that one. One thing which we do is that we take the nanowire substrate and then we rub onto the other substrate, and then basically most of the time these nanowires will start transferring onto the other substrate. The other way of doing that one is that you can put this nanowire substrate into some alcohol like isopropanol or something and put into an ultrasonic bath, and these nanowires break off. And then you take a pipette and take one of the liquids and then put into wherever you want. And then these nanowires are, of course, randomly distributed. And you go and identify that particular one. You make contacts using electron magnetography, looking at those ones as well. That's how we end up doing
it. And I think there is no other question in the chat box now. And let me see. Yes, I think it's done now. And anyway, I can keep on discussing with you for long, but suddenly I have to stop myself. But I will still ask one question. See about this electrically pumping of nanowires, which is very much required, and you have been trying for that. I could see because you are putting your nanowire on the contact basically. So the contact area between the nanowire surface and the contact pad itself is very little. So did you try to give it another coating at the end? It is difficult, I know, in nanoscale, but that could probably help.
No, what we end up doing, Tarun, is that's a good question. That what we do is that we put the nano, you see, means a strip of the metal on the sides, and then we try to have a bigger pad outside. So then you can really connect to the outside world afterwards. Otherwise, that becomes too bulky and then it becomes messy as well. One of the challenges also, because of the fact that the geometry of the nanowire is like hexagonal facets and other things, try to get a good metal contact and other things also becomes a challenge as well. That means you need to have a uniform injection of carriers as well. So if you're non-uniform injection of carriers, that means one part of the nanowire is acting like a gain medium, another part is acting like absorption region, which really doesn't help you. That's where there's lots of challenges which you need to address. That's been the major challenge of uniform and injection of carriers, and with low contact resistance, so that you're not creating heat and creating problems for yourself.
Yes, that's in fact that is a bottleneck for that application.
Exactly.
Okay.
Exactly.
Yeah. So with that, I think let's thank Professor Jagadish for an excellent talk and answering questions that nicely. Thank you so much, Professor Jagadish. And it was indeed a pleasure to have you. We know each other for many years, and it was good to see you at that in analysis, especially.
Good.
Thank you so much.
Thank you, Tarun, and good luck to all of you. And so thanks again for inviting me to participate in your conference.
Thank you. Thank you so much. Friends, now let's move on to the next talk. And next talk is going to be given by Professor Shukla. Professor Shukla is a professor at IIT Bombay, Mumbai, India. She obtained her PhD from sunny Buffalo, USA. Prior to joining IIT Bombay, she was a postdoc at Harvard. At IIT-B, she has been working on nanophotonics devices, water-related technologies, metamaterials, and plasma devices. Shukla has published articles in several journals. She currently serves on the editorial board of Scientific Reports and Journal of Physics Photonics by IOP. She is currently heading the Water Innovation Center at IIT-B. Today, she is going to talk on additive manufacturing of sub-wavelength resolved 2D, 3D freestanding micro nanostructures. Professor, over to you, please.
Thank you, Professor Sharma, for your kind introduction. I'll just share my screen. Please let me know if it is moving.
Sure.
You are able to see it. Is it visible?
Yes.
Okay.
You can make it full screen. Thank you.
Okay, great. Thank you very much. So thank you everyone for organizing this wonderful NLS. And I still remember looking at NLS as a student, and now I'm becoming part of it, giving a talk in NLS. It's definitely very prestigious and it's a great honor for me. And also, I would like to thank organizers to put my talk right after Professor Jagdish's talk, because he has nicely introduced the subject, which kind of related to what we are also trying to achieve in a slightly different manner. And some of the things that he has introduced, we will be talking about how we have taken it, and we have been following his work from quite some time. And I hope this would allow me to have more collaboration in India and abroad. And I would be very much happy to interact with you even after this session through email or other mode of contact. So with that brief introduction about what we have been trying to achieve about this nanophotonics field. So today I'm going to talk about the additive manufacturing of sub-wavelength resolved 2D, 3D freestanding micro nanostructure. As you can see in the background, we have a diffraction image of something which we have made at that micro scale. And even this our institute emblem, as well as national emblem that we have manufactured at the scale of this 250 micron or 200 micron by 200 micron. And it's not just the picture, but also like all the Hindi text and all. If there will be a time, I'll maybe show you the kind of things that we could achieve. Before I go into the technical details of the work that we have been doing, I would like to acknowledge the work that is done, that I'll be discussing today. It's done by 4 people. 3 are shown here, Arun, Shweta, and Ajinkya. There is another student, Gaurav, who was also instrumental in doing some of this work. So with that, also, I would like to acknowledge my funding agencies for generously funding me for developing this facility in-house. It's not a bottom facility. We built this facility from the scratch, and that allows us to have a much more control over the things that we wanted to achieve. So this will be the outline of my talk. Initially, will be I'll be talking about why are we doing this, what are the fabrication issues, and why the approach that we have taken, and then finally few applications that we will be we are trying to get, or we are trying to at least address the issues. So before I go into any of the motivation, exactly why lithography, I think I should take a step back and talk about a very famous line. There is a plenty of room at the bottom. I'm sure all of you are aware of it. Back in 60s, when people, when somebody was saying this, nobody would have thought that this will become a reality. And within 50, 60 years now we are here. already we are using some of the nanostructure materials in our day-to-day life, and our laptop is one of the best example. And this actually gives a very nice introduction about where we were almost like 100 years back, and now we are here, especially with the CMOS technology. If you see the kind of growth that it had seen, and thanks to Gordon Moore, or thanks to Intel, we should say that CMOS has like had an exponential growth, but now it has reached to a limit where now even Intel is facing a problem, and some of the other TSMC or Samsung have now rolled out to even like 7 nanometer technology, which Intel is still having an issue with. But nevertheless, the future is definitely aligned with the plasmonics or photonics or somewhere at the intersection of all of these. So nanophotonics is the way to go, and the next big thing which is going to happen in our field is definitely going to be very, very small. So when we look at the nanophotonics, it's actually a marriage of nanotechnology with the light. Okay, so it works at the interface of many engineering branches. So if even if you look at the kind of profile of all the speakers of NLS, people are from electrical engineering, from physics, from chemistry, from nanotechnology. They all are trying to work at this interface, which is the most exciting interface, and the metaphotonics, which even Professor Jagadish introduced, and we are also trying to address some of these issues, are also a kind of a sub branch that is coming out from the nanophotonics. So devices that exploit this nanophotonic phenomena are enormous. And this is something which has taken center stage now, but optical filtering, photo detection, lasers, and solar cell are the applications which are right now, even we are using some of these devices which are based on these technologies. So how to achieve these nanophotonics technology, that is the major focus that we are having. And if you remember, almost like 40-50 years back, when silicon was the center stage, I remember there was a talk in the morning when people were talking about now the next generation lithography will not be as slow as the kind of growth that silicon had seen. And maybe next 10-20 years, we will be seeing the technology which, or lithography based technology, or the kind of exotic technology that we will be using for patterning. So optical lithography, which is mostly using the electromagnetic wave and charged particle, then X-ray ion beam comes into the picture. That is one way of achieving or patterning any material in order to get the kind of devices that we would like to realize. So devices, when I'm saying devices, doesn't mean any particular. I'm talking about general photonic devices or the kind of electronic devices that we are dealing with, FET including. Then there are imprint-based lithography, especially if we are trying to make small structures and molecular structures. Then SPM-based technology, AFM, STM, and these things comes into the picture. There is another way of looking at this lithography. If we want to divide it, whether the top-down approaches or the bottom-up approaches, the demarcation is not really very clear, but in general, we can see we start from a bulk and then we go towards patterning or making it smaller and smaller feature. Whereas bottom-up approaches, we start from atomic scale or molecular scale, and then we try to bring it together, and then ultimately we try to see how we can make the kind of a useful structure or useful architecture that we can exploit for various applications. So top-down approaches are photolithography, e-beam lithography, X-ray lithography, interference scanning probe, and so on. Similarly, bottom approaches these are some of the approaches that I have mentioned, not exotic list. Then comes the direct laser writing. Some of the people may call it in one of the two, but I say it's more of a combinatorial approach that it utilizes. So why are we going away from the top-down approaches? So again, I would like to draw your attention to Moore's law, which if you see, it went very well till 2005 and 6. And at that time, people started to talk about that it's going to break and we have almost achieved all the diffraction limit and nothing can be done. And this thing has even cost of this new machine and clean room. That is what is stopping Intel to go ahead with the 7 nanometer technology that TSMC and Apple are boasting about. But actually, if you look at this, is not the 7 nanometer technology. The technology earlier, which was defined by the line width, it's no longer defined by the line width, but that is not the scope of this presentation. So when we are talking about our need is, in general, we want more number of transistors in the same kind of a space. So more processing power, that is what is needed, and that one can achieve by smaller geometries. But then there are physical limits, heat dissipation, and quite a few issues are coming into the picture, and that is what is stopping us in making or realizing this. So as I mentioned, there are many issues with the fabrication, making smaller structure, smaller feature size, sub-wavelength feature size, EUV, etc. have also approached kind of their limits, and we cannot go beyond it. And like quite few of us are from Mumbai, and we know that as the population grows and our requirement grows, instead of going horizontally, we start to grow vertically. And that is what the lithography industry is also looking at, growing in the third dimension, so growing vertically. And that cannot be achieved with the standard lithographic technique that is being utilized now. So the 3 dimension is the way to go. Then writing on the flexible substrate, because we want variable electronics, we want something which can be wrapped around, which we can carry easily, and so on. Then functional and 4D patterning, 5D patterning, people are now even talking about 6D, 7D patterning. That means adding another dimension to whatever we are patterning in 3-dimensional space, adding magnetic properties, adding fluorescence properties, adding plasmonic properties, adding any sort of the other properties and time-derived properties that are also needed. So large area, low cost, that are also required. So bottom-up approach are definitely going to take the center stage in the upcoming decade, but not currently. Bottom-up has not matured enough that we can go towards exactly, we don't have enough control over the atoms and all, so that we can go and do the 3-dimensional reliably. So combinatorial approach, which is like kind of combination of top-down and bottom-up, will be the future. And the photon-based approach may help in that one. So photon-based chemical reaction, it can result in a metallic nanostructure, which is the most important part, especially if we are going towards the electronics application in the third dimension. Sub-wavelength structure, writing 2D, 3D, multi-dimensional structure, writing on any flexible substrate. Actually, any substrate is fine. Then there are many other adjectives that can be added to this approach. So electromagnetic waves we have been using from quite some time, and ultraviolet was the one that we were using. And this is typically where the photochemical changes that we are trying to achieve. So what happens? Typically we are here and we are into the weak field excitation, and we are not able to utilize something which is can be used for making third dimensional. So that happens only when we are going into the very high intensity regime, and then perturbation theory and multiphoton excitation start to take place, and that is what we can use for making third dimensional, or we can go inside the material without getting absorbed. And that is what we are trying to achieve here, the femtosecond laser based nanolithography. And so this is some of the grating and the mesh structure. Even this kind, you can call it a micro resonator if you want, because the spacing is almost like 1 micron by 1 micron. That's the kind of cage that we have made. Then you can also call it a metamaterial, because in this kind of a fishnet structure we have made wood pile and so on. Diffraction ring to show the kind of quality of the structure that we are making. Fundamental is fairly simple if we don't go into the much of a detail. Sorry. Okay, so you have a visible light, and typically material have a like linear absorption in that range. But if you have an infrared absorption where this material is transparent, material directly in the linear regime does not absorb anything. But in the non-linear regime where the intensities are high enough, we can have a kind of a polarization that gives rise to this kind of a phenomena. Sorry. And we can have this 2-photon absorption. So simultaneous absorption of the 2 photon to fill the band gap of this material, or the reach to the kind of excitation that is needed, and then we can make changes in situ into that one. So this is actually that is shown here. If you have a beam of light that comes in, and you can go inside the material and make changes into the material into the 3-dimensional that it is moving in. So it will retrace the path of the beam. That is another way of looking at it, because microstereolithography is one of the most common technique that people are using. So just to give you a kind of a comparison, so this typically use 1 photon absorption, and you write layer by layer. So here you have a 1 layer of polymer in the microstereolithography. You do polymerization, and then you just build layer by layer, and that's how one can make 3-dimensional structure. Only thing is resolution is limited by, so 1 micron is the best I'm talking about. Typically you cannot make less than 5 to 10 micrometer in 1 layer, and because of material limitation as well as the other process parameter limitations. Multi-photon lithography, as I mentioned, you can go inside the material and the changes will only take place where the beam has a very high intensity, and the intensity where this 2-photon absorption phenomena can take place or multi-photon absorption phenomena can take place, and you can have the resolution around 100 nanometer or so. You can have like any kind of 3D structure that you can envision. So this is the kind of system that we have built at IIT Bombay, and so we are very proud that this is one of the kind of a system in the kind of a whole world where it's not in the clean room. It's whatever the things that we have achieved, it's at room temperature, and the resolution that I'm talking about is almost like sub-wavelength. So reliably we can make 200 to 300 nanometer structure in the room temperature in room ambient conditions. So this is a kind of a system, and this is the lab program with which we have automated entire unit. So it's like fully automated click-based system that we have developed. And this is a wood pile structure. If you see, actually it was the initial plan was to make a spatially varying photonic crystal. And then we ultimately, we made that, but along with that, we made this wood pile structure. You can see some of the ropes that are that are down there. And this is the edge of this especially varying crystal, and the sizes are very tiny here. This is a 3-dimensional structure that we have made. So now I would like to emphasize we are not really limited to polymeric structure. As I mentioned, we want to incorporate multiple features into this structure. So we added dye, we made various functional structure using that. Then 2-photon dyes were very expensive. That was a major limitation of popularization of this femtosecond approach. So we moved towards dye-less lithography. So after I moved to India, we worked on some of the material system. We removed the dye with some of the inexpensive photoinitiator. So 2-photon absorption cross-section of typically photoinitiator is less. So we compensated the amount of dye. So we removed entirely dye from this picture, and the photoinitiator, which has a slightly higher GM values, which is kind of 2-photon absorption cross-section, and we overdoped it, and that's how we could make this dye-less polymeric structure. So a starfish kind of a 3-dimensional structure that we had made. Then we moved towards this dye-less gold polymer, dye-less, I believe we have done silver, copper, and so on. Then recently we moved towards the fluorescence carbon quantum dot system. Carbon quantum dot has very huge 2-photon absorption cross-section, and that is what we doped, and we were able to make very high aspect ratio, 1:20, 1:10 kind of aspect ratio, micropyramid, and quite a few other structures that I'll show you in a couple of slides later. We have now moved towards the ceramic-based system, so quite a few ceramics. It is mostly for these kind of optics application. So we, due to this disclosing issues, we cannot exactly tell you what actually we are using, but any ceramic we are able to pattern now. And now we have moved towards graphene oxide, graphene silver, and so on. Now even we have been able to incorporate magnetic and magnetoplasmonic structures into these 3-dimensional and 2-dimensional structures. So principle is fairly simple. Okay. So I'll just quickly show you this animation. So you have a laser that falls onto this system where the 1-photon absorption takes place, and simultaneously it absorbs 2 photons to fill whatever the band gap that is required for starting the polymerization and radical polymerization process starts. And ultimately, it whenever the it meets the end of the another photoinitiator, this process finishes. The macroscopic view is shown here. So wherever I'll shine my light, you have a polymer mixture with any of the 2-photon absorption material, and then polymerization process will start to the place where this light will be shining. So this is one of the real-time video of the 3-dimensional pyramid structure that we have been making. So we typically start from the top because we want to go towards the bottom where the surface adhesion we can improve upon. And it's always better because the refractive index will keep on changing from the top, and if we'll just then it will start to scatter the beam, whereas polymer is more or less transparent to especially the monomer and oligomers are transparent to the IR wavelength. So that is the freestanding 3D resonant structure that we have made, the fluorescent one as well. So how we are able to control? So this is just only one parameter that I would like to show you, and rest of the parameter I did not show because this is the most important parameter. So with the laser power, we just keep on reducing the laser power, and we'll have the we see that the line will keep on reducing, and then at this this is the threshold value. At this threshold value, if you look at from here, so you just kept on increasing the power. If you go from this side to this side, and at the threshold value, you'll start to see the polymerization. And when you go slightly above, you will be able to see the increase in the voxel size. It's actually the 2-dimensional, that is what you are seeing. So it looks like it will be a perfect sphere, but it doesn't. So there is a point spread function that defines actually how much would be the width and so on. And these are some of the gratings that we have made. So the structure that we are showing here is this is a gold loaded structure. This you can see very finely spaced grating, and the line widths are in the range of 200 nanometer or so. This is a gold varying spacing gratings to show the quality of the structure. Again, we made a spatially varying grating. So spaces from 5 micrometer to 1 micrometer or even 0.5 micrometer to show this. You can like a very fine blue colors to the near infrared kind of a light that one can see. We have been using it for various applications. This is the one application where we have shown this kind of focusing of light. So it's a diffraction as well as this plasmonic phenomena that gives rise to the increase in the. So this is a achromatic achromatic focusing of the light, and so this is a silicon solar cell. On top of it, this is a tiny structure because at that time we did not have enough travel range to cover this 4 mm range. So we have put our structure concentrator, and we could see increasing the performance of the solar cell. So this is the recent work that I was talking about. So this is a fluorescent structure that we have we were able to fabricate. So CQD was used and the photopolymer as a 2-photon absorber. So 2-photon absorption takes place. This is a typical UV absorption that you see. And in the 2-photon regime, you are able to go and make 3-dimensional structure. So this is a the process flow. And ultimately, we have made like grating structure to show again that we are able to make in the what kind of quality, whether it's a 3-dimensional, 2-dimensional wire, standing wave formation. So there are quite a few issues that we have addressed, and then ultimately we were able to make. So actually, this line that you are seeing, actually, we forgot to switch off the light. Actually, this was a software glitch. So then we made it, and then we found that, see, there is a uniform stress and then non-uniform stress because this is thinner, this is thicker. And that's how we were able to even check the kind of a mechanical property of this system. I'll skip this slide in the benefit of time. This is to show that with the increase in the, with the increase in the power, you will just keep on increasing the line width, or you can look at it the reverse. And as expected, with the increase in the carbon dot loading, one can reduce the power that is required, and one can always make a thinner and the better structure, but there is always a limit beyond which one cannot go. So this is the optical image of the grating and the fishnet kind of a structure and so on. And then this is the fluorescence and the combined image of the same thing. This is without any carbon dot loading. Okay. So this is a top view and this is the side view of the same thing. As this is just a zoomed view of something that I was telling you earlier, whether the uniform stretching and the non-uniform stretching, and the fluorescent structure top view. So this we were developing for this drug delivery application. So that was a pointed needle, but then we had 3 other applications in mind, and where this coaxial or the flat bottom needles were there. So kind of a mosquito nose from which it sucks the blood. That kind of a bio application was also required, and for that we made these kind of structures. And so again, this is a fluorescence and the dark interference contrast image to show the quality of the structure and the uniformity of the structure that we made. We had some fun as well. We wanted to make our own micro chess. So this is like within 240 micron by 240 micron, we made our own chess, and you can see the kind of structure that we made. So recently there have been a lot of attempts in, instead of making a fully solid structure, kind of a mesh kind of a structure, because it the performance is exactly same. Actually, mechanical properties improves even further because it can absorb the shock even more. So that is also we try to achieve, and we have made these kind of structure. We are now looking at the other properties and utilizing it for other applications. Just to show the kind of strength that we have done even tiling to show the structure in almost like 3 mm by 3 mm area. And you can see from the color, the kind of quality of the structure, the uniformity that we are able to make. We are trying to explore some of these applications: metamaterials, photovoltaics, biosensing, including the Raman spectroscopy, drug delivery, microfluidics. This is something which we have been approached by this Rutherford lab, and they were trying to use these micro cages for a nuclear application. So we are still not very sure how they will be using it because of this. I think they would not like to disclose it. So again, this is a showcase to show the kind of structure, the kind of things that we are able to make. Very tiny, very refined structure. Even Jnanam Paramam Dhyayam, even a DST logo, you can read if you look closely. Satyameva Jayate. Due to paucity of the space, I did not maximize it. Some of the chiral structure, some of the metamaterial structure, then the grating, the like fixed spacing grating. You can see the purity of the color and the kind of grating that we are able to make. With that, these are some of the three-dimensional structure, optical resonator structure, sorry, I'm not able to recall. So this is our own Jesus, then the coaxial resonator, the pyramid structure, the starfish structure, the all sort of gears, and the fixed closed loop needle, open needle, and so on. This is a fishnet and the diffraction grating, diffraction pattern to show the kind of quality that we have here. Again, this is the camera phone images to showcase the quality that we are making. This we are trying to, now we have loaded it with the dye, we have loaded it with the CQD. Now we are trying to calculate the Q factor of this resonator, and we are actually looking for a collaborator to look at it more closely, and for a single shot experiment where we can see what kind of motives is going to support and how we
Shukla,
can
probably if you can conclude quickly, that may be better.
Yeah, sure.
There are some questions for you. So,
sure.
Yeah.
Sure. Thanks, Professor. So these are some of the metamaterial structure that we have been making and simulating those structures. So this is one interesting application which is like very common for all of us that we have made. So this is a micro QR code. Actually, this is a fluorescent QR code. This is hidden behind this non-fluorescent micro QR code. And so if you can see, there is a shroud also that you are able to see. And we are going to approach it for we are going to implement it in quite a few new kind of devices, especially for the army applications. So I'll just quickly run this 1-minute video to which actually talks about some of the things that we are doing, but not actually all.
We present the micro QR code in stealth mode for anti-counterfeiting application. It's a dual-layer architecture and involves two-step fabrication. The QR code is fabricated in emissive resin and is cloaked using a non-emissive resin. The fabrication of QR code is carried out by using two-photon lithogram. We can observe here the fabrication of micro QR code in the emissive resin over an area of 50 micrometer by 50 micrometer. Now, once the fabrication of QR code is completed, a cloaking layer is fabricated exactly on top of the QR code in a non-emissive resin. Now, if we observe the final fabricated cloak structure under white light, it appears as a simple block. But if we observe the same structure under UV illumination, the hidden QR code can be seen, and the readout can be obtained by using any simple QR code scanner.
So this is another thing that we are trying to achieve using this. I'll not run this video. So basically what we have seen, there is a change in the output intensity when this coupling takes place. So this is again a CQD-based system that we have made for heavy metal sensing. There are a few other applications that we would like to explore in the near future. With that, I'll stop and I'll be happy to answer any question that you might be having for this lithography.
Yes, thank you so much, Professor Shukla. So in case, because we are running out of time, so maybe one or two quick questions we can take. So one question is like, what is the smallest structure you have achieved with 800 nanometer pulses?
Almost like 140 nanometer. That is, I'm talking about the reliability. So like long area, we were able to make 140, and that with in the 3-dimension as well.
And another quick question is, what are the characteristics of the zero index photonic crystal metamaterials? Some brief characteristics.
Okay, so it's the negative refractive. If we are talking about zero, then we are not talking about the negative. we are talking, so n is equal to root mu epsilon. So you can play with the permittivity and permeability of the structure. Then if you are talking about the chirality, so that is where this chiral kind of swastika, if from Indian sense we can talk about swastika, otherwise technically Gamadian structure. So then you can play with the epsilon and mu are the material inherent property. And we are talking about the metals, then mu is anyway out of picture, and it's very tiny, but the epsilon is negative for most of the metals. And that's why the metals, plasmonics, are the most important for metamaterial or achieving zero index or achieving the negative refractive index. That is important. But this chiral thing, if we can play with this chiral and instead of now concentrating on mu and epsilon, and we can make a sufficient enough chirality, because typically chiral values are very tiny, and that's why whenever we talk about the refractive index, we say n is equal to root mu epsilon. We don't talk about chiral at all. But this chiral, if you can introduce these kind of structural parameter, that's why strategic patterning is the most important parameter for metamaterials kind of structure. For photonic crystal, zero index is actually not really achieved with this kind of metamaterial kind of approach. The approach is slightly different from photonic crystal perspective. It's a slowing down of light. So that approach is slightly different from metamaterials perspective. That's why this metaphotonics is the range where when we are talking about the parameter with which we are able to sweep the refractive index of a material. I hope I was able to answer some of the queries.
Yeah, I think we can take one final question and maybe you can give a quick answer to that.
Sure.
Please give some idea about the lithography techniques of holes in slab and rods in air-based photonic crystal devices, and which type of photonic crystals are easy to fabricate.
So photonic crystal, when we talk about, so our group is pretty active in this self-assembled photonic crystal. So not necessarily you need laser for photonic crystal. You need a very good, if you have even decent enough in chemistry, you can make your PMMA or polystyrene based nanoparticles, 100 to 200 nanometer particle, and you just let them self-assemble, drop cast them. If you have a good quality photonic crystal, it will assemble into the three-dimensional opal kind of structure, and then you can refill it and make inverse opal kind of photonic crystal. So now if you're talking about reliably making holes into a slab, femtosecond laser, typically it has a sufficient enough power to make a hole into any slab or rod, and you can make this air and the other refractive index material, the kind of structure that you are talking about, that you can make. So femtosecond laser, especially if you are going towards the 3-dimension, that is why it becomes important. Otherwise, people have shown, even we have also shown the continuous 532 nanometer laser beam with the interference holographic lithography. That also you can make a kind of a grating. So 2-beam grating, then if you are adding 3-beam, you can make a hexagonal, but that will be 2D or quasi 2D structures. And easiest one is definitely self-assembly. Otherwise, the second easiest one will be interference lithography. The third one, I would say you go towards the laser lithography, especially femtosecond, because it seems simple, but building this system took me 3 years. And then automating it and then finally controlling it, it's not that straightforward. Everything seems simple, but in reality, even when I talked about this question of with Professor Jagadish, discriminating between the pumping and the emission wavelength and the notch filter, they're so close. The notch filter doesn't work. There is always an overlap and it will get shadowed. So things look pretty simple on paper, but reality, a lot of efforts are needed for doing any research. I'm sure all of us are aware of it.
Yeah, but in that context, because I work in the same area, there are ways to do that. So it's, in semiconductors, we have several other things to do. So that's not an issue. And in your sub-wavelength lithography, you mentioned about 200 to 300 nanometer smallest resolution that you could achieve. What is the largest area that you could get, basically?
So mostly we are doing tiling. So we use piezo stage, which has a travel range of 300 micron by 300 micron. So we make tile of 300 micron by 300 micron with 2 nanometer resolution. So that is the kind of resolution that we have. And then we tile. So currently we have shown up to 3 mm by 3 mm. But it is only limited because of our travel range and the time it takes. So making 3 mm by 3 mm, it takes 18 hours. So
It's a
that
lot
is
of time basically.
right,
Yeah.
because you are right, you are going like 10
Correct.
a step.
Yes, yes. Yes.
So other than that,
Step basically.
right, right.
Okay. So with that, let's thank Professor Shobha Shukla once again for giving an excellent talk, a very nice piece of work which is being carried out at IITB.
And I think
for
I'll
all
talk
those who are
to you, Professor
interested,
Sharma, for
yeah,
because we are looking forward for some of these things where this notch filter issues that we are not able to resolve.
yeah, sure, sure. And certainly, like who want to interact, she is there at IITB, so no problem, they can do that. So thank you, Professor Shukla, once again. Thank you so much.
Thank you, Professor
Okay.
Sharma.
So now let's move on to the next talk in the last talk in this session. And the last talk is going to be given by Dr. Jitendra Kumar, who is a scientific officer F, and indeed is my colleague at RRCAT. Dr. Kumar joined RRCAT in 2006 from BARC Training School at RRCAT. He obtained his PhD degree from SBI in 2018. Dr. Kumar has worked on dye pumped copper vapor lasers, nonlinear frequency conversion, fabrication of customized fiber break gratings, fiber break grating, base temperatures, strain and refractive index sensors, and so on. In fact, at RRCAT, they have an excellent facility for the fabrication of fiber grating and associated devices. Dr. Kumar has published about 100 papers in journals and conferences and has received Group Achievement Award from DAE and also the OSA Student Prize. Today, he is going to talk on the technology development and application of fiber break grating sensors. Dr. Kumar, over to you. Thank you. Please go ahead. Can you hear me? I think you are muted, it seems. Yes, please unmute yourself. Yes, yeah, now you can go ahead.
Okay,
yes.
is it visible? I think.
Yes, yes, please go ahead. Your slide is visible, very
okay.
clear.
Okay. The title of my talk is Technology Development and Application of Fiber Break Grating Sensor. Basically, in this talk, I will discuss something about the fiber break grating that is being developed at RRCAT and the application where we are using these fiber break gratings in, I can say, for in the market, or we can say in the research groups or various laboratories where we are using this type of fiber break grating. And the outline of my presentation will be like this. First, I will discuss about the requirement of the sensing system. And then the requirement of then fiber optic sensor. In fiber optic sensor, I will discuss about the fiber break grating sensing. Then FPGA sensor activity at RRCAT and its characterization, and finally its application and deployment in different areas of basically research or I can say industry or in Indian railway safety. And first of all, requirement of sensing system. Nowadays, this sensing system, it should be it is required. Why I am showing two figures in this first slide. In the first figure I have shown, it is the Vasai bridge of Mumbai. Actually, it is in the depleted condition, and nowadays people are not using this bridge, and even government has started dismantling of this bridge. The reason is that there was a certain crack was there in the middle of this bridge, as it is evident from this figure. So people were still using this bridge. To avoid the use or to avoid any type of accident by using this type of bridge which have some cracks, some type of sensor should be installed on these bridges, and that should be something like distributed type of sensor should be there, so that the information regarding this crack can be taken I think in real time. Basically, we can have the information of this type of bridges, so that these accidents can be avoided. And in the second slide, second figure, I have shown that report was there that this train crashes, some train crashes happens due to the cracks in the railway lines, or some I can say some wheels, defective wheels. If timely information can be taken using these sensors, if there is some crack in the railway line or some wheel is not working properly, it is flattened, so that will be useful for mankind. And in the third example, I have shown these wings of an aircraft or this aeroplane. some first crack is shown in this, basically in this figure. And as this aeroplane moves in, it moves, this cracks propagates further. And these type of cracks may lead to the accident or the severe accident, and that is very harmful. So some sensors need to be installed on the wings of this type of aeroplanes so that we can timely have the information that we should avoid using this type of wings, or we should go for the better replacement of this type of wings, or think for some other solutions. And this fourth slide, this is regarding our department, basically radioactive waste management in India, in which this radioactive waste is basically canisters of the vitrified waste. They are kept at the ground in the below the 3 meter of the, or the below the ground at certain depth. At that depth, the temperature monitoring is required so that the radioactivity of that product or that waste material can be identified. So if the radioactivity of that waste material is decreasing, we can say that the temperature is also decreasing. So temperature monitoring system at this type of location is required. Nowadays also, these solutions are already available. Means for strain sensing, electrical strain gauges are there, and they are working very properly. And they are giving much useful information. And for temperature, thermocouples and RTDs, IR sensors, all things are there, and they are providing very useful information. So what extra is needed? Means what are the things that are needed that we are not getting with these thermocouples or these strain sensors that are already in the market? The first thing is the real-time monitoring of parameters. And so second one is the fast response of the sensor. Third is the distributed sensing. Like we want to monitor the crack in the bridge at several locations. In that case, if the strain sensor, commercial electrical strain gauges are there, and if we want to use, we have to place many of the sensors there. But there should be some solution in which the single cable should be sufficient to provide the information regarding the distributed strain in these type of bridges. And then remote location sensing, and accuracy of the measurement should be there, and sensor should be able to work in harsh environment like radiative environment. And for the real-time monitoring, I can say some incident happened in Mumbai in 2006. Some water of seawater got sweetened. At that time, people started drinking, considering this as a holy water. So at that time, a sensor was needed, a real-time sensor was needed that can provide the information readily about the concentration or the composition of the water at that time, why this is sweetened. So can we think for a common platform? So that we can measure this type of all type of parameters like temperature, strain, pressure, vibration, reflector, all type, either separately or in combination. So the answer is yes. And the platform, that the suitable platform is an optical fiber. What is an optical fiber? Optical fiber is basically a transparent, it is a type of wire that is transparent, and it is made of either of glass or plastic. We are using basically at our RRCAT, we are using mainly the glass optical fiber. And the sensor, fiber optic sensor that uses this optical fiber, that works on the principle that when the light is passing through this optical fiber, and there is some perturbation that is affecting the performance, that is affecting the properties of the light that is passing through the fiber, and we have a detection system that by which we are monitoring the change in the wavelength or intensity or polarization or phase, so that we can estimate what is the value of the perturbation, and that perturbation may be temperature or strain or anything else. This is the basic principle of fiber optic sensor. Advantages of optical fiber sensors. Basically, size of the optical fiber sensor is of the order of around 0.25 micron, and its size is comparable to the human hair. So it is very small in size. So it can be easily integrated into wide variety of structure without affecting their structure. Okay. Then normally inaccessible areas are allowed due to these optical fibers. We can use remotely. We can monitor the sensing sensor. Basically, this about the information about these parameters. And these type of sensor are immune to radio frequency, microwave, and EMI, and they have high resistance to the ionizing radiation. They can work in distributed mode, and they provide high accurate information and fast response. Classification of fiber optic sensor. Fiber optic sensors, based on this I think they can be classified in 4 types that are based on intensity, phase, wavelength, and polarization. This fiber Bragg gating sensor, it comes in the wavelength modulated sensor. In case of fiber Bragg gating, we are basically monitoring the change in the Bragg wavelength. So what is fiber Bragg gating? Basically, fiber Bragg gating, it is a periodic refractive index modulation that is created inside the core of an optical fiber. In this figure, I have shown that this is the optical fiber, and this yellow one is the coating of the optical fiber, and then there is the cladding of the optical fiber, and inside there is a core of an optical fiber. The clad is made of silica, and how we are creating this FBG pattern. We are taking the interference of UV beam, and the interference pattern of the UV beam is falling on the core of an optical fiber. And since the core of an optical fiber is made of generally doping is there, germanium doping is there, or germanium boron co-doping is there, that's why we are able to create the refractive index pattern inside the core of an optical fiber. And depending upon the effective refractive index of this fiber Bragg grating and the period of the FBG fiber Bragg grating, there is a certain wavelength, that is Bragg wavelength lambda b, that is being reflected with this fiber Bragg grating, and it depends on 2 parameters. First one is the effective refractive index, and second one is the period of the fiber Bragg grating, that is lambda cap. Typically, FBG interrogators that are available in the market, they are in C band, that is 1550 nanometer. For 1550 nanometer, this lambda cap or the grating spacing is around 0.5 micron. In this figure, I have shown that if the broadband ASE light from 1525 to 1565 nanometer is falling on this fiber Bragg grating, and this fiber Bragg grating is reflecting a particular wavelength lambda b, that is I think in this case it is around 1546 nanometer. So in transmission spectra, this wavelength is disappeared. So we are having a transmission dip in the transmission spectra. Now this effective refractive index of the fiber and this lambda cap, these both parameters, they depends on the temperature, applied temperature, strain, pressure, and vibration. All these things, they depend on that. In some cases, an effective depends basically the role of an effective is higher, and in some cases the role of this lambda cap is higher. But in totality, this Bragg wavelength depends on this N effective and period, or we can say that this lambda b or the Bragg wavelength depends on this temperature, strain, and pressure. If the surrounding temperature or pressure is changing, our Bragg wavelength is changing. Principle of sensing by fiber Bragg gating is that if we could measure the Bragg wavelength change, that is delta lambda b, due to this applied parameter, we can estimate the value of that perturbation or test temperature or strain. Like if x is the external parameter, and we can calculate this change in the Bragg wavelength, 2 terms are there. In the first term, it is the basically refractive index term, in the change in the refractive index with that applied parameter, and the second term is the change in the length of this fiber Bragg grating, or the change in the length of this period of the fiber Bragg grating with applied parameter. Like for FBG temperature sensor, we can say that 2 terms are there. Delta lambda b depends on 2 terms. One is xi and one is alpha. Xi is basically thermo-optic coefficient, and alpha is thermal expansion coefficient. If we calculate by this method, the temperature sensitivity of fiber brag grating is around 13.2 picometer per degree centigrade. So for 1 degree centigrade, we should have a system that can measure the wavelength shift of around 13.2 picometer. At the same time, FBG can also be used for a strain sensing, and in this case, the Bragg wavelength depends on effective strain optic coefficient. And for germanosilicate fiber, if we use the value of this strain optics coefficient, we get the strain sensitivity of 1.02 picometer per micro epsilon. So to detect 1 micro epsilon, we should be able to, we should have the system that is able to monitor the wavelength shift of around 1 picometer. Now FBG activity at RRCAT. Up to this slide, I have shown the basic of fiber Bragg grating, how this FBG works. It is a uniform or type 1 FBG I have discussed till now. Basically, FBG fabrication facility at RRCAT, it is type of Make in India type of project. We are fabricating fiber Bragg grating using the second harmonic of copper vapor laser, and this facility is developed for the first time in India, and it is operating successfully since last 8 years. We are providing fiber Bragg grating through incubation center RRCAT to various laboratories, research institutes, universities for their various applications. And the benefit of fiber Bragg grating sensors developed at RRCAT is that we have basically full control on our laser system. We can basically, if any problem occurs in our laser system, we can replace easily. We have dedicated manpower. They are working. They have some expertise on these electronics and mechanical parts, all these things. So, and the grating that we are writing, that is also cost effective. So we are providing these gratings. Prerequisite in fiber Bragg grating fabrication. The things that are required for a fiber Bragg grating. The first thing is the photosensitive fiber. The photosensitive fiber in which the fiber Bragg grating can be inscribed. Fiber Bragg grating can be inscribed in telecommunication fiber also, but in that case, a special type of hydrogen loading is required. So we have developed that facility also. We are creating hydrogen loading also in our lab. Then a suitable UV source is required. The wavelength range of this suitable UV source should be between 240 to 260 nanometer. And our second harmonic of copper vapor laser around 255 nanometer. So that's why we are able to write fiber Bragg grating with our laser. And then an interferometer setup is required to make the fringes of this UV light of particular, like I can say 0.5 micron spacing. Then for detection system, we need some broadband size, broadband source, then optical spectrum analyzer or FBG interrogator to monitor the reflection as well as transmission spectra of the fiber Bragg grating. This is the FBG fabrication facility at RRCAT, in which the second harmonic of CVL, we are getting 255.3 nanometer. Then by using phase mask method, what we are doing, by phase mask method, we are creating the fringe pattern on this optical fiber. And by using this ASE light source and OSA, we are observing the transmission and reflection spectra of the fiber Bragg grating. Parameters of the fiber Bragg grating, that is written at RRCAT. The wavelength range is in C band 1525 nanometer to 1565 nanometer. Although we are able to write fiber Bragg grating at 1064 nanometer and 1030 nanometer also. That is useful for fiber laser applications. The gauge length of the fiber Bragg grating, it is from 2 mm to 15 mm, we can write. And the reflectivity up to 99.99% we can go. Bandwidth, it varies from the type of grating that we are writing. It is from 0.1 nanometer to 2 nanometer. 0.1 nanometer for the low reflectivity FBG we are writing, and the 2 nanometer for the FBG in hydrogen loaded fiber. And the temperature sustainability, our FBG can go up to 1000 degrees centigrade. And for strain, they can go even far beyond this 6000 micro epsilon. Type of grating we are writing, this is uniform FBG, type 1 FBG, then type 2A, regenerated, chirped, tilted, etched, and even long period fiber grating we are writing in our lab. Now, customized FBG fabrication at RRCAT as per the requirement from industries and research institutes. We are fabricating fiber brick grating, then we are encapsulating these fiber brick grating in proper packaging, and then we are basically deploying this type of fiber brick grating at certain you can say research institutes or the industries for measurement of different parameters. Like the first application, it is the single point temperature monitoring was there. Single point temperature monitoring of oil immersed ferrite cores. In this case, the challenges were the temperature was 120 degrees centigrade. So it was not a big challenge for us, but high EMI and high voltage was the challenge. Solution we provided using this type 1 FBG, that is the uniform FBG that is routinely written in our lab, and the writing time is of the order of few seconds. We can write type 1 FBG in few seconds. And how this type 1 FBG is basically defined? This type 1 FBG is defined as the basically in this type of FBG, the reflectivity of the FBG monotonously increases with UV beam fluence. Or we can say as the UV fringe exposure is falling on the fiber, this reflectivity of the FBG is increasing. This is both things are basically rising. There is no any sharp dip or any sharp fall is there. So these type of grating are type 1 FBG, type 1 gratings, and type 1 gratings were fabricated and yield characterized and installed at this temperature monitoring of this ferrite core. And what we have monitored, as the temperature of this ferrite core was increased, the temperature of this electric power, as the electric power of the ferrite core increased, the temperature also increases, and we have measured the temperature up to 110 degree and 108 degree at two certain locations. In the first figure, it is shown that this is the calibration setup used for this fiber brick grating. Then a second application was there. The aim was multi-point temperature monitoring of a gas discharge laser tube. In this case, we were having some 1.5 meter of the long tube of the laser tube, and the work was we have to monitor the temperature of this laser tube. So challenges were there. The temperature we have to measure up to 500 degrees centigrade, and multi-point sensing was required. And high EMI and high voltage, as in previous slide I have shown, it was also a challenge. The solution, again, it was type 1 FBG we have used, because the temperature sustained of this normal fiber brick grating is around 300 to 600 degrees centigrade. It can survive. For multi-point sensing, what we have done, this 5 FBG interrogator range which we were using, but it was around 40 nanometer. And depending on the sensitivity of the FBG and the temperature range that we have to measure, we have calculated that 6 number of FBG can be placed on the tube. So 6 fiber brick gratings were written in a single fiber, and that fiber was placed on the tube for monitoring of the temperature. And this is the structure, or this is the schematic of this laser tube, and the sensor placed on the upper side of this laser tube. And by monitoring the Bragg wavelength shift at each location, this temperature at that location was estimated. And temperature, I can say it varied from 467 to 500 degrees centigrade during the operation of the laser. And one sensor was kept outside just for the reference, or it can provide the temperature about the room temperature. Then the aim was the temperature monitoring system for vacuum chamber wall of dipole magnet of Indus 2. The challenges in this case were the temperature was 150 degrees centigrade. So type 1 FBG can be used. Multi-point sensing, like previous slide, we can write multi-point sensing, but since the temperature range was 150 degrees centigrade, we can write 20 fiber brick gratings so that they cannot basically overlap with each other during the rise of the temperature. Third thing was it was radiation environment. Then inaccessible area was there, and data logging they required was from outside. So our optical fiber provide data logging from outside. We provided them a bundle of a 1 kilometer fiber, and due to the small size of the optical fiber, it was easily pasted on the vacuum chamber wall of the dipole magnet. So 20 BG sensors were written in at the different Bragg wavelength and installed on the surface of this vacuum chamber wall of the dipole magnet. And this, in this slide, on the right side slide, I have shown what are the results that we have obtained using with this sensor. It is shown in this figure that as during operation of this Indus2, the temperature of this vacuum chamber wall is increasing, and it is varying from 24 degree to 37 degree centigrade. Then the problem or the challenge was there, the temperature monitoring system for storage vault at solid storage and surveillance facility BARC Tarapur. In this case, the temperature monitoring required was around 30 to 150 degree centigrade. So that can be done using type 1 FBG. This solid storage surveillance facility, basically in this facility, this vitrified waste of the nuclear waste, basically vitrified waste is kept under the ground. So they require a sensor of 3 meter basically length. Length of the sensor or the connecting fiber should be 3 meter, so that they can monitor the temperature at the surface of this ground. And the second thing was the radiation at the sensor location was around 80 gray per hour. So this was challenge for us. So to test the radiation hardness of the FBG, we have done the experiment at higher BARC. There the radiation source was cobalt 60 and dose rate was 11.7 kilogray per hour. At the total accumulated dose of around 1 megagray, what happened? That the reflectivity of the FBG decreases. But since our sensor was the wavelength encoded sensor, it was not a problem for us, because we were getting the information by the changing in the wavelength. But what happened? The change in the wavelength was also there, and it was around 35 picometer. Due to this change in the wavelength, it can basically create some inaccuracy in measurement that is of the order of plus minus 1.5 degree centigrade. But we can avoid this inaccuracy if we have before basically installation of this type of sensor, we can give some irradiation or the radiation to the fiber bracketing of the order of 1 megagray, and then we can again recalibrate this type of sensor. Then we can work with higher accuracy. This is the in-house developed fiber bracketing sensor that was installed at S3F BRC Tarapur, and this is in the second figure I have shown the data received at that site. In this data I have shown that one thermocouple data is there and one is the FBG sensor data. Thermocouple, this is the data is for 1 year, and during this 1 year they
Dr.
have
Kumar?
Yes sir.
Can you conclude in a minute or so?
Yes sir, I will try to complete in 5 minutes.
Okay, fine. I think we are running out of time, so maybe
Okay.
2 more minutes. Okay.
Okay,
fine,
okay, sir. I will try to complete. And similarly, some application we have done this in advanced fuel fabrication facility BRC Tarapur. In this facility, we have the challenge. All other challenges were same as the previous challenges. The main challenge was that the temperature monitoring required was around 800 degrees centigrade. As I have already said, that temperature by type 1 FBGs are not more than 600 degrees centigrade. So what we have done, we have written regenerated fiber bracketing, and that fiber bracketing was used in the system for temperature monitoring. And other things were there like HNO3 environment there, the Teflon coating done for this HNO3 environment. For high microwave power, we have encapsulated the fiber bracketing in ceramic tubes, and all these things were done. But regenerated FBG, basically in regenerated FBG, the reflectivity of the FBG decreases due to sudden rise in the temperature. And if the temperature is around 900 degrees centigrade or of the order of 900 to 1000 degrees centigrade, what happens? The reflectivity of the FBG again increases, and that is known as the regeneration. In this figure, I have shown that this one is the seed type 1 FBG, and its reflectivity is around 99.98%. And if we apply a certain thermal annealing schedule in which we can provide some ramp annealing to this FBG, what happens? We have some regeneration of the FBG. And the properties of the regenerated FBG is that the reflectivity is almost, it is although lower than the original FBG, but its temperature sustainability is very high. So this type of sensor were installed at this fuel fabrication BRC Tarapur. And then there was a requirement from Jigru-heated ceramic melter regarding temperature measurement at multi points. So what we have done, we have created the regenerated grating at various points so that this type of sensor can be installed at the at joule melter. Then there was some requirement from this development of wheel impact load detection system for railway safety. For railway safety, we provided the fiber brake grating because they required some highly sensitive sensor, and that can be easily installed on the web of the rail. And this work is being carried out by the Lab to Market. It is a startup of IIC Bengaluru, in which these FBG sensors basically they have mounted on the web of the rail, and what they have monitor as the train passes through this basically track, the wavelength of the FBG changes. Means there is a rise in the wavelength. If for the loaded wagon I have shown, the wavelength shift is higher. For the unloaded wavelength, it is lower. Now I am going to show you a single video in which this a train is passing basically, and as the train is passing through this FBG sensor, the wavelength of the fiber brake grating is changing from this point. So there is a change in the fiber brake grating wavelength, and by monitoring the change in the wavelength, the estimation of the load of the fiber brake of the wagon or the any material, or and if some problem is there, like some wheel is flattened, so that information can be taken out from that. It is the slow motion in which I have shown that as that wheel of the train is passing through this FBG, there is a sudden rise in the brake wavelength. So to summarize, I can say that FBG sensor is an emerging tool for sensing various parameters. RRCAT has developed this indigenous CVL setup, and we are providing fiber brake grating to various institutes, and different type of fiber brake grating like FBG, tilted, chirp, long period, all type of fiber brake grating are being developed at RRCAT and are complementary in the scope of applicability. And there is a huge scope for FBG sensor deployment in capital intensive sectors, national security, and in a variety of industry research installations. And I would like to acknowledge our director and director laser group, Dr. S.V. Nakhe, and Dr. S.K. Dikshit, our head fiber FSOSS, and Dr. Om Prakash, head of our fiber grating laboratory, and my colleagues, Dr. Saxena, Dr. Mahakud, Shri Pankaj, Sudhi, Gaurav, and Umesh Kumkar. Thank you, sir.
Thank you, Dr. Kumar. And indeed, I knew that because this is just before lunch, so I took the liberty of giving some extra time to you and other speakers also. And let's take one or two quick questions. There are several questions in the chat box, so let me read one by one for you. There is one question from Alok Kumar Rai. If you need to measure multi-parameters such as temperature, pressure, strain simultaneously for railway safety
Sir,
external
your
applications.
sound is basically some.
Hello.
Some disturbance is there. I think so. I am not able to hear this sound.
No.
Some audio.
Can you hear me? Oh, okay. Can you read the questions from the chat box?
Just a minute, sir.
Can you do that yourself? Hello.
Just a minute, sir. I will try to read.
Can you hear me now?
Yes, sir. I can hear.
Okay. So if you need to measure temperature, pressure, strain simultaneously, how do you do that?
Sir, there are proper I think methods are there. Some multiple methods are there. We can measure the temperature by one FBG that is not fixed at any point, and we can place some other FBG nearby to the sensor that is fixed at 2 points. By monitoring the wavelength shift for them, and by proper basically equation, 2 equations.
So you mean to say you have to put a separate sensor each parameter? So
yes,
that
sir.
is the answer basically. Is
yes,
that right?
Yes,
okay,
sir.
fine. Thank you. So another question is, can FBG temperature sensors measure metal welding temperature, for example, 1600 degrees C?
Sir,
1600 degrees C, can you measure that?
Sir, actually your voice is breaking, I think.
Can you measure temperature as large as 1600 degrees C?
1600. What did you say?
Yes, correct.
Yes, sir. If the fiber brake grating is written in sapphire fiber, in that case, we can measure the temperature higher than this temperature, this range. But for this for FBG written in the silica fiber, we cannot measure temperature more than this, because ultimately the reported temperature for this FBG sensor is around 1395 degrees centigrade using this FBG written in silica fiber. But for higher temperature, we have to go for the sapphire fiber.
Okay. And there is one more question here. How do you separate the cladding from an optical fiber for fabrication of grating on the core?
How did you
How do you separate the cladding
Okay.
from
No,
an
no, no.
optical
Actually,
fiber?
this cladding need not to be separated from the fiber. Actually, basically, UV light
Yeah.
is falling on the fiber, and this UV light is transparent to the cladding. Cladding material is silica, but the doping is done in the core only. So, and core is germanium and germanium boron core doped is there. So, the light is basically interacting with the core only. So, cladding need not to be removed for writing fiber brick grating. But if we want to use this fiber brick grating for some chemical sensing or refractiveness sensing, then cladding need to be removed.
Okay.
For
there is another question. How do you design or produce and verify the interference pattern of required spacing?
How did you, sir?
How do you design or produce and verify the interference pattern of required spacing?
Yes, sir. We are using basically two methods. One method is this phase mask based method. The phase masks are commercially available. That they are having particular period, and if the light falls on that phase mask period, they create certain +1 and -1 order, and the space interspacing that depends on the phase mask period. And we can get 0.5 micron easily with the phase mask. And some homemade methods are also there. We can design a biprism with certain angle, so that if light falls on the biprism and by the interference pattern that is being created by this biprism, we can create this period of
Okay.
this required.
Okay. So let's thank Dr. Kumar for an excellent talk and giving an overview of wonderful work that is being carried out at RRCAT on fiber break grating sensors and devices. And in fact, I have been ordered by session management that we should stop the session now because the next session has to start after lunch at 1:30. So thank you, Dr. Kumar, once again, and thank you all for joining this session. We had an excellent talk from 3 people,
Thank you,
and I hope everyone enjoyed that. Thank you so much.
Thank you.
If there is any announcement from session management, they
Yes,
can
we
do
will
that.
take over from here. Thank you very much, Dr. Sharma. The next session is, as Dr. Sharma said, it's about oral presentations. These presentations will be run in 2 parallel sessions, and all the presenters, they are requested to please connect to us by 1:20. So I request all of them to please be there on time, because these sessions are also going to be very time packed. Another announcement that I have to make is I request all the participants to please visit the exhibitors gallery on NLS-30 website, where you can get a broad view of variety of products that will strengthen your laboratory. So please do that, and please assemble back here at 1:30. Thank you very much.
Hello.
Thank you.
On behalf of organizing committee, we thank session chairs for maintaining the timings. Thank you all. We'll close.
Thank you.
अच्छा हाँ बोल के बता दो क्लियर Murthy sir, are you able to hear us? Yes, Murthy Babu sir, are you there? Oh, muted. Hello. Murthy sir, are you able to hear us?
Hello.
Yeah, yeah. Yes, sir. Hello.
Hello. Sunil Verma ji. Hello.
Hello. Hello.
Hello. Murthy sir. Hello. This is session management from the main auditorium. Hello. Check. Murthy sir, are you there?
Hello. 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 I am Murthy Babu here. How are you, Dr. Sunil?
Yeah, sir. I am from the session
Fine, but
management.
now
Mr.
the session we have to coordinate, post the session.
Yeah, yeah. So Mr. Sunil Verma has not joined yet, and he's going to take some time. And the same with Mr. Kamath also.
Okay.
He will join at 1:40. So what do we do? Do we wait for them or we start the session? So all participants will be unmuted at the time of presentation, and we will be sharing the slides from our side here. We are waiting for the judges to join, so we'll start in a few minutes from now. Murthy sir, are you there? S. Murthy Babu sir, are you there?
Hello.
Yes, sir.
Yeah, this is Dr. Sunil Verma. I have
Yeah.
joined.
Okay, yeah.
I am MP Kamath. I have also joined.
Okay.
Hello.
Hello. Yeah, Dr. Murthy Babu there?
Hello.
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 Yeah, I can hear.
Hello. Murthy Babu, can you?
Hello.
Hello.
Okay, sir. So welcome you all. So we start the poster session now in auditorium A. So we request all presenters to be online. If somebody is not connected, we will go to next presenter and your turn will come in the end. You have 3 minutes to present. After 2 minutes, first bell will ring. After 3 minutes, last bell will ring. Please wind up the presentation quickly as the judges will take over. So I request presenters of poster number CP0301, presenting Mr. Monica M. to start now. So Monisha M, please start.
Sir, am I audible?
Yeah, you are audible.
So very good afternoon to all. I am Monisha M, research scholar from Manipal Institute of Technology. So today I'm going to give my presentation on the topic bright red emissions from EU3+ doped zinc aluminum borosilicate glasses for solid state lasing application. So you can go to the next slides. So coming to the introduction, so we know that radar doped glasses, so they are the most popular solid state laser gain medias due to their electronic transition that usually occur in within the 4F shell. And among the rare earth ions, the EU3+ ions have bright red emissions and they have tunable emission wavelengths with longer lifetime. And also the europium ions have strong lines in the orange to red spectra region due to their 4F electronic transitions. So these europium ions are mainly considered for luminescence display as well as red LED application. So the experimental method for the preparation of the glasses is given here. So this is the glass matrix that was designed for the preparation of EU doped glasses. So here europium oxide is varied in different molar percentage, starting from 0.1 to 2.5 mole percentage. So initially the raw materials were taken in an agate mortar. They are grinded well, and they're transferred to alumina crucible, and the raw materials inside the crucible are kept inside an electric furnace and they are melted at 1320 degrees Celsius for 3 hours, and the melt is quenched on a preheated brass plate, and the obtained glasses are annealed at 2 hours at this temperature, that is 350 degrees Celsius, and we obtain the transparent glass ceramics as shown here. So next slide. So the result and discussion. So I'm going to discuss the UV visible NIR studies startingly. So here the absorption peaks of the europium doped glasses have different absorption in both ultraviolet visible and NIR region, and the main intense absorption is observed in the NIR region, and the transition corresponding to the absorptions are given here. So coming to the photoluminescence study, so the excitation spectrum was recorded with an emission wavelength of 630 nanometer, and we see that there are 7 excitation peaks that is observed in the spectrum, and these excitation have their transitions that is happening from 7F0 ground state to different excited state. So next slide. So the photoluminescence study. So next we are seeing the emission spectrum. So this emission spectrum was recorded with an excitation wavelength of 3 nanometer, and we have nearly 5 emission peaks. So in which the intense emission peaks is observed at 612 nanometer. So from the emission spectrum, we are calculating the radiative parameters, which includes the radiative transition probability, the branching ratio, the stimulated emission cross-section, and effective bandwidth. So from the different doped glasses, we see that 0.2 mole percent highest emission compared to other glasses.
Your time is over. So over to judges.
I'm Kamath calling. I want to understand how do you say that it is for solid state lasing applications with all this data?
Sir, actually, we calculate the parameter called stimulated emission cross-section using the emission data that we observed. So we know that these glasses are mainly have the, I mean, the radar doped glasses, they have light amplification achieved by the stimulated emission of this excited rare earth ions that happening within the glass. So from the higher emission wavelength, we confirm that the glasses have their lasing property.
But europium is not a very good lasing material as such up till date. And to get a inversion, you may have to dope further with some ytterbium or neodymium. Is it that way?
Yes, sir, for when looking for some upconversion or other application, there are co-doped glasses with europium, but on single-doped glasses, this properties what that I have achieved is comparably better. So,
But why there are no much lasers on this?
and maybe this laser mainly they have their emission in their visible region, so they don't have a prominent emission in NIR region. So maybe that could be the reason, like the studies are very less on this rare earth.
No, but you can have lasers even in the visible.
Yes, sir.
What is the maximum size of the sample which you could prepare in this?
Maximum size in the sense, sir, like
the size of your crystal, that glass.
a
Size
glass.
of the glass.
So the glass, it is actually the shape that we obtain is spherical or like the form, the way we quench the melt. So the glass size can vary from like some 2 mm to 5 mm. That depends upon the way of preparation.
Any new result in this?
New results means so still we are working on the EU doped glasses for the CODOP studies also. So at present we see that the glasses show their bright reddish emission, and also their emission cross-section values are higher, that is 14.920 obtained for this 2 mole percentage glass.
What is the lifetime of these excited states?
The lifetime will be around 1.95 milliseconds, sir. That is not actually included in the slide, but the lifetime of the rare earth is that order.
Okay, thank you.
Thank you very much.
So our next presenter will be Mr. Jivraj, and his poster number is CP0303. Please continue, Mr. Jivraj. Are you there? Hello, please start, Mr. Jivraj. Hello, are you there? So we will go to next presenter. Maybe he is not there. So our next presenter is Mr. Sushil Kumar Pathak, and his poster number is CP0304. So Mr. Sushil, please start. Hello, Mr. Sushil, are you there? Okay. Mr. Sushil is not there, so we'll go to the next presenter. So Mr. Santanu Kaushik. So Mr. Kaushik, please start your presentation.
You please tell the poster number also.
So poster number is CP0305. Mr. Shantanu Kaushik. Mr. Santanu.
No, Shantanu, you have to unmute yourself.
Hello.
Yeah, we can hear you now.
Okay. Should I start now?
Yeah, please.
Yeah, please start.
Okay, okay. Actually, can you please enlarge my this PPT?
Shantanu, hello. Shantanu, you
Yes,
have to
yes.
do it at your end. So you have to drag the screen to make it bigger.
Okay, okay. Thank you. Good afternoon, everyone. In this work, we have demonstrated magnesium zinc oxide based metal semiconductor metal solar blend UV photodetector grown by pulse laser deposition. The objective of our work is to fabricate solar blend photodetector based on magnesium zinc oxide. The solar blend photodetectors have attracted very much attention in last few decades because of its various civil and military applications like space-to-space communications, missile fuel sensing, and so on. However, there are many challenges with these traditional UV detectors, like they are bulky and heavy, and they usually requires high voltage for operation, and also they requires high cost optical filters. And so as an alternative, wide bandgap semiconductor materials are supposed to be an effective alternative to replace these traditional UV photodetectors, and among them, magnesium zinc oxide is considered one of the ideal UV sensing material because of its various advantages, properties like wide bandgap tunability from 3.3 electron volt to 7.8 electron volt, radiation hardness, and etc. And till now, various groups have developed UV photodetectors with different device structures. In this work, we have mainly focusing on MSM geometry because of its simple fabrications. Next slide, please. Next slide, please. Yes. Here you can see the schematic of our PLD deposition system, where we have optimized a growth condition to deposit magnesium zinc oxide thin films on sapphire substrate. And then we have prepared the MSM photodetector by making this platinum interdigitate electron by RF sputtering. The XRD spectra shows this magnesium zinc oxide films, so the mixed phase characteristics, which having both this Upadhyay and cubic phase existed, and the transmission spectra shows a sharp single transmission edge with a band gap of around 4.4 electron volt. Next slide, please. Here you can see your device MSM spectra, MSM schematic, and the linear IV characteristics here confirms that platinum makes ohmic contact with a magnesium zinc oxide layer. The direct current is found to be around 8 nanoampere at 2 volt, and under UV illuminations, the photocurrent increases up to 20 nanoampere. And from this responsivity spectra, you can see there is a single cutoff wavelength of around 280 nanometer. And this means that this device can be used in the solar blend region with a peak responsivity, which is found at around 267 nanometer, with a responsivity of around 0.9 milliampere per watt. And most interesting, the UV to visible rejection ratio is of 3 orders of magnitude. And here you can also see the
Your time is over now. Please wind up fast.
Okay, the peak responsivity also increases as we increase the bias voltages, which signifies that the device operates in a photoconductive mode. So in conclusions, we have successfully fabricated MSM solar blend photodetector based on mixed phase magnesium zinc oxide thin films. So we believe that these results present a significant step towards achieving practical solar blend UV photodetectors based on magnesium based materials. Thank you.
Judges, please ask the questions.
Why you have used PLD? Any other technique you could have used?
Yes, sir, we have also used RF sputtering, but there we have we could not tune so effectively this band gap actually. So that's why we have chosen this PLD technique.
Okay. And these precursor materials, what were the precursors used?
Yes, sir, this is PLD, so a ceramic material target was used.
Okay, fine. And these type of solar blinds are not earlier reported. And what is the basically takeaway? Unique.
So yes, sir, basic takeaway is this: this is a mixed phase sample. So ideally, in mixed phase samples, you will get two band responsivity spectra, but here we get only the single responsivity spectra with a single cutoff. or that is also below the 280 nanometer. So in that sense, this is very unique in a sense, and only one report that proposed this single band photoresponse spectra.
There is only one report you mentioned.
Yes.
Which is from which group?
Chinese groups are data.
Okay, fine. What is the UV source you have used?
Sorry, sir.
You have used some UV source.
Yes,
So
sir,
what is that UV source?
Xenon lamp, sir.
Xenon lamp. So you use some sort of filter in front of xenon lamp?
Some monochromator.
Monochromator. Fine. Okay, fine. Thank you.
When you have two phases, how do you get that one response?
Yes, sir. That is interesting, basically. So maybe the two phases, that is the Ujjayi and cubic phases, they may be in the although they are in a different phase, but their bandgap may be same. So that may be the one of the reason that people have proposed, and also maybe the contributions from the cubic side, as you can see from the XRD spectra, the contributions from the cubic phase may be negligible. That is maybe one of the may also be the one of the reason.
Nobody has confirmed it?
Yes, that group already confirmed this.
It is confirmed. How do you confirm that?
Basically, you can see that from the transmission edge, there is only single absorption edge.
Yeah, that is there. But
Yes,
why
yes,
we
yes.
are not seeing the other one? That because that is a
Yes, actually, sir, that is actually depends on the growth condition, basically. The way we tune the growth mechanism, that actually dictates this single absorption edge or double absorption edge. So basically, this is because of the growth condition.
Okay.
Mr. Shantanu,
Yes, sir. Yes, sir.
you have grown on sapphire substrate.
Yes, sir. Sapphire substrate.
What is the lattice mismatch between this film and the substrate?
So it is around 18%. But if you talk about from domain lattice mismatch, that is below 1%.
Okay.
Yes, sir.
Next presenter will be Miss Pooja Sharma, CP0302.
Sir, am I audible?
You are audible. Please start.
Okay. So the topic of my today's presentation is, sorry, sir, I'm not seeing my presenting. Okay. So the topic of my today's presentation is proposal for ultra compact air drop filter, which is based on ring resonator created in holes in slab, 2D hexagonal photonic crystals. Photonic crystals are artificially created structures having periodic variations of refractive indices in different directions, and propagation of light through photonic crystal, it is restricted in certain directions for a specified range of frequencies, which is called as photonic band gap. So here I use the 29 rods in the x direction and 21 rods in the z directions, and I have created a hexagonal cavity between the two waveguides, that is bus and the drop waveguide. Lattice constant that I have chosen is 296 nanometer and refractive index, which is 3.9, and the radius of the rod, which is 0.29 into a, and this is the diagram for the band structure of the proposed structure. Sir, next slide. Please, next slide. This figure illustrates that when I injected a pulse which is centered at 1550 nanometer, then at resonance wavelength, which is around 1554.77 nanometer, and all the lights will appear at port C, which is called as a forward dropping port, and no light will be appeared at backward drop port and the transmission port. This figure represent a figure 3. It represent the normalized transmission at the different port of the proposed ADRA filter, and the third one figure represent the off resonance wavelength. At off resonance wavelength, which is around 1545 nanometer, all the light will appear at the port B, and the band gap, which is considered here, it lies in the TA mode, and of the wavelength, which is ranging from 1228 nanometer to 670 nanometer. And I have used I simulated this structure using the plane wave expansion method, or simulation will be done using the 2D FDTD method, and the two waveguides, two defect waveguides is created. That is the bus and the drop waveguides. So next slide, please. The results are that when we varied the lattice constant or the refractive index, and their performance is studied over the Adroff filter, and we found that when we varied the value of lattice constant, the different resonant peaks observed, and same for the different refractive indices. So we can use such type of devices for different multiplexer, demultiplexers, and for sensing. And the conclusion is that the 2D photonic crystal based devices, all optical filters, they are of high
Time is
research
over.
interest due to their features like compactness, high efficiency, and high quality factor. And the proposed structure is very compact, which is around 53 micrometer square, and the resonance is 1547 nanometer. 1554.77 nanometer with the high quality factor of 675.98. That's all. Thank you.
Over to you, judges.
Is it only a design or is it fabricated?
Sir, it is only a design.
Okay. So you have studied a design for some certain
Yes, sir.
application, for certain application, or it is
Yes,
a
sir.
general study? You want
No,
to
sir.
multiplex certain number of signals, or you want to use it with certain other communication devices or something like that?
Sir, this is a general study of a ring resonator, and we can use such type of devices for different multiplexer, demultiplexers, and for different types of sensors, and in photonic integrated circuits, and different types of logic gated. So we can use such type of devices for that purpose.
So is it a optimized design? What you
Yes,
have
sir.
done? Optimized for
Yes, sir.
losses or for speed or for what?
Sir, we have optimized this device for in terms of size. I have reported some of the proposals that their size is very large. So today's communication technology, it requires a very compact size, compact design size. So this is the novelty of my structure, and also our structure produces the high quality factor, which is around the 675.98 nanometer. Sorry, 675.98. It is a unitless quantity.
So how are the available commercial devices? What are the quality factors for that?
Sir, there are different type of devices are available, and their quality factors. Last I have reported some of the papers in which their quality factor, which is around 432, and in some of the papers which is around 2000, but their size is very enlarged, which is around 400, more than 400 micrometer square. But in contrast, our structure is very compact, and their quality factor is very high in terms of that.
How did you achieve that with the smaller size? How did you achieve a lower loss in the ring resonators?
Sir, I have done using the different values of the refractive index. I have calculated this value for different values. I have calculated this value for 3.46, 3.46 refractive index, of which is around 3.46. Then I found that the size of the device is very large. So that I changes the refractive index, and I have found at 3.9, at the refractive index of 3.9, the size of the structure is very compact, which is around 53 only.
But is there any material with 3.9?
Yes, sir. Germanium is the material. I read some of the papers in which the refractive index of germanium is, or experimentally calculated value of the germanium is 3.9.
Okay.
Refractive index of germanium is 3.9.
Okay.
What is it that you would need to realize this in experimental this thing. So this is a simulation study, right? So if you have to do some experiment or somebody has to perform some experiment, so what you will do?
Sir, they need to perform the different lithography techniques that today's attended the today's session in which Professor Shukla ma'am already discussed some of the different lithography techniques. So they will use the lithography technique to produce such type of devices, or of laser lithographic techniques, or interference based lithography techniques, electron beam lithography techniques, etc.
And what is the material required? What material you will choose?
Sir, in this simulation, I choose the germanium. The refractive index of that is 3.9.
Okay. Fine. Thank you.
Next present is Sushil Kumar Pathak, CP 0304.
Thank you, sir.
Yes, this is to request you to.
Hello.
Hello. This is from.
हाँ नमस्ते, मैं एस के पाठक, मेरी आवाज सुनाई पड़ रही?
Yeah, this is from the session management. To the judges, please kindly maintain the time because we have a next session in this, and so we have to really finish all these poster presenters on time. Thank you.
Right.
हेलो
पाठक जी शुरू करिए।
हाँ जी, अच्छा, ये मेरे जो वर्क का टाइटल है माइक्रो स्ट्रक्चरल एंड ऑप्टिकल कैरेक्टराइजेशन ऑफ क्रोमियम डोप्ड एल्यूमिना सिरेमिक। तो इस काम में हम लोगों ने सिरेमिक सिंथेसिस रूट से एल्यूमिना बनाया है, उसमें क्रोमियम की डोपिंग की है। ठीक है, ये एक लेज़र होस्ट मटेरियल है और सिरेमिक रूट से बनाने का एडवांटेज ये है कि हम इसको किसी भी शेप में बना सकते हैं, कम टेम्परेचर पे बना सकते हैं और बड़े साइज में बना सकते हैं और डोपिंग कंसंट्रेशन जो है कम ज़्यादा कर सकते हैं। ये सब एडवांटेज हैं इसके। लेकिन उसके बावजूद भी थोड़ा सा इसको बनाना इसलिए डिफ़िकल्ट है कि ये जो पाउडर बनता है सिंथेसिस के समय ये नैनो साइज़ में होता है और इसके कारण से इसमें एग्लोमेरेशन बहुत ज़्यादा होता है। तो एग्लोमेरेशन के कारण क्या है कि जो फाइनली हमको पार्टिकल साइज़ चाहिए वो अचीव करना थोड़ा डिफ़िकल्ट हो जाता है। तो और सिंटरिंग में क्या है कि फिर अगेन वो साइज़ और बढ़ जाता है। ठीक है, तो उससे क्या है कि ऑप्टिकल स्कैटरिंग वगैरह इस तरह की समस्याएं शुरू हो जाती हैं। तो इसमें जो हम लोग का मेन टारगेट था कि जो रेजिडुअल पोरोसिटी है हमारे मटेरियल में उसको हम कैसे कितना कम कर सकते हैं। तो ये मतलब इस फोकस से हम लोगों ने इस काम को किया और इसमें नाइट्रेट सॉल्यूशन लेते हैं और साथ में इसको प्रेसिपिटेंट के लिए अमोनियम हाइड्रोक्साइड सॉल्यूशन यूज़ करते हैं और फिर पहले मतलब प्रेसिपिटेट फॉर्म में जब उसको प्रेसिपिटेट करा लेते हैं देन उसको फिल्टर करके ड्राई करके और फिर उसको कैल्साइन करते हैं करीब 1200 डिग्री सेल्सियस पे। उसके बाद XRD से देख लेते हैं कि भाई रिक्वायर्ड फेज बन गया कि नहीं बन गया। देन उसको शेप करके और फिर सिंटरिंग करते हैं। तो सिंटरिंग करीब 1780 डिग्रीज तक पे ले जाते हैं एक सर्टेन प्रोफाइल देके। तो जो हम लोग का रिजल्ट जो हम लोगों ने एक्सरे पे देखा और उस पे डायलेक्ट्रोमीटर पे, तो उसमें ये देखा कि जो सिंटरिंग है वो जनरली 1200 के बाद जो कंपैक्शन है वो स्टार्ट होता है तेजी से और फिर 1550 के बाद डिग्री सेल्सियस के बाद काफ़ी और मतलब तेजी से हो जाता है। तो इस तरह से हम लोगों ने करीब करीब 97% तक करीब उसमें डेंसिटी थ्योरेटिकल डेंसिटी के कंपैरिजन में अचीव कर लिया। उसके बाद फिर उसको जैसे एक बार पार्टिकल जब वो मतलब पार्टिकल फॉर्म में था तब उसका XRD किया था और देन एक बार जो सिंटर्ड।
प्लीज वाइंड अप, टाइम इज ओवर। जजेस प्लीज आस्क द क्वेश्चंस।
पाठक जी आपने जैसे ये बताया मटेरियल बना लिया,
जी
किस एप्लीकेशन के लिए बनाया वो आपने बताया नहीं।
एक्चुअली ये लेजर होस्ट मटेरियल है।
हाँ, तो उसकी कुछ आपने टेस्टिंग की बनाने के बाद इस सैंपल को?
नहीं अभी, हाँ मतलब जैसे इसका एक वो किया था एटेन्यूएशन कोफिशिएंट ऑप्टिकल ट्रांसमिशन लेके देखा था कि कितना हो रहा है। तो उसमें हम लोगों को करीब करीब 28% के आसपास इसमें ट्रांसमिशन मिला था।
ओके
और जो कैरेक्टरिस्टिक एब्जॉर्प्शन है वो मतलब उसमें दिख रहा था।
ओके। और पार्टिकल साइज कैसे मेंटेन करते हैं, क्योंकि आपने बताया कि वो उसमें एक ये प्रॉब्लम है सिंथेसिस रूट में कि पार्टिकल साइज मेंटेन नहीं हो पाता एग्लोमरेशन की वजह से।
हाँ,
सो हाउ डू
उसके लिए
यू मेंटेन? उसके लिए कुछ इन्वेस्टिगेशन किए थे, कुछ ऑप्टिमाइजेशन किया था?
हाँ, उसके लिए हम लोग क्या करते हैं कि थोड़ी मात्रा में मैग्नीशियम ऑक्साइड और थोड़ा अमोनियम सल्फेट ये ऐड करते हैं। तो ये डिफरेंट डिफरेंट कंसंट्रेशन, जैसे कई बैच बनाए तो सब में किसी में कम, उससे थोड़ा ज़्यादा, उससे थोड़ा ज़्यादा, ऐसे करके थोड़ा थोड़ा क्वांटिटी बढ़ा के ये देखा कि भी किस में हमको मतलब पार्टिकल साइज कम से कम मिल रहा है।
तो ये जो दो आपने बताए मैग्नीशियम ऑक्साइड और ये आपके उस पेरेंट फेज में नहीं चले जाते हैं?
ये जब कैल्साइन करते हैं तो फिर ये वो हो जाता है, निकल जाता है, उससे बाहर आता है, क्योंकि XRD में हमें इसका वो
जो
नहीं
कोई
मिलता
ऐसा
है,
उसका सिग्नेचर
सिग्नेचर
नहीं मिला है।
हाँ, XRD में सिग्नेचर नहीं मिलता है।
ओके, थैंक यू, थैंक यू।
थैंक यू।
Next presenter will Miss Rachna.
Hello, am I audible?
0306. Yeah, you are audible. Please start.
Good afternoon, everybody. Today I will be presenting our work on small angle neutron scattering study of transparent laser host Nd:YAG ceramic. For this work, the samples of Nd:YAG ceramic were synthesized at RRCAT, and we have done the small angle neutron scattering studies at BRC. As it's well known that Nd:YAG is a well-known solid-state laser host material, but generally it is used in a single crystal form. But to the single crystals of Nd:YAG, high concentration of anti-doping is difficult, and it's difficult to make the large size Nd:YAG crystals. Whereas the Nd:YAG in a ceramic form can be easily prepared for the high concentration and the large sizes. But preparing, as per in the previous presentation, Dr. Pathakji has already informed that preparing transparent ceramic is actually a difficult task. It involves a lot of synthesis techniques to be evolved. The transparent ceramics actually face the optical quality of the ceramic is basically hindered due to the presence of the scattering centers. Those are basically grain boundaries, residual porosity, secondary phases, bifringes, and the surface flaws. Surface flaws and the grain boundaries scattering losses can be avoided if we polish the ceramic properly, and if the density is more than 99%. Whereas the secondary phases can also be avoided by using the high advanced synthesis techniques. And for the cubic, if the ceramic material is a cubic, as YAG is a cubic material, so bifringes losses in such cubic materials are almost zero. Whereas the residual porosity remains a major factor that plays the important role for the optical quality of the ceramics. Therefore, we in this study, we investigate the pore morphology of the 1 atomic percent ND-doped YAG transparent ceramic synthesized by co-precipitation method using the SANS technique. Next slide, please. Here in the figure 1, you can see the prepared ceramics are translucent, nearly transparent in nature. These have 75% transmission at the 1000 nanometer wavelength. That is equivalent to the 90% of the theoretical transmittance. The second figure shows the SEM picture of the prepared ceramic. It is a optically polished SEM picture. Here you can see, here we can see nearly nanopores of the order of the 200 nanometers.
Please wind up. Your time is over.
Next slide, please.
Please wind up.
Yeah. The scattered intensity of the Nd:YAG ceramic in the first figure, you can see the scattered intensity over the fuel Q range. Here we fitted this scattered intensity with using the model of spherical pores with the log normal distribution. And the second figure shows the obtained particle size distribution. From here you can see the there are pores of the order of 10 to 400 nanometer, and the maximum pores have the radius of 80 nanometers, and the mean size of the pores is 150
Please ask the
nanometers.
questions.
Yeah, thank you. It's over.
हट जाओ, वीडियो ऑन कर दिया मैंने. Rachna,
Answer.
nice to see you back.
Thank you, sir.
Yeah. एक क्वेश्चन है, ये जो pore density and all you used to measure here also, है ना, in some way.
हाँ सर, DLS और इससे निकालते हैं ना सर,
Right.
BTS से.
So how does this compare with what you have done with small angle neutron diffraction studies?
सर DLS वाले से भी हमने किया था, लेकिन DLS में कैसे करना है ना, वो उसको सिरामिक को एज इट इज नहीं यूज कर सकते. उसको पाउडर बना के फिर उसका अब्जॉर्प्शन स्टडी करते हैं, और DLS में भी नैनो पाउडर ही यूज करते हैं. बट अल्टीमेट जिस यूज फॉर्म में हमको याग को यूज करना है, Nd:YAG को, वो तो सिरामिक की फॉर्म में है ना, तो
तो ये
उसमें उसका
स्टडीज जो तुमने की हैं, ये these are on those transparent samples.
हाँ सर, एज इट इज जो अपना Nd:YAG सिरामिक है, उसको इन ट्रांसमिशन मोड वी हैव मेजर्ड द स्कैटरिंग.
Okay.
तो
So this is a sort of non-destructive testing in that
हाँ,
sense.
it's a non-destructive technique, sir.
Okay. And what is exactly the principle? How does it function?
सर इट्स ऑलमोस्ट सिमिलर टू बेसिकली एक्सरे. जैसे एक्सरे में इलेक्ट्रॉन डेंसिटी की वजह से एक्सरे स्कैटर करती हैं, इसमें बिकॉज ऑफ जैसे अभी अपना सिरेमिक है और उसमें कुछ सॉलिड मटेरियल है, फिर पोर है, पोर तो इट्स लाइक एम्प्टी नो. तो इसकी वजह से जो कंट्रास्ट इन स्कैटरिंग डेंसिटी होगा, उसकी वजह से जो न्यूट्रॉन स्कैटर होंगे, सो वो जो स्कैटर्ड न्यूट्रॉन है उसका इंटेंसिटी इन द फर्स्ट ग्राफ वी हैव प्लॉटेड दैट स्कैटर्ड न्यूट्रॉन का इंटेंसिटी विद रिस्पेक्ट टू क्यू. तो उस अब जो डेटा आया उसको एक मॉडल लेके फिट करते हैं, उस फिटिंग से जो सेकंड ग्राफ है NR वर्सेस R प्लॉट करते हैं, उससे डिस्ट्रीब्यूशन निकलती है कि क्या पोर साइज है, क्या पोर उसका वॉल्यूम है.
What is the percentage error in this pore size
सर
calculation?
नियरली 10%. सर नियरली जो
10%.
फर्स्ट ग्राफ है ना, here we get the percentage error. From here you can calculate ultimately nearly 10% is a percentage error.
और जो पुराना DLS के एक्सपेरिमेंट्स करते थे, उसमें से जो निकलता था, उसमें क्या एरर परसेंटेज रफली?
DLS वाला तो मतलब वो डिस्ट्रक्टिव है.
Destructive है.
सर वो कैन नॉट से अब एक्टिव है ना, यो तो आपने सिरामिक को पहले क्रश किया, पाउडर बनाया,
नहीं, ठीक
ट्यूब
है,
में
वो तो
डाला,
सैंपल ही खत्म हो गया.
हाँ सैंपल ही खत्म हो गया, तो उसमें मतलब
ठीक ठीक.
मल्टी प्रोसीमीटर से भी सर किया था यहाँ पे हमने पाशी में, जो अपना BRC का सेंटर है, लेकिन उसमें कुछ निकला नहीं. Cause they said like इधर से जो दिख रहा है सर, जो पोर साइज है एक्चुअली इज नियरली 800 नैनोमीटर तक है. डाया जो 800 नैनोमीटर तक का डाया है, इट्स वेरी स्मॉल फॉर द मल्टी प्रोसीमीटर टू फाइंड आउट.
ओके, ठीक है
मैडम.
Next presenter, Mr. Sanjeev Kumar, CP0308. Sanjeev Kumar, are you there?
Yes, I am here.
Please start.
Hello everybody. I am going to present the results of index mesh filtering technique, which is set up for fast detection of refractive index homogeneity in anti-doped phosphate glass slabs. Large aperture anti-phosphate glass slabs are key optical element of a high power laser system, which is being developed at RRCAT, and these glass slabs are being developed at CGCRI Kolkata. Optical homogeneity of laser glass dictates the performance of the laser. It controls the quality of the wavefront and ensures damage-free high peak power laser operation. Therefore, laser glass must be highly homogeneous and free of stress, stray bubbles and inclusions. Fast qualitative measurement of optical inhomogeneity of the laser glass is of crucial importance. It is required for feedback during development to optimize the melting and casting process, during which imperfections take place. Serene and interferometry are the known methods for detection of inhomogeneity, out of which serene imaging is preferred if the inhomogeneities are significant and the glass is under development. When light passes through imperfections, it gets deflected and scattered, resulting intensity changes in the transmitted light beam. Serene image of the transmitted beam gives a measure of the inhomogeneity present in the empty glass slab. Next slide, please. Serene setup consists of two plane mirrors for folding the light beam, two concave mirrors for collimating and focusing the beam. And it is a light source. Aperture is kept at first focus, and that a knife edge is placed at second focus to unblock the beam, and the transmitted beam is imaged using a camera. And test glass slabs are kept at the path of collimating light beam. For these measurements, we require polished glass slab. Next slide, please. Figure A shows the serene image of transmitted beam when the slab is polished, and it shows the complete map of local refractive index inhomogeneity variation over the whole volume of large anti-phosphate glass slab. Here we can see that this dimension is 300 mm and this is 180 mm. That can be obtained. This image can be obtained by capturing single serene image, and we can see that it reduced the complexity of scanning and stitching technique, which we reported earlier during NLS-29.
Judges, please ask the question.
Optical
Sanjeev Kumar.
Yes, sir.
Yeah, very good piece of work. And why you have chosen 300 mm dia? Is there any significance for the 300 mm dia?
It is required for it is size of empty glass slab that is required for the laser development of that is of high power.
Okay, okay. What will be the minimum size and the maximum size of dia you can go with your experiment?
That is 300 mm. The beam size.
Maximum.
Our beam size.
Also, you use ND-doped phosphate, you know, glass.
Yeah.
What are the other samples which you have evaluated?
Other samples we can test using our setup, but at present any sample we can test for homogeneity using our setup. Now I come to that what we did new in our experiments.
Okay. Okay. Thank you.
Just hello.
Next presenter, Mr. Karthik, CP0309.
Hello. Can you hear me?
Please go ahead.
Yeah, so good afternoon, everyone. I'm Karthik and I'm studying in the Indian Institute of Space Science and Technology. And today I'll be presenting a very simple study, which is done on frequency modulation using acousto-optic modulators, which is particularly relevant for laser cooling experiments. So next slide. So acousto-optic modulators are devices which can modulate the frequency and intensity of the laser light which is passed through them. They're quite ubiquitous in laser cooling experiments where the precise control of detuning of the laser light, which is used to address particular atomic transitions, as well as modulating the intensity of the laser light, is very crucial to the whole laser cooling process. Now, the fact is that the output intensity of an AOM placed in a conventional double pass configuration where a frequency shift of 2 times f, where f is the RF modulation frequency supplied, this output intensity depends on the supplied frequency which is given. And such variation poses a practical problem in laser cooling steps where a change in detuning needs to be implemented. So here I present a simple study to explore the theoretical and experimental factors which play a crucial role in affecting this system efficiency. Next slide, please. So theoretically, the modulation can be understood as a photon-phonon scattering process. The incident light wave diffracts off a grating which is formed by an acoustic wave traveling in the AOM crystal, and this is produced by a piezoelectric transducer controlled by a RF driver. Now, the crucial point to understand here is that the Bragg matching criteria, which is basically the conservation of momentum and energy, which is given by these two relations, for a particular orientation of the AOM crystal, this Bragg matching occurs only for one particular value of the modulation frequency. And the thing which to understand here is that the diffracted efficiency drops if there's any deviation from this particular value as given by this delta F. So ID is sort of inversely related to delta F. So what we can understand from this is that the precise control over the orientation of the AOM crystal is extremely critical in this regard. Next slide. So experimentally, the key factors which we have identified which affects the performance are, most importantly, the beam waist size as it enters the AOM and how it compares to the active aperture of the AOM as given by its data sheet. These needs to be comparable for proper diffraction to occur. And we have controlled this by placing lenses in front of the AOM, and this can be done using a telescopic setup or even a single lens where the AOM is placed at the focus of the crystal. And additional steering mirrors in front of the AOM in order to precisely fine-tune the incident angle is also very helpful. So finally, if we steer using the steering mirrors as well as the final mirror, sequentially controlling these helps achieve the best possible efficiency for any value of f. Further, the position of this final lens is also found to be critical in impacting the system performance. So by altering the beam size to an appropriate value and maximizing intensity at the center value of any frequency tuning range, both higher efficiencies and much more uniform spread across the range was observed as compared to
your time is over now.
Sorry?
Your time is over.
Yeah, I'm done as well. That's
Yeah, Mr. Karthik.
Yeah.
This is nothing to do with your subject, but this is NLS-30, not NLS-29.
Yes, I'm sorry for that.
He has used last year's slide.
Yeah.
I had downloaded the wrong template and really sorry for that.
Hope the presentation is this year's, na?
Yeah. Okay.
Which crystal have you used for acousto-optic modulation? Which one? Which is the crystal?
Sorry?
You have used some crystal in this?
Yeah.
What
Lithium
is that?
niobate crystal.
Lithium niobate. You obtained it from somewhere? Is it a commercially acquired?
Yeah, commercially obtained one.
What was the size?
It's around 5 mm.
5 mm?
You
beam
mean
size?
the active aperture or the whole size of the crystal?
Whole size of the crystal.
It will be around a few centimeters, 3 to 4.
3 to 4?
Along with the piezoelectric transducer as well.
Okay.
The aperture is around 1 mm.
What is the beam size?
The incident beam size we initially had around 5 mm, and we just wanted to observe the effect of how it reduces. So we reduced it to size comparable to the active aperture, and you could see a marked improvement.
Okay, fine. Okay, thank you.
Thank you.
Yeah, we can go to the next.
Yeah, okay, sir. Next presenter, Mr. Sanjeev.
Yes, sir.
CP0310. Please start.
Good afternoon. Effect of NLL on the optical properties of transparent NDX ceramics. We know that transparent NDX ceramics is a laser host material which can be synthesized by different route. but conventional solid state route and co-precipitation source has advantage over the crystal growth. That is, it relatively short processing cycle. It does not have expensive Arabian crucible, and high ND doping is possible. And first laser generation in India was done in 1995. Our motivation is when we prepare NDR by vacuum sintering, so it gives develop some color centers due to oxygen vacancies, which may affect the optical properties. The purpose of this study is to roll up this air annealing on these color centers. Next slide, please. Next slide, please. Optical investor, this is the transmission spectra of NDR ceramic, which was vacuum sintered, and the second one is vacuum sintered at and post annealing at 1250 degrees centigrade, and the last one is air annealing at 1450 degrees centigrade, and we have seen that the transmission is equal 37 to 45%, and this is due to the absorption become stronger. If we see the absorption which becomes stronger around 250 nanometer, which indicates the removal of oxygen vacancies and also the color centers. And this is the attenuation coefficient data, in which the high background coefficient value suggests the presence of micron size isolated pores, which we have to remove to get the higher transparency. And next slide, please. And this is the densification study, which was carried out using a dilatometer, and we see that around 1300 to 1450 degrees centigrade, there is a rapid densification, and we have achieved around 95% density, and then the densification becomes slow, and around 780 degrees centigrade, densification again slow, and while dwelling at 780 degrees centigrade, we got mainly coarsening. So this shows the importance of keeping the sample at 1450 degrees centigrade to get the good quality transparent ceramic. And this is the visualization of scattering study, in which the helium neon laser passed through the NDX sample, and the laser energy is detected here by energy meter, and simultaneously we also capture the picture on the PC, okay? And it shows that the transmission get dropped down around 20% when we shift the detector, and this due to the scattering of isolated pore. And we can conclude that the area annealing produce strong absorption due to the unintensified purity or color centers, which can be removed by annealing. And visualization of light scattering center has revealed the presence of light scattering center, which are residual pores. Thank you. Thank you, sir.
Sanjay?
Yes, sir.
Yeah, Dr. Moti, please carry on.
Yeah, please. Okay. Sanjay, is there any correlation between nature of pores
and
scattering centers?
Yes. If the pores becomes larger and larger, it reflects very strongly around. There is a R to the power 6 at the down. So if pores is increased, so scattering increase strongly.
Okay.
So our aim is to use some sintering. We use sintering aids to get the pore as small as possible, so that we get the less scattering possible.
Okay, fine. Thanks.
Yes.
Sandeep,
Yes.
You said that the percentage transmission decreased from 63 to 40% when the detector shifted from 1 centimeter to 40 centimeter.
Yes.
Now that decrease in transmission is understandable, and it is very natural also to occur because you are moving your detector. So basically your beam is expanding continuously.
And actually, this is if we take the
So this
crystals, so there is a
decrease in transmission is can be correlated with the increase in the distance between the sample and the detector. Right. So what exactly you are extracting out of this experiment, that percentage G decreased from 63 to 43 when the detector was shifted from this to this? This is expected.
Now this is expected, but we have a good quality crystals, so the loss is very low. And we
Okay.
try this in crystals available in our lab. We see this loss is very low when there is a almost 100% density.
Okay.
There is no scattering center.
Fine. And this sample which you had prepared, this didn't have any sort of other imperfections, na? So that is because you are relating the loss of all this thing because to the pore size. So
Pore
pore
size
size
and color
becomes
centers
important
actually.
if there are no other residual imperfections in the sample.
Actually, we use a very high purity, almost 5.9 purity aluminum nitrate, and 4 and 5.9, 3 or 4, 4.9
No, I'm
purity
talking
tritium nitrate.
about in the sample, when the sample has been prepared and your annealing has been done, and there should not be any visible or imperfections in the, for example, agglomeration or anything.
Now,
Because then, of
agglomeration,
course, you can relate.
there is, but we have used some surfactant and
Okay, fine.
surfactant to keep
Thank
the
you.
agglomeration as low as possible.
Fine. Okay.
How do you see the color centers, and how do you say that it is not there?
It is mentioned actually papers, they around in India around 300 nanometer less than. The strong objection, this is closure due to color centers, and these color centers basically oxygen vacancy due to pores and others. And when we annihilate these color centers,
No, but did you test
gone.
it? It is a color center. Did you test it that it is a color center?
Now
which is...
we are doing that, but still not.
Okay.
We can move to the next presenter.
Next presenter, Mr. Chinmaya, EP0311. Please start.
Good afternoon, everyone. Am I audible?
Yeah, please.
Good afternoon, everyone. Yes, sir. I'm Chinmaya Kara, presenting this paper, Graphene Enhanced Dual Band Near IR Absorber in a Multi-Layer Grating Structure. As per the title, we have designed a dual band absorber by simultaneously exciting two interface states in a photonic heterostructure. The states are optical TAM states and TAM plasmon polaritons. As well, we have used graphene to enhance the absorption of the modes of the structure. Can you go to the next slide, please? Can you go to the next slide, please? Hello?
Yeah,
Can you go to the next slide, please?
You're on the next
yes,
slide.
the device config. Yes, sir. The device configuration is shown here. This consists of a distributed Bragg reflector, and which is mounted at the bottom by a silver layer, and the top at a reflecting silicon grating. The parameters of the grating has been optimized to match with the reflection bands of the DBR. There is a special layer between the grating and the DBR. As well, we have placed a graphene monolayer between the grating and the DBR. The absorption spectrum of the device has been calculated using finite difference time domain in 2D, considering the symmetry of the device. The FDT simulation along with the region, along with the boundary conditions is shown here. There are two interfaces in the structure, one at the DBR and the grating, and another at the metal and the DBR. So the optical TAM states are excited at the DBR and the grating interface, and TAM plasmon polaritons are excited at metal and the DBR interface. And monolayer of graphene is been used to enhance the absorption of the device. We can see the absorption spectrum of the device in the next slide. Can you go there, please? The absorption spectrum of the device with and without the graphene layer is been here in the picture, and we can see that there is a huge enhancement of the absorption of the optical TAM states due to presence of the monolayer of graphene. That is, graphene layer is absorbing the interface mode due to high field confinement in the region, which is shown in the field profile data in the picture. The device absorption modes have been behavior of the modes have been also studied by varying the spatial layer parameters and grating parameters like its width and height, and a refractive index of the outer medium. Normally, the TAM plasmon polaritons are insensitive to the outer refractive index of the medium, but here, due to presence of the patterning of the silicon layer, we can find that there is a somewhat sensitivity of the TAM modes towards the outer layer of the refractive index of the medium. So this can be used to fine tune the device. Along with the, we can find a strong coupling between the device. This can be used for numerous optoelectronic applications like sensors, filters, mode log lasers, thermophotovoltaic devices, and all. Thank you, sir. Thank you, sir. I have none. Hello?
Is it a design now, or is it a device?
Presently, yes, sir. Presently, this is a design, and we are in a process to manufacture the device. And along with, we are also in the process to observe its behavior along with the angle of incidence of the beam. Because in this design, the angle of incidence is normally, and polarization is being shown in the second slide. And there has been recent reports in 2021 that for using the silicon grating, we can found bound states in continuum at very less angle of incidence. So we are in the process of fabrication of the device.
How will it be fabricated? With what process?
Sir, first we have to prepare a multi-layer device, and then we will use some lithography techniques to fabricate the pattern, the silicon on the top, and then we will observe its behavior.
Okay.
You can go to the next one now.
Okay. Next presenter.
Thank you, sir.
Miss Madhupriya, CP0307. Please start.
Hope you can see my screen. Good afternoon, all. Sir, can you hear me?
Yeah, you are audible.
So the topic of today's presentation is theoretical analysis of photonic switching networks using a RADC network, that is a ring assisted directional couplers, which includes the fabrication tolerance analysis. So I'm from the Institute Sastra, deemed to be University, Tamil Nadu. So my actual design is silicon on insulator. So it is sandwiched between, it is a rib network of silicon. So it is a rib waveguide of a silicon, which is sandwiched between the top silicon oxide and the bottom silicon oxide layer. And the bottom substrate will be a silicon substrate. So we are going to design a ring resonator initially. So the input will be fed through the linear waveguide, and I'll be having a ring waveguide like this. So when I'm going to propagate the input light wave through this, either it gets coupled to the ring waveguide entirely or locked up within this itself during the off state, or else it again back couples, giving out a high intensity at the output port. So this corresponds to on state. So how do I tune this? Is that by using a PIN junction. So PIN junction is a p-type material here and an n-type material here. So I'm going to apply the voltage across these two terminals in order to provide a change in refractive index here. So the applied voltage directly proportional to delta n, that is change in refractive index. So this is given by the SORF relation. So my actual device is, initially I'll be optimizing the ring resonator separately, and I'll be optimizing the directional coupler separately, and then I'm going to integrate the device together using an FTTD simulation network. So I'll be applying a different voltage for tuning the on state here, and I'll be applying VDC, a different voltage for optimizing the cross or bar port outputs. So the design of 2x1 RADC network is based on the tuning mechanism. Either on or off state will be tuned according to our requirement. So the gap between the center of the ring and state linear waveguide is optimized as 0.3 micrometer. So the dimensions of my silicon will be, silicon rib will be 450 cross 220 nanometers. So, okay. So this will be the transmission characteristics of 1x2 RADC. So this is for the cross state operation. So initially the ring resonator will be tuned to an off state condition. So this is the off state condition, after which the light propagation will be very, very feeble, and it will be very less at the output. And when I'm going to tune it by applying the voltage of 0.86 volts. So I can either so I can have a on state configuration here, and by either tuning it to an on state or an off state, I can either switch it to a bar port or to a cross port configuration. So this is what the analysis that I have done, and followed by when I'm going to implement this in an experimental manner, so I need to analyze for the fabrication tolerances. So fabrication tolerances can be understood by by analyzing the width variation and height variation. So 450 nanometer and 200 nanometer is going to be my optimized design. So I have evaluated the cross port, that is my extinction ratio has been evaluated for my optimized design, and also the shifted design, that is
Please wind up.
Okay. So 10 seconds I can complete. So I'm going to tune my on-state and off-state for different set of width variation. So I'm going to evaluate the fabrication tolerance of my design network so that it can be applicable for any experimental design. That's it.
Will you couple this device with fibers?
Yes, sir. Actually, we have designed this. We have evaluated all these, especially for data center network. So I'm planning this to implement it in a double layer network. So there are different types of data centers like BNS architecture, switch architectures, switch select architecture. So out of which I'm going to choose double BNS architecture so that I can implement that, especially for data center and cloud trafficking. In order to manage cloud trafficking, I have designed a RADC, so all these RADC network has a optimized crosstalk and also has an appreciable extinction ratio.
Is it compatible with the existing devices?
Yes, sir. Actually, the design, all the design that I have considered here are based on the experimental values only I have taken, and I have simulated that using a real-time values only I have taken. But it is entirely a theoretical analysis. But the values that are exactly, I have taken it from the literature survey papers only, sir. The dimensions, I haven't changed anything. Like I have tuned, the tuning is different and the carrier concentration is different, but which is compatible for the experimental realization values alone I have taken.
Okay.
Okay, then we can go for the next presentation.
Yeah, next presenter, Mr. Ashish Singh, CP0312.
This is Ashish Singh. Am I audible?
Yeah, you are audible. Please start.
Okay. Good afternoon, everyone. This is Ashish Singh Bess, and I am going to present my research work on integrated optical Michelson interferometer on a chip. As we know that the heart of the Michelson interferometer is bidirectional coupler, work as a 3 dB coupler in which the input light divided into 2 equal parts by power. For this, the phenomena is used is FTIR, frustrated total internal reflection. In figure 1, by suitably adjusting the coupling length L, the input power P in may be split into equal or arbitrarily unequal output power P1 and P2. For complete energy coupling, P1 is equal to 0 and all the power is input power is come from P2. Next slide, please. If two identical linear waveguides are parallel to close enough to each other, a coupling length L, they will couple energy due to evanescent field between them. In case of a synchronous codirectional coupler, all the energy can theoretically be transformed from one waveguide to another if the coupling length L is equal to Z such that satisfy kappa Z is equal to 2m plus 1 multiplied by pi by 2. Here m is real number 0, 1, 2, 3 and kappa is coupling constant. It depends on the core material refractive index and separation between the parallel waveguides, in which I firstly simulate by console multi-physics software bidirectional coupler. Here in figure A, the symmetric design are shown, and from figure B to D, here B shows the complete power transfer by FTIR from one port to other, and in figure B the power is transmitted in half in the 50-50 power transmission, and in fourth one the waveguide separation is such that there is no power transmission from one waveguide parallel to other. Next waveguide. Next slide, please. Here we fabricate that bidirectional coupler by using UV photolithography and the use as core material a polymer which is S1813 by microcam. The in simulation we decide the width of core is 1 micrometer, but here some fabrication limitation we are not able to achieve that low dimension. We are able to achieve approximately 20 microns, and we are further work on that further reduce that width so we can achieve that dimension. And due to this limitation, the FTR can't take place in such a large distance between two parallel waveguides. That is approximately 25 micron. So our conclusion is we establish a low cost and simple UV photography lithography setup to fabricate a bidirectional coupler waveguide and demonstrate the coupling and decoupling of light from all the ports. Thank you.
What is the material you have used for this?
Sir, we use core material polymer that is S1813 microcam. Its refractive index is 1.62 at 1.55 nanometer. 1.55 micrometer wavelength.
Okay.
Okay.
These this microscope, these boxes are not clearly visible, at least to me. In figure 3, you are showing 3 optical micrographs.
Okay.
They are not visible.
Yes.
Anyway, fine.
Optical
Thank you.
micrograph. Okay.
Okay, we can move ahead now.
So next speaker, Ms. Susmita, CP0314. Please start. Ms. Susmita, are you there?
Yes, sir. Hello.
Yeah, please start.
Hello. Yes, sir. Good afternoon. Am I audible?
Yeah.
Hello. Okay. So my topic is on synthesis of carbon aerogel Boyle's foam target for laser metal interaction studies. The next slide. Next slide, please. The utilization of ultra-short intense laser in the field of laser metal interaction for the area of X-ray and fast electron generation and shock enhancement are a recent topic of interest for the researchers. For this reason, the low density thin foam targets are necessary for the enhancement of energy coupling efficiency, coupling of plasma and the laser in the plasma. So this motivated our work, that is for the development of cost effective and reliable and simple approach for low average density and high local density foam targets, which is a key requirement for these type of interaction studies. So the carbon aerogel, the optimum thickness of carbon aerogel that is required theoretically calculated from plasma critical density is nearly to be 10 to 20 range. Next slide. Next slide, please. The carbon aerogel that we prepared was synthesized using dissolved formaldehyde-based gelation, and with which we have obtained the density of 200 milligram per cc of the density for the carbon aerogel. The surface properties of carbon aerogel that has been listed in the table shows the area of 1900 meters square per gram and the total pore which attributes to the lower density carbon aerogel. So these low density carbon aerogel was further used for the preparation of target materials, and these target materials were prepared using the two different binders, that is Nafion based binder and PVA based binder. The Nafion based binder was volatile solvent based binder, and PVA is the organic aqueous based binder. So because of different binding capabilities, the film quality that has been achieved with two different binders were different. So we have observed that the nephron base binder was more defect-free. So we have carried out studies using the nephron base binder, and in the image, the same image showing the uniform thickness dispersed image of the film over the metal foil, and the small inset is showing the foam target structure of the carbon material. The thickness of the film was measured using the profilometer, which gives about 10 micrometer thickness with the roughness of 1.87 micrometers. So this was further used for initial experiments using the ultra-short femtosecond lasers with a system of 25 femtoseconds and 150 terawatt titanium sapphire laser system, where copper K alpha X-rays was observed because the metal foil substrate that has been used was copper. Copper. So the image showing the X-ray spectrum, where we can see the with pure copper, the background radiation was
wind up.
more compared to the foam-based targets. So these type of experiments are required in order to in order to observe the plasma laser plasma imaging using the short duration X-ray sources. Thank you, sir.
Did you characterize the X-ray emission which you obtained? I mean,
No, sir. Actually, we were working in the collaboration with this laser plasma division, where they has characterized this, and we have prepared the target material.
Okay, fine. And what is the other application where you can use this carbon aerogel?
We are using various applications that as a substrate matrix for this catalyst applications, and also for supercapacitors application, and absorption for impurities absorption. Various
Purification
applications we
studies
are
also you use it?
Yes, sir. We are also doing the purification studies at water desalinations. Studies are also performed using these
So
carbon
these types of similar types of samples you use for other applications also. And this is a new
Sir,
addition to the already
yes,
other
sir.
applications.
Actually, we are just tuning the properties of carbon aerogel depending on the application. But because in our other applications, we need high density carbon materials. Here we require low density carbon materials.
Okay, okay. So this is the difference.
Yes, sir.
Okay,
How can
thank
you,
you.
how can you further decrease this?
Actually, sir, we can perform different activation methods by which we can decrease the density of carbon materials, and also during the preparation, different type of chemicals that can be template by templating it. Adding some templating material, we can further reduce the density of carbon material.
Is it the density which you got? Is it optimized for this plasma X-ray?
It is not fully organized, because we are just here we have done just initial experiments in order to observe that whether we are getting something or not.
Okay.
Yeah, we can go to the next.
So next speaker, Mr. Jivraj, CP0303. Please start.
Good afternoon, everyone. Sir, am I audible, sir?
Yeah.
So in this work, we are going to present the synthesis and characterization of luminescent property of organic inorganic metal halide, imidazolium lead. Organic inorganic metal halides have received a lot of attention because of their exceptional properties like high absorption coefficient, suitable band gap, and high defect tolerance. In particular, 3D perovskite methylammonium lead is being explored for its use in light emitting diodes because of its high color purity and narrow emission lane. However, its stability and photoluminescence quantum efficiency remains an issue. The reason for its low photoluminescence quantum efficiency of bulk methylammonium lead is because of its low exciton binding energy, that is around 10 millielectron-volt. As this is less compared to the thermal energy at room temperature, which is 25 millielectron-volts. So in this work, we have incorporated a larger imidazolium cation at the A site, that is at the A site of the ABX3, which results in low dimensional behaving hybrid halides. So next slide, sir. So in this, we are going to discuss the synthesis and characterization. We have used a simple evaporation route. We have taken imidazole and lead iodide precursor and have dissolved in the respective solvents and evaporated the precursor solution at 60 degrees Celsius at constant temperature water bath. And we have received yellow crystalline powders. And we have characterized these yellow crystalline powders with the XRD and Fourier transform infrared spectroscopy. And from the XRD, we identified that these imidazolium lead iodide crystallize in a hexagonal non-perovskite crystal structure. So even though it has a ABX3 stoichiometry, it is not a perovskite structure, as the octahedrons, inner lead iodide octahedrons in the imidazolium lead iodide has a phase sharing. Is phase sharing along the C-axis, and it is surrounded by imidazolium ions, stabilized by the imidazolium ions through hydrogen bonding. So this is a one-dimensional behaving structure. The lead iodide is connected only along the C-axis, along the C direction. All the observed vibrational modes confirm the presence of imidazolium in the conform, and which is confirmed by the FTR measurement. So in the next slide, here we have investigated the optical properties of the synthesized imidazolium lead iodide. We have used UV visible absorption spectroscopy to determine the band gap, and the band gap is estimated to be 4.65 electron volt from the top part. And from the UV visible studies, we also observe an excitonic peak around 290 nanometer. And we have excited the sample at 260 nanometer to study its photoluminescence property, and we have identified a prominence peak at 540. And this mechanism is because of the self-trap excitons. And we have also calculated the CAE chromaticity coordinates, and the CAE chromaticity coordinates matches with the color of the crystalline powders when it is shown by UV light at 360 nanometers. So the insert shows the crystalline powders at ambient light and in the presence of UV light. So on ambient light, the powder looks in the yellow color, and when it is excited with the UV light of 360 nanometer, it is in green color. So that's it.
What is the new result? Because this is a old material itself. People are working on, isn't it? What is the improvement you are observing? Mr. Jivraj?
Mr. Jivraj, are you there?
I think we can move to the next presenter.
Next presenter, Mr. Raghu, CP0315.
Yeah, can you hear me?
Yeah, you are ready.
Yeah, good afternoon, and I am Raghuram from IGCAR Kalpakam. I'll now briefly discuss about temperature cum photon sensing application of bimaterial microcantilevers. Next slide, please. Microcantilevers are nothing but miniaturized MEMS structures which are fixed at one end and free at the other end, something similar to a diving board in a swimming pool, but a million times smaller, with the typical dimensions in the range of few micrometers. They are nothing but AFM probes, but they are also being used for various sensing and actuation applications with a very high sensitivity due to reduced size. Here in this experiment, we have used a silicon microcantilever coated with aluminum thin film. When such a microcantilever is exposed to temperature variations or photon flux as shown on the top right-hand corner, it deflects. The bending is understood in terms of a differential thermal expansion of the materials involved. So now I'll come to the experimental details. The schematic is shown at the bottom, and the photograph, the schematic, the experiment consists of a UV diode laser which excites the micro cantilever, and the detection, the deflection is monitored by a position sensing photodiode. It's a four segment quadrant photodiode. However, this photodiode generates a current signal in nanoamperes, but we need information in nanometers. So we have calibrated as shown here using a force distance curve. Similarly, we also, using MATLAB program, we generated an incident intensity profile of the laser beam, and then integrating across only the MC dimensions, we could estimate the power absorbed by the micro cantilever, which is useful in analyzing the experimental results. Next slide, please. Now I'll show the results. The experimental results are shown on the right-hand side, and the theoretical estimations are shown on the left side. The first graph shows a Z in nanometers, that is the deflection, as a function of R. R is nothing but it represents metallic thickness. Here I have shown the plots for two different materials, one for aluminum, one for gold. So two important observations can be made from here. One is aluminum is twice sensitive compared to gold thin film. Second is there is an optimized parameter, there is an optimum value at which the deflection sensitivity can be maximized. Now, in order to validate these estimations, we have done the experimental, it is shown on the right-hand side. The first graph shows the deflection profile. This is a reference microcantilever, which is coated with 50 nanometer aluminum. It shows MC deflection plotted against time in milliseconds. From this, we also estimated the response time of the microcantilever, which is about 1 millisecond response, and the magnitude is about minus 42 nanometers. Then we tried to estimate the deflection sensitivity by varying the aluminum thickness from 50 nanometers to 300 nanometers in steps of 50 nanometers. It shows a linear increase according to the theoretical simulations, theoretical estimations. And third graph shows the temporal response, which is about 1.1 milliseconds. And the fourth graph shows the temperature due to the absorption of the photon. There is a rise in temperature, which is about 7 degrees, corresponding to 2 milliwatt laser power. It shows a temperature profile, which is existing along the length of the MC, which is established along the length of the microcantilever. So I would like to just highlight the important results. Aluminum is twice sensitive compared to gold, and experimentally we could show 6-fold enhancement with a 300 nanometer thick aluminum film. Further, it can be enhanced by reducing the thickness of the substrate thickness. The results are summarized in the table shown below, where from the last row one can see that corresponding to 300 nanometer aluminum thickness, we can get a temperature sensitivity of 23 millikelvin per nanometer. 23 millikelvin per nanometer, which corresponds to about 38 picowatts of laser power, which translates to 41 femtojoules of laser energy with a response time of 1.1 milliseconds. Thank you.
Raghu?
Yes, sir.
It is a nice presentation, and I would like to ask, how do you measure these deflections?
Yeah, if you go to the previous slide, it is actually there is a photodiode, a quadrant photodiode in combination with another sensing laser. The sensing laser is reflected from the microcantilever, and any bending of the microcantilever results in shifted position on the photodiode surface. So from there it is calibrated, sir. It is a normal phenomena in AFM. I have used a part of that.
Okay, okay. So what is the angle which you get? What is the angular deflections?
No, it is not angular. It's a vertical or a horizontal shift in.
At the cantilever side, it will be an angular displacement, isn't it?
No, it is not calibrated. Only my laser was incident normally. So that is all calibrated, sir. It gives a signal in nanoamperes, but we just need to convert into nanometers, which is done by a force distance curve.
Have you now finalized a design where you can use it for some application?
No, we want to. Yeah, it is already done. We have done many experiments, and we are trying to extract especially thermomechanical parameters like thermal conductivity, Young's modulus of thin films, especially uranium dioxide and boron related to the department. I am just planning for the experiments. This is only a prototype like I have developed.
Okay.
Shall I go to the next speaker?
Yeah, we can go to the next one. Yeah.
Next presenter, Mr. Sushil Kumar, CP 0313.
Okay, good afternoon, everybody. Am I audible?
Yeah, audible.
Okay. This talk is related to LAP crystal. Next slide, please. Next slide, please. Okay. LAP is one of the important material for high power laser applications. It has better properties than KDP, but there is a problem. Basically, the growth rate is low, and the low is mainly along the 100 phase. So our aim is to determine how to increase the growth rate along this phase. And we know that the main parameter, there are various parameters which affect the growth rate crystals. One of the main is supersaturation. So our aim is to determine the effect of supersaturation on the growth rate of 100 phase. For this purpose, actually, we establish a setup. Please, next slide. Next slide, please. Okay, this figure shows the optical setup, and the technique is birefringence interferometry. The main problem here is how to align the crystal along the dielectric axis, basically. So first we determine the axis related to the 100 phase, that is 35 degree basically. So we align the crystal, the beam 35 degree from the crystal phase, and calculate the growth rate basically, and then finally reconvert it to that growth rate along the 100 phase. Next slide, please. Okay, this shows the results. Here, the practical result basically, this shows how the intensity of transmitted beam varies with time, and we converted this into growth rate. This figure shows the growth rate, supercooling versus growth rate. We see the growth rate increasing as we increase the supersaturation, and this is almost linear growth rate enhancement, but the slope is very low. So it shows that growth rate can be increased by supersaturation, but it is not very high actually. So still we have to work some more. And the ground crystal was cut, made an element, and based on the transmission is sufficiently good even at the growth rate of this 1 mm per day. So conclusion is that we have developed a methodology to investigate the growth rate of LAP crystal along 100 phase using birefringence interferometry technique. Result indicate that growth rate increases with the supersaturation almost linearly, and the optical quality of the ground crystal was sufficiently good. Thank you.
Sharma ji,
Ji.
You mentioned that this methodology is developed or something. So, what is new in the development?
Actually, this is regarding LAP. In case of LAP, applied in case of LAP. This is not new. We applied first time in case of LAP because LAP is a monoclinic crystal, and the dielectric axes are not normal to the heavy phases. So that we have done here actually, that how to align the beam along the dielectric axis basically. So that we have done. That measured successfully.
And this growth rate measurements along this direction, they are this is done using this current this thing.
No, this is done.
Okay.
Not now.
This is not done.
Not current year work.
Okay.
But not reported.
Fine. Okay. Thank you.
What is the growth rate you are targeting?
Actually, normally the growth rate of this LAP along 100 is typically 0.1 to 0.5 m per day. And as you increase it, inclusions and other problems arises. Here, actually, we achieve, because setup is small, we have achieved around 1 mm per day. So we achieve higher, but the setup is small one.
So you can improve it further.
We have to extend to the main setup, actually, big setups. We have to extend that way. So that we have to do. And there may be other factors also, which may influence the growth rate.
Shall I go to next?
Yeah, we can go to the next.
So next presenter, Mr. Veerappan, CP 03.
Good evening, sir. So I am Veerappan from Anna University, Chennai. My topic is on quantification of nutrients content in Careca papaya using laser-induced breakdown spectroscopy. The objectives are laser-induced breakdown spectroscopy techniques is used to identify and currently the macro element content in Careca papaya. The plasma electron temperature is estimated using the Boltzmann plots. The electron density is laser-induced plasma is determined using Saga-Boltzmann equations. The calibration-free Lipps method is used to quantify the macronutrients in Carica papayas. The laser-induced breakdown spectroscopy technique is used to determine the element composition of samples irrespective of state, solid and liquid or gases. The advantages of laser-induced Lipps technique is remote sensing capability, in situ identification, minimal or no samples preparations, high insensitivity, and multi-element analysis. In this diagram says the incident photon is entered to the particular atoms. It observes some energy. It is go to the excited state, and sometimes it's comes to the ground state. It emits some photons. It's collected to the clarifications. This is the experimental setup. This is the experimental setup. Q-switched NDAC laser you are used to ablate the material under analysis. It has the wavelength of 350 nanometer, repetition rate of 10 Hz and pulse duration of 5 nanoseconds. The high energy laser beam is used to focus on the target using plano-convex lens of focal length of 300 mm and dia 50 mm. The optical emission of the plasma is focused into fiber optic cable using collecting lens of the focal length 100 mm and diameter of 50 mm. To reduce the continuum radiation of spectrometers triggered after the 6 microseconds from the laser pulse using the delay generator. The optical emission is collected from the plasma is spectrally studied using the spectrometers. The flowchart determined the calibration-free Lipps method. The first analyze the Lipps spectra. For quantitative analysis, we have recorded the Lipps spectra of our sample. From this spectra, we can quantitatively determine the macronutrients present in our sample, and then calculate the plasma temperature using the Boltzmann plot, and then calculate the electron density using the Saga-Boltzmann equations. And determinants of density ratio of the species of particular elements. The Saga equations reading the concentration into consecutive charges Z and Z plus 1 of particular element, and then these two use parameters are used to calculate the concentrations. So next slide. Next slide, please. Hello.
Yeah.
Sir, next slide.
Yeah, this is in the last slide.
No, sir. Okay, sir. Yeah, resultant. This is the resultant discussions. This is obtained the graph. The graphs are present are some elements. The mostly the calcium, magnesium, and potassiums we are taken in these samples, and spectra is showing. Spectra is hello. Spectra is showing irradiance, varying the irradiance, and then estimation of plasma temperature and electron density. This graph is shows the varying the irradiance, the plasma temperature and electron density also it's the varying, and then you calculate the concentrations in irradiance of 2 minutes in the calcium is 0.488 plus or minus error of 0.042, and then potassium is 0.4 somethings and magnesium is 0.9. In analysis of Clarica papaya is the magnesium content is much more of compared to other elements. It's proved is there. In conclusion of our project is the free calibration laser induced breakdown spectroscopy techniques used in this process of estimating the elements and the raw papaya sample at the laser irradiance of 2 into 10 power 11 of watts per centimeter square. From the experimental investigations, we conclude that the sir.
Please wind up. Your time is over.
Okay, sir. Thank you, sir.
Why do you use lips for this simple work?
This is a reduced sample preparation, sir. Very simple sample, no need of sample preparations. It's directly used.
But is it required for papaya? You do it for every
Just to analyze the food.
See, this is a very complicated experiment, laser-induced breakdown spectroscopy.
Is there in our idea is it's more to the portable device, on handheld device, using a farmers also. You
No,
can also use it in soils measurement, plant.
Take a sample and do it for. You don't require to do it for every papaya, I think.
Sir, no, sir. My aim is the whole experiment setup is go to one portable device, sir, handheld device.
But even lips cannot be a handheld device, is it? Is it so compact at the moment?
Yeah, it's only will try it, sir.
At the moment,
work is progress.
At the moment, how big is your setup?
Sir, in my setup is handheld, sir, just or 1 kg or 2 kg. That is only. It's a portable device.
It's a portable device. What is the laser?
Yeah, yes.
What laser is it?
So NDAG, sir, NDAG laser.
Okay.
Cost is very much high, sir. That only lagging.
And signals are good, which you can detect very simply, or it
Sir,
requires some.
Yeah, yes, sir. 10 energy is 10 millijoules, sir. That only I needed. 10 to 15 millijoules.
Okay.
No need of higher energy, sir.
But for this application, I think it will be very big test for this papaya.
Yes, sir.
You have to justify that.
Sir, not understand, sir.
Okay. Thank you.
Okay.
You can go for the next.
Next presenter, Mr. Chiranjit, CP 0317.
Sir.
Yeah, you are audible. Please start.
Okay. Sir, good afternoon, everybody. My topic for presentation is fabrication and testing of TSB PMA composite elements for X-ray imaging and INDUS2. Here, TSB PMA stands for a composite material, where TSB stands for transtylbin and PMA stand for polymethyl methacrylate, which is an organic polymer. TSB crystal is used as scintillator material for detection of X-rays, gamma rays, and high-energy neutrons. Since growth of the TSB single crystal of large cross-section is difficult and costly, there is extensive attention in developing scintillator material in composite form. Here, PMA composites has been developed for X-ray imaging applications. PMA was used is selected as host material as its density and refractive index are near to that of TSB crystals. So now the next slide, please, sir. Hello.
Yeah, it is on next slide, Chiranjit.
Okay.
Make it full screen.
So this is the synthesis flow chart for TSB PMA composite. How we have prepared the TSB PMA composites here, it has been described. Here we have used transtylbin powder of 98% purity and make alpha SR, which was further purified by zone refining process, and then this powder was dissolved in a liquid MMA, which is a monomer of PMMA. Now then the whole mixture was homogenized by several stirring and sonication process, and then it was degassed at 70 degrees Celsius for 24 hours. Then we have added some initiator for polymerization reaction, which is AIBN. Then the whole mixture was again homogenized by several stirring and sonication process and heated at 68 degrees Celsius, resulting in TSB PMA composites. So through this process, we have prepared different TSB PMA composite materials of different TSB concentration and different dimension. So this is the experimental data. These are the So here we have shown the transmittance spectra of the TSB PMA composite materials of having concentration TSB concentration 5 weight fraction, 10, 15, 20 and 25 weight fraction. And here we have observed that for all the cases the transmittance are above 75% for in the visible range. And here we have also observed that the wavelength cutoff increases with increasing concentration. This is the photoluminescence spectra obtained for excitation wavelength 240 nanometer for different. This was for different TSB concentration, and here we have observed that the luminescence peak arised at about 370 nanometer wavelength. So then the X-ray imaging was performed using X-rays of 10 kV energy, and illumination time was 180 seconds using Indus beamline of our synchrotron facility. So an object in the form of mesh with wire diameter 100 micron was used for imaging, and these are the imaging photograph. Here we have observed that with increasing concentration of TSB material, the imaging quality has been improved. And conclusion, large area TSB PMA composite elements having different TSB concentration have been fabricated. It is found that TSB concentration should be as high as possible for X-ray imaging while maintaining the optical quality and physical stability. Thank you.
So finally, it has been used, is it?
Yes, sir.
Okay, okay. What is the size you told?
This is about 50 mm diameter and 5 mm thickness, and this is about 45 mm length and 25 mm thickness.
And there is good homogeneity all over?
Yes, sir.
Okay. Okay.
Chiranjit?
Yes, sir.
You mentioned about heating at 68.
Yes, sir. Yes.
Right. How did you arrive at 68?
Because we have used some water bath, optimized that at certain range. It was maintained at 68 degree plus minus 0.5.
No, Chiranjit, question of Dr. Muti Babu is, how did you get this 68? Why not 67? Why not 65?
Okay, okay.
Yeah.
So we have optimized at 68 degrees Celsius, and we have observed that below this temperature, the reaction polymerization rate is less, and which leads some segregation of the TSB material from the solutions, MMA solutions. And if we increase the temperature further, then the MMA composites become evaporated, and MMA material evaporated and make some bubbles inside the matrix. So
Thank you. Thank you.
Thank you. I think we can move to the next.
Yes. Next presenter, Mr. Sujan Kar, CP0318.
Good afternoon, everybody. Hello, I am audible?
Yes, yes. Please go ahead.
Good afternoon, everybody. Title of my poster is Synthesis of Amend of Mg2GeO4 Phosphor and its Characterization for X-ray Detection and Imaging Applications. Next slide, please. Absorption of high energy X-ray photon and convert them in visible photon is very essential for radiation exposure monitoring, security inspection, X-ray astronomy, and medical radiography. The absorption of X-ray by phosphor depends on the atomic number of the material. For X-ray imaging, radiation exposure and to the patient is an important issue. Phosphor must be dense enough and high material to absorb 100% of the impinging X-rays. This reduces the dose required for a given image quality. Germanium is one of the suitable elements for this type of material. In this work, we have prepared red-emitting amend of Mg2GeO4 phosphor with broadband ultraviolet visible absorption. Utility of this material for X-ray detection, imaging application have been explored. And we have prepared, next slide, please. We have prepared amended Mg2GeO for phosphor by solid state reaction technique. High quality, high purity MgO-GeO2, MnO2 are taken in proper ratio, then mix them in ball milling. After milling them in ball milling, the mixture was taken in a furnace and it was heated at 1250 degrees centigrade for 6 hours. Synthesized powders were then characterized by XRD. Phase identification was done and it was perfectly matching the JCPDS file. Photoluminescence studies. For photoluminescence studies, we have prepared pellets from by hydraulic pellet press machine. Excitation scale of the pellets are taken by varying the wavelength from 200 to 300 nanometer, and it has been observed that the absorption, the maximum absorption comes at 271 nanometer. And then after excitation scale nanometer, we have observed that PL emissions comes at 640 nanometer. This absorption comes due to the transition from 4A to 4T1 level, and then during emission, the transition of electron from 2Eg to 4A2 level. To study the distribution of trap centers, next slide, please. To study the distribution of trap center inside the material, thermoluminescence study have been performed. In the glow curve, 3 main peaks are observed, found at 152 degrees centigrade, 201 and 355 degrees centigrade, and corresponding trap depths we have calculated from the formula Tm by 500, and it has been observed that trap depths are 0.85 electron volt, 0.94 electron volt, and 1.25 electron volt. Phosphor coated with tantalum sheets used for X-ray beam monitoring at Indus 2 beamline 7. Synthesized powder samples are coated on tantalum sheet with special adhesive. Coated sheet was used for beam positioning at X-ray scanner. The energy band of the X-ray was selected 3 kilo electron volt to 11 kilo electron volt. The emitted fluorescence was detected by CCD camera. Detected beam size was monitored and size was measured 3 mm cross 70 mm. For X-ray imaging study, synthesized phosphor powder were grinded very well and sprayed on a sellotape of size 10 mm cross 10 mm, and the upper portion of the sellotape were covered with another sellotape. Preliminary X-ray imaging application was performed in Indus 2 beamline 4. X-ray energy that during that experiment was 10 kilo electron volt. Kilo electron volt during experiment. Beam current was 95 milliampere. A copper grid of wire diameter 90 micron and square gap of 170 micron was kept between X-ray beam and the phosphor sample. After passing the X-ray through copper grid, just 10 seconds. Copper grid, it was falls on a phosphor material and scintillation comes. This emitted light is then collected by CCD and image is formed. The image shown in the figure is slightly is not very clear because the phosphor was not uniformly spread. Thank you.
Sujan,
yes.
What
Yes,
is the role of manganese?
Manganese basically it is acting as a it is trap center and luminescence center. It gives basically the luminescence.
Okay. If there are no questions from, we can go to the next.
Okay.
Thank you, sir.
So next presenter, Mr. Sanjeev Kumar, CP0322. Mr. Sanjeev, are you there? Mr. Sanjeev, you are mute.
Hello.
Yeah, you are audible now.
Yeah.
Yeah, please proceed. Sanjeev Kumar.
Just
Good afternoon, one and all.
Yeah.
Topic of my presentation is the design and imaging characteristics of a radiation extent achromatic doublet lens. Actually, under this work, we have designed an achromatic doublet that will be used for relaying the images from the object area to the final CCTV sensor of the optical periscope, which is being developed for remote viewing inside a radioactive waste vitrification plant. Actually, this radiation the chromatic aberration plays a very crucial role when we design periscopes or camera or like that. So it has to be minimized because it creates the color fringing in the center as well as around the edges. And this chromatic aberration comes because the this index, refractive index is different for different focal different wavelengths of the this our visible region. So achromatic requirement becomes more crucial when the image on an object is transferred to the final sensor over a long tube, such as in our periscope. So this can be minimized by combining actually two singlet lenses of different dispersions. They will have different this Abbe number, and that in the first figure now we can see that different wavelengths are focused at different focal lengths, different wavelengths. So, and the second, that is the achromatic doublet. So, in which we have done the focusing for at the same point for two wavelengths. Only for two wavelengths we can do this consideration. Next, please. So, actually, these are the design parameters. Actually, design parameter methodology is based on these two equations. Actually, this total power should be the sum of these singlets, and change in the power for two wavelengths should be 0 or C. C is the residual, but C, so we will try to make it C equal to 0. So this is the symmetric diagram of the achromatic doublet lens designed for at a D wavelength of the hydrogen spectrum. So these are the parameters. Optical lens diameter is 50 mm, working aperture is 45, and R1 is 130 mm. R2, R3 has been kept equal at 99.4 millimeter. So R4 is minus 320 millimeter. So total thickness of this lens is around 14 millimeter. Next, please. So here we have represented some plots which defines this imaging characteristics of this lens. First figure number 2 represents that spot size. Actually, spot size that is around is coming around 100 micron, which has been reduced by one order. Otherwise, it is in millimeter. And the second, this is the main characteristic of this achromatic lens. Second one, this is the plotting of the focal length versus the wavelengths. So we can see here that two focal length for the two wavelengths, C and F. C is here blue and F is red. For them, both are equal. So focal length has become equal for two wavelengths in this design. But for still there is some displacement from the mean wavelength. That is the D wavelength. We can say yellow region. We can say. So that is around 116 micron. Still, that will not, we cannot reduce in this doublet. That can be reduced in the more complicated system actually. That will involve more elements, 3 elements, 4 elements, 5 elements. That becomes very complicated, but that is not required for visual examination. That's all. Thank you.
So you have stopped correcting it, and you have got 100 microns. So what was the requirement of resolution in your system?
Actually, requirements should be that kind of diffraction limit plays a crucial role. Actually, we cannot go beyond that.
Yeah, how much is the diffraction limit in this case?
It will be around 10 micron.
Yeah.
Still, there is some scope.
Yeah. So what have you also corrected for the spherical aberrations?
Yes, spherical aberration also.
You have not shown it.
Actually, that was due to the limitation of this. I have shown in this poster.
Acha. Because you have to correct both the spherical as well as the chromatic.
Spherical automatically corrects. Actually, when we correct for this achromatic, spherical aberration is also get corrected. But other aberrations we don't
when
need
it is
to
achromatic,
minimize. Other aberrations, astigmatic, etc. They no need to, because we are going to use this relay lenses in pairs.
Yeah, and you are on the axis. Mostly you are on the axis.
On the axis, so they will cancel each other in the entire system. Now, suppose we are going to 6 relay lenses. So 6 relay lenses, one pair of relay lens will cancel out each other's aberrations, other aberrations, I mean monochromatic aberrations. But this is for a visual examination. Actually, this aberration is more crucial. Colors,
because
actually.
you are using the white light.
Yes, white light.
Okay.
Okay, thank you.
Shall we go to next?
Yeah, we can go to the next.
Next presenter, Mr. R.V. Tokas, CP0323. Mr. Tokas, are you there?
Hello.
Yeah. Now you are.
Okay. So, good afternoon.
Yeah, good afternoon. Please carry on.
My topic: development of metal dielectric narrowband pass filter for diode laser induced photoluminescence measurement application. Actually, in BRC, in beam technology group, there is a requirement of band pass filter to remove excitation light at 808 nanometer and to detect photoluminescence signal at 1064 nanometer from a nanomaterial that is being researched for anti-counterfeiting application. So in present work, we have developed a metal dielectric multilayer based Fabry-Perot kind narrowband pass filter in which two cavities of silver, titanium oxide and silver has been combined to give high optical density at 808 nanometer. So this is a computer optimized design shown left side figure, which comprises 6 layers, 5 layer for design and top layer is TiO2 layer. It is just to protect the stack.
Your slides are not visible. Yeah, now we can see.
Okay. So we have designed it, and deposition was carried out by electron beam evaporation and thermal evaporation. TiO2 was deposited by electron beam evaporation and silver was deposited by thermal evaporation. These material was chosen for their good optical constants for in near infrared region. We have realized the device, and device transmission measurement has been carried out by spectrophotometer. It is shown on the right side, and two curves are shown, one measured and one designed. We can see measured and designed peaks are matching, but their amplitude is a little different. So we have simulated what are the errors which have led to the mismatch. So we have simulated using a open source code. And we found there are some minute errors in individual layers thickness while depositing because of uncertainties in statistical nature of process parameters in electron beam evaporation and thermal evaporation. That could be actually minimized using some better technique like ion beam sputtering. So, and other thing, little change in refractive indices while depositing such film must would also have contributed to this mismatch. So finally, we measured its optical density at 808 nanometer. It is around 4. FWHM is 70 nanometer at 1064 nanometer. And transmission is around 23%. This filter has been incorporated in the setup, and some more things are awaited, then the experiment will start. Dr. Sridhar is carrying out this experiment in beam technology group. Thank you.
These types of
narrow
band pass filters. Can you hear me, Tokus? Dr. Tokus?
Yes, I can hear you.
Yeah. These types of metal dielectric narrow band pass filters.
I can hear.
Yeah. These types of narrow band pass filters are commercially available.
These are commercially, of course, available, but such filter, this is customized design, customized filter, the wavelength requirement.
So what I want to ask you is,
thing, if you want from outsider, it will take years. It will take 1 year. So this is in-house facility. We have facility, we can develop it. And design
what
is
is the
specific.
time period involved in fabrication of this and developing these multi-layer coatings and getting the materials and all?
Actually, this is metal diet. The first thing, what we need to characterize TiO2 AG individually for their optical constant, for their thickness calibration. So,
Yeah, please carry on. Hello. Dr. Tokus, your voice is not
it
audible.
took 1 week. Main challenge is depositing metal and dielectric together because their mutual addition is poor. Moreover, if we deposit at higher temperature, metal coatings gives problem in terms of it starts island structure growth, non-continuous film. So we have to avoid that by depositing at room temperature or up to 100 degrees Celsius. And it takes time because we have to extinct all the oxygen supply during the deposition of TiO2 and wait for some time for silver coating.
Okay.
Actually, hello. Actually, you have a reduced peak and you are attributing it to the thickness change or the refractive index changes in the deposition. But actually, since you have got the peak at the same wavelength, the structure and its thickness and wavelength, the refractive indexes should be same. Otherwise, the peak would have shifted.
Actually, what happens? So the bandwidth is 70 nanometer. Peak may not be exactly 106, for it may be 1060, but still it works. There is a shifting in unit position.
But the loss in transmission is more.
It is more sensitive to the thickness values, errors in thickness. It is more sensitive. If we see theoretical background, its value is much more sensitive. There should be a phase match at this value.
No, then the peak will shift. No, peak is more sensitive to the thicknesses.
So both the things are sensitive. But peak width is high. Even if shifts 1 or 2 nanometer, it doesn't make much difference.
The number of layers would have made a larger difference.
Both. Of course, if we increase number of layers, we are increasing absorption. So that will within this design, within the 5-layer design, I am talking about. If we increase number of layer, number of cavity, we are combining more cavity, of course.
Yeah. If you would have added
more, but optical density will increase.
Yeah, but here when you're at the same number of the layers, I feel that the loss is coming from not from the thickness, but from.
No, sir. This is not loss. This is simply redistribution of intensity. Errors in thickness. If it is error in TiO2, it is redistribution because interference conditions are not matching properly. If it is edgy thickness, it is high than the design one. Of course, it will absorb more light and it will decrease the P. And more of it will more other effects also.
Okay.
What is the value of commercially available such band pass filter? What is the percentage transmission?
Actually, it's a design. Even if we get commercial, it cannot go beyond design value. Design value is around 36%.
Mm-hmm.
You can see actually
So
that value is given there.
design value is
Design is 33%, 32%.
okay. Fine. Okay.
Why our main intention to cut the light at 808 with high optical density. That's why we combine two cavity. Otherwise, one cavity could have worked. We can combine more cavities, but transmission will be very small.
Mm-hmm. Fine. Thank you. We can proceed to the next presenter.
So there are no more presenter remaining. So we thank our esteemed judges for evaluating the posters. We also thank all participants of this session for presenting their work in NLS-30. So now we will break for 15 minutes and next session will start at 4:15 p.m. So I request all the speakers to be ready before 4:15. Thank you.
Okay, thank you, Sunil ji, and thank you,
Yes,
Kamath.
yes.
We will see.
Thank you. Thank you. Thank you, Murthy Babu ji.
Yeah.
Thank you, sir. Thank you very much. How do we now?
How do we evaluate this thing? I mean, we have to discuss.
There?
Hello.
Hello.
Yeah. If we can do now, we can do. No problem.
Padma man wants to talk to you.
Yeah,
He
please.
will call you on your mobile.
Okay.
Sunil?
Sir, I am there. I am there.
Right now?
Yeah. I think we can log out now.
Yeah.
Yeah, we can log out.
Sunil?
Yes, please.
We'll meet sometime and
Sure. I will be in my office now after 10 minutes.
Okay.
And I think we can discuss there.
Okay.
And then we will talk to Dr. Murthy Babu.
Okay. Yeah, then we will decide.
That will be a better way to coordinate.
Okay. No problem. Okay.
Thank you.
Thank you.
Thank you.
I think we should leave now.
Yeah.
All attendees can visit the exhibition area on NLS website.
Hello. Can you hear me?
Hello, hello.
Can you hear me?
We are able to hear you.
Yeah, and can I actually share screen once just to confirm that?
Yeah, sure, madam.
Thank you. Yeah. So I think it works.
Yeah. Your slides are visible.
And
Maybe you can
also in
scroll down a little.
Now it is in slideshow mode.
Yeah.
Works fine.
Yeah, works fine, madam. Can you scroll down a little, maybe 2 or 3 slides down?
Yeah.
Yeah.
Works,
Everything
right?
is fine.
Yeah. Should
Okay.
I now unshare?
Sure.
Stop sharing.
begin the session in a few minutes. The session chair is trying to connect, so please bear with us. We'll begin in a few minutes.
And start speaking. Start with.
हेलो सुनो आवाज जा रही है कि नहीं? हेलो
Yes, sir, you are audible.
So now I can. There were some issues. So I have joined now. So now
So shall we
we
begin,
may
sir?
start. We have already started or what?
No, we have not yet started. We'll begin now.
Okay, fine.
So welcome you all to the NLS-30 Day 2 session on quantum and atom optics. The session will be chaired by Dr. S.K. Dixit. There will be 3 speakers in the session. I'll just give a brief introduction to Dr. Dixit. Dr. Dixit joined the laser program of RRCAT Indore in 1987 after completing 30th batch of BARC training school at Mumbai. Since then, his contributions are in the field of lasers and optics, non-linear optics, fiber optics, optical fiber sensors, and laser spectroscopy. He received his PhD degree from Devi Ahilya Vishwavidyalaya, Indore in 1996 in the field of laser technology. He was postdoctoral scientist at Oxford University and visited major laser and accelerator facilities all over the world. He has, to his credit, around 200 publications in journals and conferences. He was editor of a book published in USA. He has guided research work of 4 PhD scholars. Currently, he is leading fiber sensors and optical spectroscopy activity of RRCAT Indore and is a professor at Homi Bhabha National Institute, Mumbai. So welcome, sir, and I now request you to take the session forward.
Okay, thank you, Padma. And all the speakers have joined? Hello?
Yes, sir. The
All the
speakers.
speakers.
Yes, sir. The speakers have joined.
Okay. Yeah. Okay. So all the speakers and all the people who are present online and offline, I welcome you all on this 8th session of NLS-30 on the topic quantum and atom optics. Today in this session, we have three distinguished speakers, leaders in their own field, Professor Urbashi Sinha from RRI Bangalore, Professor M.V. Suryanarayana from BARC Vizag, and Professor S.P. Ram from RRCAT Indore. The first talk is on photonics, quantum science and technology from Professor Urbashi Sinha. Professor Madam Sinha has a very wide experience in the field, and she is experienced from University of Toronto and University of Waterloo, Canada, and Cambridge University, UK. She is a very decorated researcher with several awards such as Homi Bhabha Fellowship, ICTP, ICO, Galileo, Leonardo Award in Optics, Asia's top 100 scientists, as well as ASSOCHAM Women in Cyber. Currently, she is heading quantum information and computing activity at RRI and also heading India's first project on satellite-based secure quantum communications. Now I invite Professor Sinha to deliver the talk. Professor Sinha, you may start
Yes,
now. You
thank
have
you very
25
much.
minutes for
Yes.
5 minutes for question and answer.
Okay, thank you very much. Can you hear me?
Yes, yes.
Yes. So thank you very much to the session chair for this kind introduction. And of course, thanks a lot to the organizers, especially Dr. Nilaya, for this invitation to begin with. I just want to ensure that my screen is visible in full screen mode to everyone. Can you please confirm that? Is my screen visible?
It is, yes, it is visible.
Okay, great. Yeah. So thank you very much. So I move on to my talk. It is, going to be an overview of our activities in photonic quantum science and technologies at our lab at RRI Bangalore. Since it's a 25-minute talk, I won't go into too much detail, but the idea would be to give you a flavor of various things that are happening at RRI, and hopefully it can lead to further discussions later. Well, one of the main, agendas or foci of what we do is perhaps very well captured in this quote, which is today's science is tomorrow's technology. So we actually are a lab where we are having some sort of a happy marriage between scientific explorations, fundamental quantum mechanics, quantum optics, as well as applications in quantum computing, secure quantum communications, and others. So we try to balance between the two and hopefully get the best of both worlds. Our field has gained a lot of, attention in recent times with the National Mission on Quantum Technology and Applications being announced by the finance minister last year, and so hopefully it is going to take off shortly, and that will lead to, I'm sure, a lot more activity in this field in India as we speak over the next few years. Okay, so what is the big picture behind what we do? Well, our theoretical understanding of the universe is very incomplete, and we don't really understand 80% of what the universe is made of. So one of the things that we focus on in the lab is fundamental tests of quantum mechanics and quantum optics. And that is very important because giving precision bounds on various laws and principles actually has direct ramification in the technological applications that they are used for. And so this is one of our focus areas. Of course, the two areas which we are working on in terms of applications, one of them is quantum computing. As you know, there would be solutions possible using a quantum computer that would be exponentially faster than what is possible in classical computing. And of course, secure quantum communication, in which we are dealing with quantum cryptography, among other aspects. So we deal with theoretical and experimental aspects related to all these genre of photonic quantum science and technologies. Right. So this is our lab website. I mean, we don't cover much in a not very long talk. So please feel free to have a look at the website where there is a lot more detail about these various activities and the kind of projects we are working on in this. Of course, the lab is pretty incomplete without the people who, make things happen. Of course, as we know, it's the students who make things happen on a daily basis. And so I'm blessed to have, lots of support there in terms of various categories of people who are working with us and who have been with us before and gone on to other pastures. This is a snapshot of various activities in the lab. And of course, we have this symposium online. This is the third year in a row where we are having several things online, but I sincerely hope that we get out of this soon. And then we would be very happy to welcome visitors again to our lab to, have detailed discussions. It is the National Laser Symposium. So of course, there is, I should say a little bit as to why what we do is relevant to lasers in general. And of course, our session chair is an expert on these topics. So, we work with lasers, and lasers are the ones which give rise to our single photon. So we work with nonlinear optics in our lab, and specifically the process of spontaneous parametric down conversion, which gives rise to our single and entangled photons. So lasers definitely of different types, whether solid state, gas lasers, or diode lasers, various types of lasers are the, first thing we encounter before, of course, lots of other optics and alignment and so on and so forth. So this is a review that I wrote with my students, which is something maybe for people who are coming in from a different background, you can have a look at this about different types of photon sources that are currently available. And of course, also covering the one we are focusing on right now, which is SPDC. And this is how, the SPDC rings look. I'm sure you've seen this before. So these are the, the rings of down conversion. So as you know, the solution to the down conversion, the photons, they come out in the form of cones. And so the intersection point of the cones is where we have the entanglement. So these are, the cross section of a cone is a circle, and these are pictures which have been taken on our own intensified camera. And so this is where we would harness entanglement, because we do not know which cone the photon a priori belongs to. And so we have different types of single and entangled photons in our lab. A little overview of the different types of physics we are approaching with this photons. Well, as I said, fundamental tests of quantum mechanics. So this is a series of work that we have done, which is testing what is called the quantum superposition principle. And the quantum superposition principle, as you know, is the main workhorse for quantum computing. And so we have found, we have proposed theoretically and found for the first time experimentally a correction term to the use of the superposition principle in interference experiments. And this is our experimental data. As I said, fundamental quantum optics, quantum mechanics experiments are of special interest to us. So this, is the Hongo-Mandel dip. So we have actually been able to show that you can get this even using classical pulses. And this work is very recent. As of 3 days ago, it was published. And here we have shown the first loophole-free or unambiguous violation of what is called the Leggett-Gaerke inequality, which is one of those fundamental inequalities which actually rules out what is known as realism. So, Einstein's famous question, is the moon there when I don't see it? So, in fact, that is what is realism. So, the idea is that an object is real even when you don't measure it. But quantum mechanics actually does not say that. It says it's measurement, which the result of measurement is what is real and not otherwise. And so, our experiment actually shows a fantastic match with the quantum predictions. Okay. Entanglement is one of the key areas that we are working on. So, here you have your laser again. This is our tunable diode laser. And this is actually, this is your nonlinear crystal. This is giving rise to entangled photons after a lot of optics and alignment. And here we are studying entanglements, static as well as dynamic properties. We are very particularly interested in quantum measurements. As you know, that is one of the most interesting areas of exploration in quantum mechanics, because when you measure something, you change it, and that forms the basis for many things. And so we are exploring a type of quantum measurement where, by using a statistical ensemble of measurements, you actually do not disturb the system. And that is called generalized measurements or weak measurements. And this is a series of work that we have done experimentally on this topic. A little bit of detail I will go into in the quantum computing and quantum communications applications, because they may be, things that you have already, you're already familiar with from other perspectives. And so our approach to quantum computing is kind of different from the usual approach where you talk about qubit-based quantum computers. What we are working on is, in fact, what are called higher dimensional quantum systems. Okay, and so this is called spatially correlated qubits or qubits, where n is greater than 2 using SPDC. This was the first work from the lab where we generated these qubit pairs. And so the idea being that a qubit has 2 orthogonal basis states, and this is your superposition. A qubit will have 3 orthogonal basis states, and this would be the linear superposition. So by having a single photon incident on a plane with 3 apertures, what happens is you do not know a priori which aperture the photon will go through. And so you form a superposition state of all these possibilities, and that gives rise to what is called the 3-dimensional superposition or the qubit. Okay. And so this is called a spatial qubit. And why is it interesting to explore higher dimensions? Well, a simple example would be, let us consider a football match. Okay, and of course that's not my area of expertise, but maybe some people are familiar with this game, and so I can envisage different results for a football game. There could be a win. There could be a loss. There could be, let's say, a draw. I mean, it just goes on, and then people just give up. Or it could be, let's say, washed out because of rain. These are 4 realistic possibilities for a match. Now, if I want to declare the results of such a match using qubits, I have to use 2 qubits because, each qubit can only have 2 states. So only 2 results per qubit. So I need 2 qubits. But if I had a Q-quad, which is a 4-dimensional system, then all 4 things could be declared using the same system. So what this tells you is, and of course this is a toy example, but the idea being that as you go to a higher dimensional system, then you can have access to the same dimensionality of state space by using smaller number of systems. So 2 qubits, 1 Q-quad. Similarly, what we are interested in as a community is in the, for at least 2-3 years ago, we were looking after this elusive 50 qubit quantum processor. Now it exists. Companies like Google and IBM have come up with this, and as well as a Chinese company. But then the idea being 2 to the power 50 is what we were after, because this is a very large number. But then if I actually replace the 2 with a 3 or a 4 or a 5, then the 50 drops. So I can have the same dimensionality by reducing the number of systems that I deal with. And that, of course, has a lot of advantage, given that, it has taken so long to reach 50 qubits. And so this is the general idea of how you can have the same complexity by using higher dimensions. And what we are working on, so what we have established in our lab is a new way of generating higher dimensional systems by using what is called the pump beam modulation. Again, a detail I won't get into, but then by modulating the pump beam itself of down conversion, I can generate qubits and qubits directly from the nonlinear crystal. Okay, instead of having the photon incident on a aperture system like I showed before, I'm actually modulating the pump itself and generating high dimensional systems. And this is the how the setup looks in the lab. And the whole idea being, based on transfer of the profile of the pump to the daughter photons. So this keeps happening routinely, the Gaussian pump and Gaussian daughter photon. But this is what we have done, that we have transferred this sort of a profile of the pump to the single photon profile at the detector. Okay, and we had very high correlation between these qubits, these pairs of qubits in our first work. However, very recently we have done a lot more exciting work on this over the last 3 years. And in fact, these are 2 papers which have been uploaded to the archive over the last couple of weeks. One was yesterday. Maybe keeping in mind today's talk. But then having said that, the idea is that we have now been able to come up with a new way of measuring entanglement in higher dimensional systems. As you may know, entanglement is a basic correlation, quantum correlation that is required for many of these applications. And so what we have been able to show is a first direct measurement of an entanglement monotone, or a measure of entanglement without using several measurements. That's the usual. We have been able to do this by using only one set of measurements. Okay. And similarly, we have shown a few other things. We've come up with a new technique for measuring this entanglement directly without resorting to this large number of measurements. So do have a look. If you're interested in details of this field, we can have a discussion later. So we are working on diffraction-based linear optics quantum information in collaboration with collaborators in India and abroad, and several QIP protocols using these higher dimensional gates over the next several years in our lab is what we envisage. And again, for students and others who are perhaps not from this field, you can have a look at my invited article in Scientific American, where actually I've given a little holistic overview of higher dimensional QIP in our lab. One of the other things, which we are very interested, I mean, again, this is something which we have done last year, end of 2020, which is about a new quantum state estimation technique, okay? And why is that interesting? Well, as you know, wave function is something that is used to completely describe a quantum system and is central to quantum theory. So in theoretical calculations, one can assume a form of the wave function and then proceed with the calculations. But what about experiments? For instance, quantum computing. You need a precise knowledge of the state of the system so that it leads to precision in all that follows. We simply cannot assume something and think that our assumption is right. And so we can also deduce entanglement by knowing the reduced density matrix, for instance. So what we have done in our work is use one of the most fundamental phenomena in quantum systems, that is interference, to devise and experimentally demonstrate a new method for quantum state estimation, which we call quantum state interferography. And in fact, this is based on this concept of interference, which, as you know, even famously said by Richard Feynman himself, that interference captures within it, the double slit interference captures within it all the mysteries of quantum mechanics. It's, it is at the heart of quantum mechanics. And we have used a version of the double slit, which is a Mach-Zehnder interferometer, a two-path interferometer, to come up with a quantum state estimation technique. So this is the central question we have resolved, that if I have a beam, and in fact, we have reconstructed the state of a laser beam in our experiment, and it is also easily applicable to single photons. And if I have a device, then can I simply, read out the state of the system without changing anything internally in the device? Okay, and this is what is called a black box approach, or a single shot state determination technique. That is quantum state interferography. This is the schematic, which I'll skip, but we had very high fidelity for pure and mixed state reconstruction, highest being 1. And this is very comparable to the conventional method called quantum state tomography, which requires n square number of measurements. Okay, and here we have a linear dependence. So for qubits, only one setting. And so this is something which is very useful again for higher dimensions. As I said, we have a d-1 number of measurements as opposed to settings as opposed to d square. And this something which we can see is going to lend itself to, getting itself made into a product very soon as well. We can just carry around this interferometer in our pockets and measure the quantum state whenever we want to. That is how we see the future for this. Going on to another very interesting area, which involves, again, photons, primarily because photons are really the perfect particles for communication. Photons are chargeless, massless. They don't really interact very well with each other. They can carry information for long distances. And that is why photons are quite irreplaceable as of now in quantum communication. Okay, and the most practical, quote unquote, practical quantum technology is perhaps quantum communication, and the quantum aspect being quantum key distribution. Okay, so why you should worry? Well, these are all the kind of activities that all of us are, doing, purchasing things with credit card, online banking, voting, so on and so forth. So all of these are examples of strategic communication. So if you give some information to your bank, you don't want a third party to get that info. And so this is what currently is kept secure by what is called classical cryptography. But all of this is at a risk of being compromised with quantum computers. And so the solution is, of course, also quantum, which is quantum cryptography. Okay. What happens in classical cryptography is that unconditional security is not possible because it is based on mathematical complexity. So 3 times 7 is 21. That's a simple problem. But if I tell you what are the prime factors of 1, 1, 2, 3, 7, 1, you cannot just say it very easily. Factorization is a hard problem. And the Shor's algorithm, which is going to run using quantum gates, can perform factorization in polynomial time. So the hardness of the factorization problem changes when you use a quantum computer. And so this basis for this protocol for classical cryptography breaks down. Okay. Computational resources grow very fast, and today's hard problem could be solved tomorrow using brute force attack. There could be new algorithms for classical computers. Of course, there is the realization of quantum computers. So my security should be independent of future advancements in computational power, new algorithms, or new technology. That is, it should be future secure. And this brings forth the need for quantum cryptography, where security is based on laws of nature or laws of physics and not on the mathematical complexity of a problem. And the most important part is the quantum key distribution. But just to keep in mind that, the kind of quantum computer which will break the current, number of bits that is being used in RSA requires 4,000 qubits and 100 million gates. And some of you may say, we are not there yet. So why bother? But that's actually very primitive, it's very naive because, the rate at which quantum computing research is progressing, especially globally, is very, very, very quick. So, this sort of functionality could be with us in very few number of years from now. And so we should be prepared with an alternative solution so that it doesn't become a problem, because this will have many other useful applications, quantum computing. So we don't want it to break our security. So we need an alternative method, and one of the forerunners here is quantum key distribution. So far as quantum communications is concerned, our lab is involved in different types of activities. One of them is India's first project on satellite-based QKD, which is called Quantum Experiments Using Satellite Technology. It's a collaboration between RRI and ISRO. We are working on integrated photonics-based QKD in an Indo-Italian collaboration. We have a project under the DST's Quantum Enabled Science and Technology program on long-distance relays and repeaters and quantum teleportation. And we also have a center of excellence in quantum technologies from MITI, the Ministry of Electronics and Information Technology, where we are working on what is called device-independent random number generation. Again, a very interesting area, which gives you a much higher level of security when used in a quantum key distribution protocol. Random numbers form a fundamental part of security in quantum key distribution. We have done several experiments in our lab for QKD, which involves, single as well as entangled photon-based protocols. This is a BB84 protocol. This we did some 5 years ago, which is the first ever QKD protocol that was, devised by Bennett and Brassard. In fact, they declared this in a conference in Bangalore in 1984. One of the things that we have done, which we are very, very excited by, is this implementation of this free space QKD protocol, which has higher key rate and lower error than all known protocols based on this particular approach so far. And we have done this with information theoretic security, and this is in fact India's first published result in free space quantum communication in an internationally peer-reviewed journal. And I'm sure people who are interested definitely have a look at this for the very nice key rates and Q-bar and how we went around achieving those. Entanglement-based QKD, this is a snapshot of our setup, and we have very high amount of entanglement. And in fact, this is another thing we have done is come up with a simulation toolkit for QKD, and this is also a patent that we have applied for. So there are lots of simulation toolkits available, okay? And if you search for it, you will find all these examples. But one thing one has to remember is that when you talk about simulating a system, usually simulations or softwares are done by software developers. So they are not particularly sympathetic to the cause of experimentalists. And as experimentalists, we know that, physical processes as well as components, they have imperfections. So these are things we need to take into account when we develop a simulation toolkit, so that the results we get would have some probability of being a close match with the experimental results themselves. And that is what we went on to do, painstakingly include all these physical processes and imperfections in our modules. It's a modular approach, and it was very well received by in India and abroad. This development, this particular experiment and simulation toolkit. Of course, it's all towards long-distance quantum communications. This is a quote from Isaac Asimov. He's a great science fiction writer, and this holds very well. Today's science fiction is tomorrow's science fact. And so when we first approached our agencies for funding, I will speak for another couple of minutes, if that is okay, to the chair.
Okay.
Yeah, okay. This is something, which forms the, when we first asked for this, it was treated as, will this really work? When you send a photon up to a satellite, will it really reach? It seems like fiction. But then, of course, a neighboring country launched a mission, and within a year, we got our funding for the first project on satellite-based quantum communications. And that's very important because ground-based approaches, they suffer from distance limitations because the Earth is round. So you have the problem of the horizon. If you use fibers, then you need to use, you need to use boosters, and that violates no cloning theorem. So you need to come up with an unconventional approach, and that is satellite-based QKD. You use a satellite as a trusted node between two ground stations which are really well separated, okay? And this is the kind of distances one can achieve. These are all various countries and their efforts. Ours started in 2017 in collaboration with ISRO, and what we are going to do is establish secure communications between two Indian ground stations using an Indian satellite as a trusted node. And one of the results we achieved early last year was, in fact, free space quantum communication between two buildings at RRI through the atmospheric channel. That is a very important step towards satellite QKD, because within the lab, things work very well. But when you go outside, that is when you have to circumvent many problems. And this was also our country's first such demonstration using an atmospheric free space channel. Again, very honored to have received a lot of recognition, including the DST's, recognition as one of the 20 major success stories in 2020, as well as the Vigyan Prasad in India Sciences top 10 innovations of 2020. So this is RRI, by the way, and it'd be great to have some of you there. With that, I think I'm on time, and so I'd like to end. This was basically an overview of various activities. This was during our last physical conference in 2020, and we really hope that we can go on to these days very soon. With that, I would like to thank you. Future is bright, and of course, future is in quantum.
Thank you, madam. You finished in dot 25 minutes. Very good. And very good work and excellent talk.
Thank
now,
you
this
very much.
talk is open for questions. This work is a very excellent activity and is the future of India. In long run, everybody has to go for quantum cryptography or quantum communication.
Yeah.
And I suppose, madam, maybe many people may not ask questions because many people do not understand the things.
Sure.
So,
today
anyway,
it was not
we still
possible to
invite.
give a lot of
Dixit?
detail. Yeah. Sorry.
Yes, yes. Please ask question.
You have few questions in auditorium. Dr. Biswas wants to ask a question.
Sure, sure.
Good afternoon.
Good afternoon.
Actually, you often refer to a beam of light during the course of your presentation. I'm just curious to know what kind of beam it is. Is it a steady beam, a periodic beam, or a chaotic beam? What kind of impact it would have on the outcome?
Right. That's a great question. So, of course, when I talk about a beam of, it depends on which part of the talk. So in one, I talked about a laser itself, but in most of it, I talked about a single photons, right? So I would talk about a stream of single photons or a stream of entangled photons. And these would have a certain, this would be a coherent stream because we are, of course, performing interference. But the thing that happens is as soon as we go outside in the atmosphere, then we have to deal with all these atmospheric parameters, right? Like, in fact, that is one of our main sub-projects, dealing with atmosphere, its turbulence, how that would affect our communication in free space. And so we are actually collaborating with different centers of ISRO, where we are, analyzing the atmosphere in different possible locations to see which one will have the maximum throughput for quantum communications and what would be the best site for a ground station. And so indeed, these considerations will come in to the part of the satellite QKD project, where, we are not dealing with a, very well modulated lab environment anymore. But we are not dealing with, a chaotic beam as a source. But what would happen is our regular beam, our coherent beam, will actually interact with different components, both dynamic and static, of the atmosphere. And that would lead to interesting ramifications for our quantum communication. I hope that answers your question, because I don't really see anything other than my
Madam, there is a question in chat box.
Okay, so should I?
The fellow says, can we use femtosecond laser for down conversion? Will it be more efficient for single photon generation?
Right, that's again a great question. So in fact, we use both continuous wave and pulsed lasers for our down conversion sources. So I could only cover a small part, but then, in one of our projects, we are doing pulsed down conversion. And that has its own advantage because, of course, it has, there are pros and cons to both. But the pulsed one, it gives us better timing information. So if you are interested in synchronization problems, which we are in some aspects, some applications, pulse sources have a natural advantage. And in fact, here in the picture, it's very interesting. So you can see us here, maybe you can see my mouse, but behind us, we have the titanium sapphire laser here. Which is our femtosecond laser source, actually. Here also you can see it, but it's only so much you can see. So indeed, that is something we are also doing. But then pros and cons, yeah.
And another question is, excellent talk, madam. This is Shaptrishi, maybe you may know her or him. How do you see the future of quantum computing given the decoherence effects as compared to the topological quantum computing?
Well, topological quantum computing is a subject you don't usually talk about in a because it's what happens is that there is a lot of promise in topological quantum computers, and in fact there was this demonstration which came from the Netherlands and so on. But unfortunately, they retracted that particular work because they found some shortcomings. So currently, it is still not as experimentally, what should I say, advanced as the other more conventional approaches like solid state and photonic and various other methods of quantum computing. But then, if the topological quantum computer actually becomes a real, reality in terms of an actual experiment and technology, then naturally it will have various advantages. But the advantages to us currently are a little more theoretical because we don't really have as much advancement, but that leaves a lot of scope for doing those advancements, I would say. So a lot of things going for it from a theoretical perspective, but at the moment it is not as advanced as, let's say, photonic quantum computers or superconducting ones or quantum dot ones and so on and so forth.
Yeah. One more question: does DBO thickness affects entanglement?
Oh yeah, that's a very good question, and of course it does. And so so one of the key points in actually having a high amount of entanglement, I would say, is that these two photons, they need to be perfectly indistinguishable, right? And so if you have a very thick crystal, then it can lead to some path distinguishability between pairs of photons and so on and so forth between the two photons, and so we would choose this very carefully, and we also have what are called path compensation crystals in our setup, so that whatever distinguishability comes in can be mitigated by a pre or post compensation. So indeed, but then having said that, the brightest sources do come from long crystals. But then those are, our brightest sources are coming from PPKTP, which is periodically poured titanium phosphide, tantalum phosphide, because BBO is not necessarily something which gives you the best brightness, but it does give you, very good entanglement. So depends on the application. So sometimes you're not interested in bright. We are just interested, in having a high fidelity and a reasonable number of photons. But in QKD, perhaps brightness does matter because it directly translates to the key rate. And so there we do have long crystals, but then we have ways in which we can ensure that, we still retain the indistinguishability between the photons, so that you have entanglement. Because if you have distinguishability, then you know which photon is which, then that, entanglement quality is not going to be high anymore.
So now, thank you, madam. Thank you. Very nice talk, and thank you. Very nice discussion. Thank you.
Thank you. Trying to stop sharing the screen.
So the next speaker, Dr. Suryanarayana, are you there?
Yeah. Yes, I'm there. Yes.
Yes. Very good. Welcome.
Thank you.
So now this second talk of this present session is on the challenges in the atomic vapor laser isotope separation of lutetium from Professor Dr. M.V. Suryanarayana. Dr. Suryanarayana is a senior scientist at BARC. Dr. Suryanarayana has very wide exposure of 32 years in BARC in the field of high resolution atomic laser spectroscopy, multi-step and multi-photon photonization schemes, and mass spectrometer, etc. He has published about 50 articles in peer-reviewed international journals, and he is doctoral supervisor both in Andhra University as well as in the Homi Bhabha National Institute, Mumbai. He is currently working on new technologies for the production of enriched isotope for cancer treatment. This is indeed a core activity of our Department of Atomic Energy. Now I invite Professor Suryanarayana to deliver the talk. Professor Saab, you have got 25 minutes for talking.
Yeah, thank you.
Start.
I'll start sharing them. Yeah. Yeah. Good afternoon to all of you. At the outset, I would like to thank NLS for giving me an opportunity to speak on this particular topic. I'm going to talk on the challenges in the atomic vaporizer laser isotope separation of lutetium. And AVLIS is a very old topic. Actually, there's a lot of time and efforts have been spent world over on largely on uranium. Atomic vapor laser isotope separation is essentially a method wherein you take atoms from ground state to into ionization continuum using multi-step lasers. The countries like Russia and US have made a very significant progress in this field. And most investigated element is uranium for very obvious reasons. So in this my entire topic, I'm just going to compare this lutetium always with uranium because many people are very conversant with uranium. Uranium has ionization potential of about 6.2 eV. If you use lasers of typically about 2.1 eV, it needs about 3 lasers. So you can see that it's a kind of a 3-step photoionization. One need to do it for ionization of uranium. No, at least I can compare it with like something like an orchestra. In orchestra, you will see somebody who is playing violin and somebody is playing cello here, and somebody is playing a keyboard here. Like it's a multidisciplinary art. But there is one person who is standing in the center. He plays a very key role. See this. If you compare again, how do we compare with this with AVLIS? There are some metallurgists who are working on, say, metal evaporations, etc. The laser spectroscopists will be working on getting the isotope shift and HFS and branching ratios and decay rates and all those that kind of data. Electronics engineers are working on the control systems of the AVLIS system. But this guy who knows what should be exactly what are the control parameters, like what should be the line width of the laser, what should be the delay between the pulses, what should be the power, etc., to achieve the desired selectivity and production rates. And why isotope separation of lutetium? Of late, lutetium has become a very important isotope. The conventional radiotherapy for cancers has gone into a different scale, where now people talk about a radioisotope which can be bound to a chemical compound. It's a bifunctional ligand. One end it is complex to the radioisotope. The other end it is connected to the peptide, and that peptide takes this particular radioisotope into the body, and that is where the radiation is delivered. And if I compare that, it is something like this. See, peptide is like an engine, and radionuclide is like a bogie. The peptide takes this particular radionuclide to the appropriate body part, and wherein the kind of radiation is delivered to the cancer-affected cells. Why is lutetium? What is so unique about lutetium? If one looks at the several several radioisotopes that are available for treatment, they have say for example 165 dysprosium, which has got a half-life of about 2.3 hours. It can deliver 1.3 mega MeV 1.3 MeV beta particles. On the other end, the other extreme is gadolinium 153, which has got about 241 days of half-life. It can deliver 97.4 keV of gamma energy. But if the half-life is very small, we produce this particular isotope in a reactor environment. By the time it is delivered to the patient, it is already died down. So if it is too large, it is convenient, but many times the energies, etc., may not be suitable. Ideally, we are looking for some kind of an isotope which has some reasonable half-life and whose energies are also not very high. Lutetium exactly fits into the category. It has got about 6.7 days of half-life, and its energies are somewhere in medium. It's not as high as 1.3 MeV or as low as 97.4 keV. What it can do is it can really penetrate into about 650 micron kind of depths into the cell, and it can cause enough damage. And added to that, lutetium also gives, apart from beta, it also gives gamma. So one can always do the gamma diagnostics and find what is the kind of dose is being given to the organ. So this is called a theranostic isotope because it can do both therapeutics and diagnostics in one. And lutetium-177 can be produced from in two routes. One is irradiation of 176 of ytterbium or 176 lutetium. But if one looks at ytterbium-176, its abundance is about 12.76, which is much higher than lutetium. So initially, one can think that ytterbium-176 is a good route to take it. But if you look at it, the thermal neutron absorption cross-section of ytterbium-176 is much smaller. So the conversion efficiency is very small. So it's not going to give us in large quantities of lutetium-177 that is required for the patients. So either way, in the we need to have either enriched ytterbium or enriched lutetium-176. So one of these things we need to choose. And let me just take, for example, why we need to enrich. If I look at natural lutetium, if I put it in the reactor, I can have three kinds of scenarios. Reactors which are having low neutron flux, that is about 10 power 3 neutrons, or 10 power 14, which are called medium flux reactors, 10 power 15 high flux reactors. If I put this natural lutetium in the reactor, then you can see that the low flux reactors produce very small quantities of lutetium-177. That's about typically 0.17%, 0.17 to 0.2%. Whereas if you have a high flux reactor, that takes it to significantly nearly 1%. That means whatever the lutetium which we take out is only 1% of it is lutetium-177, which is not sufficient. So what we need to do is we need to enrich it to at least 50%. So if you do it to 50%, then the overall content is nearly of lutetium-177 is going to be about 10 to 12%. And many of these the medical fraternity now they are looking for about 50 to 60% of lutetium-177 in the drug. So this is also in fact not meeting the requirements. Even if you see the 100% enrichment of lutetium-176 is not going to give us nearly the 60% criteria of lutetium-177. So the alternatively one can think of irradiate natural lutetium and then separate out lutetium-177 using ELIs. So how we do it? Let us compare now uranium and lutetium. If you see the ionization potentials, if you look at it, lutetium has lower ionization potential, melting points are comparable. Uranium has two low-lying metastable states, while similarly lutetium also has two low-lying metastable states, but the lowest metastable state has got a higher population density. And the comparison in compared to uranium-235, lutetium-176 abundance is much higher. Obviously, lutetium-177 is radioactive isotope; its natural abundance is 0. So both uranium and lutetium have got multi-electron system. It is going to have a very rich spectrum. So it is possible that we can do, we can think of several photoionization schemes. Now, if we compare the isotope shifts, so isotope shift, it is well known actually. I'm just going through for the completion. Isotope shift has a contribution from both field shift and mass shift. But if you compare the field shift parameter, which is, the field shift part, if you see, there are two factors. This is called a field shift parameter. The other one is mean square nuclear charge radii. So mean square nuclear charge radii, if you see it, uranium has got much higher than lutetium. So it only means that field shift part of part is going to be very small for lutetium in compared to uranium. As a result, what happens is the isotope shift in case of uranium are much higher than lutetium. This shows that how difficult it is going to be. The isotope shift, you can see that it is about -393 in case of lutetium. At least it is 20 times less than uranium. Now, if I see the some of the transitions of lutetium, I can know in case of lutetium, what happens is both the isotopes of 175 and 176 both have got hyperfine spectrum. So we need to see only the separation between hyperfine components is the only way to separate them out. In the first step, if you see the difference between the two of the hyperfine transitions, you see the separation is about 2.7 gigahertz. In the second, so then my question is, what should be the line width of the laser? So from initial reaction will be about 500 megahertz may be sufficient because that's about 1/5 of the separation. On the other side, if you go take to the next higher level of it, it is the separation between two hyperfine levels is going to be about 1.5 gigahertz. So again, in this case, is 300 megahertz sufficient? Or we should go for 100 megahertz or 1000 megahertz? I mean, that's a kind of a question one should ask. And compared to, again, once we compare in ablaze of uranium and lutetium, it has uranium ablaze is a two isotope system, whereas lutetium ablaze is also two isotope system if you are looking at natural lutetium. But whereas if you are looking at irradiated lutetium, it is a four isotope system. And in this case, uranium, the mass difference is 3. In this case, lutetium mass difference is just 1. So even mass shift part is also going to be small. So largely people have used lasers with bandwidth of about 3 gigahertz for uranium. In this case, it is required, about 100 megahertz is required. And many times I have been interacting with isotope separation scientists, then kind of quantifying the numbers. We always get a qualitative answers. If the isotope shift is large, selectivity is large. If the laser power is higher, we get higher production rates. Is it possible for us to quantify? That was a big question. But many times it was not possible as I have observed it. And several of those, that's simply because there are several variables. So there are source parameters like atomic beam, like angular and velocity distributions, divergence conditions, whether the optically thin or thick media, in terms of lasers, whether what kind of lasers we are going to use, pulsed or CW, what is the bandwidth, temporal profile, spatial, and all those, whatever listed, even atomic parameters, whatever we are talking about, the initial population of the levels, oscillator strings, decay rates, everything is going to make, it is going to impact the final, the selectivity and ionization efficiency and the production rates. Therefore, it is very difficult to give a qualitative answer to these things, but it is important for the process to get to a quantifiable answers. Now, if I compare the laser isotope separation as a chemical reaction, one can just think of, in a equilibrium chemical reaction, if you know the rate of excitation and the rate of de-excitation, you can always at any given point of time, you can calculate what can be the population at each upper level or in the trap states. So we can always relate it to that. This is what exactly Lawrence Livermore was doing somewhere in 1970s. Initially, there is a beautiful paper on this, the Livermore experience by J.H. Eberle. All their experiences, they have well documented in this. Of course, for additional reading, there is another paper here. They have also done on the plutonium, and their experience on plutonium is also listed here. And what they have done, initially they started working in a similar like considering it as like a chemical reaction, and then started using rate equation model and try to calculate the ionization efficiency after the laser interaction. But soon they have discovered that that doesn't help at all. There are reasons why it doesn't work, and that particular aspects have been well illustrated there. I'll come to that in the next slide. So now, if one looks at the single photon ionization process, let me just take a single photon process wherein the atoms from the ground state are excited to the first excited level or eventually ionized. As per the Schrodinger equation, we can write the density matrix equations like this. And now you can numerically integrate all these equations, and you can get at the end of the laser interaction what is the population in each state. Like the population in row 111, row 22 will give you the population at this level 1 and level 2. And level 3 will give you the ion population term. And this is nothing but the ionization efficiency. So by adjusting the laser powers, then we at any given point of time, we can calculate the ionization efficiency. In case of two-step resonance ionization, the equations are going to be much more complex. But in this case, we are going to see some of the terms like rho 13 and rho 31. So these are the coherent two-photon ionization processes. They make the huge difference in laser isotope separation process. And now suppose I take a two-step excitation process, and in one of these things, now if I detune one of the lasers, what happens? So I can, instead of, this is the case where laser 1 is fixed at resonance and laser 2 is scanned. And in B, in case laser 2 is fixed and laser 1 is scanned, you can see the shapes are a bit different. That's because of the lifetimes of the levels are different. And now what you can do is the other possibility is fix one of the laser to minus 500, say in this case, and then scan the other laser. You can see now you can see that coherent two-photon ionization peak is going to appear. This is a stepwise peak, and this is the coherent two-photon ionization peak. And in a rate equation model, this coherent two-photon ionization doesn't come into the picture at all. So if you are doing detuning laser 1 in the x-axis and detuning of laser 2 in the second axis, what you are going to see is this is the excitation peak of the first step, and this is the excitation peak on the second step, whereas the coherent two-photon ionization part of it is completely missing. So this is a very important thing in the overall laser isotope separation process. In three-step photoionization, actually it is much more complex. Now you will see some terms like rho 13, rho 31, and rho 14. That is nothing but coherent three-photon ionization process. All these processes are simultaneously happening. And whatever so far I have described about are about even isotope. In case of odd isotope, it is much more complex because each of the resonant level, each level is having again split into multiple states because of the hyperfine structure. So the generalized density matrix element for two-step ionization of an odd isotope recently we have published. Actually, three-step photoionization is now we are publishing. Now, if I look at it very specifically about lutetium, this particular scheme, whatever is shown here, has been very extensively used by Russians. So we started our work on this. In three-step photoionization, it is possible that from the selection rules, we can work out 44 hyperfine pathways for say lutetium 177. Among that, 5, 6, 5, 4 hyperfine pathway is the most intense. And now, how do we visualize that three-step photoionization process? In this case, what we have done is we have set the laser 3 to 5 to 4 hyperfine component of lutetium 177, and then scanned the laser 1 and laser 2. Then this shows and then we plotted the ionization efficiency of that. This is where the 5654 hyperfine component can be seen here. And the other hyperfine pathways are also can be seen here as islands here. And in this, we have just superimposed with the resonance positions of 175, 176, and 177. You can all see many of them are coming onto the, if I can draw a path of coherent two-photon ionization path, you can see several are coming into the resonance into coherent two-photon ionization line. So it also means that we need to very carefully control the powers of the lasers. Otherwise, these major isotopes are going to cause significant interference, and thereby we lose the selectivity. And now, suppose therefore, what we thought is we will what we will do is we will investigate the possibility of first irradiation of natural lutetium in the reactor, and then do isotope separation of lutetium 177, so that we can get a highly carrier-free radioisotope lutetium 170 for medical applications. So already we have already developed a density matrix code for this, so which can study the effect of laser frequency, peak power density, bandwidth, and pulse width, and delay between the pulses and Doppler distribution, etc. And we have put to use for solving this problem. Now selectivity is defined as the ionization efficiency of a desired isotope by summation of ionization efficiency of all isotopes. But this doesn't give a good picture. What we look at is the degree of enrichment. Degree of enrichment is nothing but the ionization efficiency of a particular isotope multiplied by the abundance of the target isotope divided by summation of this particular product. So what we need to essentially calculate is ionization of each isotope when the laser is tuned to say 5654 hyperfine pathway. If you are able to calculate under the given conditions, we can always calculate the degree of enrichment. And these particular calculations are highly time consuming, so needs kind of some kind of a cluster computation. We do it on the 20 teraflop machine what we have here. All these are indigenous code developed at Vizag. Now I'll just show you some few of the pictures. So now in this case, what we have done, we have fixed the bandwidth of the first excitation laser to say 100 megahertz, and then bandwidth of the second and third excitation lasers are scanned. What it shows is whether we can use broadband lasers for enrichment. So in case of low flux reactors, so what it is showing is even if suppose I use lasers of 100 megahertz bandwidth, it is going to give me around say 20% of enrichment. Whereas in this case of medium flux reactors case, it is going to give us about 75% enrichment of lutetium-177. In case of high flux reactors, it is nearly about 95 to 97% of Li-177. And of course, even if you are able to enrich to that level, the extraction of these things is going to be a really complex problem because of charge transfer collisions. Now, for at operating temperatures about 2000 degrees centigrade, the resonant charge transfer cross sections are known. Suppose we fix the extraction length, the probability of charge exchange can always be calculated for any number density. So now what we have done is now we started varying the number density of lutetium, and we calculate try to calculate the degree of enrichment at the collector for various number densities. One can see that up to about 10 power 12 number density of atoms, there is not much of significant deterioration of the degree of enrichment of lutetium-177. Whereas above 10 power 12 atoms, it is there is a significant loss. But loss is particularly going to be more significant for low flux reactors, whereas in case of lutetium, for high flux reactors, it is still okay. Suppose you have irradiated reactor lutetium in a high flux reactor, you can even use 10 power 13 number density and still get 60% of degree of enrichment. Whereas in case of it is medium flux reactors, it drops down to 40. So from all these calculations, you can always calculate the production rate also. The only unknown parameter in this case is going to be the ionization efficiency. So all these things we know, the laser beam diameter, we know the length of laser atom interaction, etc. And all those things, whatever is listed in this equation are known. The only one is ionization efficiency is the only one which is not known. Fix this from the calculations, you can always find the production rates. Finally, I come to the optimum conditions for the enrichment of lutetium-177. We have three case scenarios, and all almost show the same kind of peak power densities that are required. All lasers we have taken in this case co-propagating, because this process always prefers co-propagating laser systems. And here you can see the degree of enrichment of lutetium-177 is it varies from 25 to nearly 98%. And the productivity rate, it requires about 1.8 milligram per microgram per dose. Based on that, the number of patient doses what we can produce are about 19 in case of low flux reactor, up to 980 for the high flux reactors. Another important parameter in the entire thing is we are avoiding production of the lutetium-177. Another high half-life radioisotope is produced along with that, that can be also that can be very effectively eliminated. Now, whatever the human excreta or whatever is radioactive waste that is coming out, it can be safely disposed. In this sense, patient retention times also can be reduced. See, all these analysis, what we have done now, if it needs to be done experimental, it takes several years. This particular work has probably taken about 2 to 3 months of time. That's the beauty of this method. Now, I just want to conclude the isotope separation of Lu-177 from radiated natural lutetium gives carrier-free radioisotope, largely carrier-free. Let me just put it that way. The degree of enrichment is from 25 to 98%. The production rate is adequate to meet the current demand. The content of long-lived radionuclide can be reduced drastically. This allows, of course, direct disposal of biological waste and reduces patient retention times. So therefore, this lutetium enrichment of lutetium should be seriously considered. This can be considered as a panacea for lutetium medical applications. So in terms of laser isotope separation, a comprehensive density matrix analysis code has been developed. It has also been tested on various standard test conditions. So optimum parameters for lutetium-177 have been obtained, and this code, of course, can be applied for any isotope of interest, and we can quickly get the results. So with this, I just conclude. These are our 4 publications of last year, 2 in scientific reports and 2 in Journal of Optical Society of America. Dr. Shankari is my other collaborator, and I thank you for your kind attention.
Thank you, Dr. Satyan. You finished almost in time. Now, this talk is open for questions. And this talk was a very good talk for if you want to understand the inside of ELI's process. So now, any questions from participants or other people who are present?
Dr. Dixit, one question is.
Yes, yes.
Hello. Hello.
Yeah. Please.
Dr. Suryanarayana, nice talk. Can you please tell me, like you have just told that low flux neutron reactor, it will be around 25% enrichment.
Yeah.
And with the when flux is increasing, it is also increasing increment.
Yes.
So have you considered that neutral atom scattering in these calculations? Because that finally how much the neutral is landing to the collector, that will be the major factor actually to spoil selectivity or enrichment factor.
Yes, yes. I have shown you the slides on that.
No. So what fraction you have said? Suppose my it is 0.1% neutral are reaching there, scattering is there. If it is 0.2, then that's...
Yeah. Okay. Neutral atom scattering is not considered in this case. Of course.
So, but that is the main deciding factor actually.
Okay.
Thank you.
Yeah. Maybe I agree with you, but this has not been considered in this present case. Yes, I agree with you.
Any more query or questions? One thing I know that because I know this field, because this is a very complex field and somebody doing theoretical calculations or definitely gives ideas to experimentalists what they should choose. And there are always certain background is there that has to be properly taken care of. But this starting gives a very good confidence to everybody that how the process should be done, especially for now. Lutetium is a hot topic nowadays. So if there are no more questions, let us thank Dr. Suryanarayan for a very excellent talk. Thank you.
Thank you.
Okay, Professor, you disconnect. Okay, Professor SP Ram, you're there? SP Ram?
Yeah.
You are connected, SP Ram?
Yes, sir.
Okay, good. No, you take your time. You take your time, get it connected. So please speak something.
Yeah, am I audible, sir?
Yes, very much audible and very much visible also. Now you sit down, relaxed, and then we will start.
Now you can.
So So would you sit down or you would remain?
Yeah,
Like...
I'll stand. I will.
No, it's okay for us also, no problem.
No, I'll like this.
Okay. So now let me introduce the third speaker. The third and the last talk of this session is on trapping and manipulating cold atoms using magnetic and laser fields by our young colleague, Dr. S.P. Ram. He is a senior scientific officer at RRCAT and is from 45th batch of BARC training school. Dr. Ram has been working for last 20 years in the field of laser atom cooling, Bose-Einstein condensation, RF dress ring traps for cold atoms, electromagnetic induced transparency in cold atoms, atom trapping in optical dipole traps and optical lattices, and generation of Bessel beams. Dr. Ram was awarded DAE Group Achievement Award. He has more than 60 papers in journals, conferences, and one Indian patent to his credit. Now I invite Dr. Ram to deliver his talk, and 25 minutes for talking. Please start.
Thank you, sir. Thank you, sir, for the introduction. First, I will thank the organizers for providing me this opportunity to present my work, basically our group work here. So it is trapping and manipulating cold atoms using magnetic and laser fields. Professor Sinha has already given a glimpse of the work which is going on quantum field. So I believe this is experimental work which will give how those things can be achieved and how what we are doing here. So the plan of the talk is like that. First, I will give an introduction to the traps of cold atoms. Then how atoms are trapped, that will be discussed. And for trapping, what is the things are used, like for traps using magnetic field and traps using laser fields. That is, those are the main broadly two categories which are used for trapping the atoms. Combination of magnetic and laser fields are also used. And during discussion on trapping magnetic field, I will describe about the quadruple trap, quadruple IFE configuration or the quick trap. Then I will discuss something about the RF dressed potentials and RF dressed trap. There are also another field which our group is working. It is basically micro wire traps that I'll just give a brief glimpse. And then I will discuss our work on trapping atoms using laser fields in optical dipole trap and what are the results we have got. And finally, I will conclude. So the introduction to traps for cold atoms. What is the importance of trapping cold atoms? That as I have said that already it was discussed. So it has a lot of applications are there, like high resolution precision spectroscopy, cold collision studies. Trapping the atoms leads to the Bose-Einstein condensation, which is basically real manifestation of the quantum mechanics. And it is also used for atom optics, quantum information processing, quantum metrology, quantum computation, and all these fields requires atoms to be trapped, and they are utilized for various applications. Now, how we trap the cold atoms? So basically, trapping means confining the atoms in space using some external fields. So these external fields may be magnetic field or the electric field. So they can be broadly classified into two categories. One is the magnetic trap or the traps which are used magnetic field, because here the interaction of the permanent magnetic dipole moment of the atoms was interacted with the external magnetic field, and this is due to basically Zeeman effect, and it results trapping of the atoms. And the other one is where the interaction of the electromagnetic field of a laser beam was done with induced electric dipole moment of the atoms, and due to AC Stark effect, the atoms are trapped. So first I will discuss about this magnetic trap. Here the traps using magnetic trap, where I will be describing these these three traps. So magnetic trap of cold atoms, the potential energy of an atom interacting with the magnetic field B is given as this one. So the force is a gradient of that potential. And if you see that if we check the GFMF product of the atoms, then we'll see that some atoms will try to see a minima at the low field, and some atoms will see a minima at the high field. So the atoms we see a low field minima at the low field, they are known as the low field seeker, and the atoms which are see maxima at the minimum of the B field, they are known as the high field seekers. So for example, for rubidium atoms, these are the trappable states because a low magnetic field minima can be achieved and magnetic field maxima cannot be possible by Enso theorem. This can be seen in any book or papers. So basically these are the trappable states of the atoms, and other the anti-trappable states because they cannot be trapped in the minima. Now the most common trap which is used is the quadruple trap. It is basically two coils are used in where the current is flown in opposite direction. So a zero is achieved at the center, and a increasing or decreasing type of field was obtained in there. So this is the most common trap, and in any of the applications you will see that this is the first step when you basically laser cooled atoms are obtained, and then laser cooled atoms are first transferred to the this quadruple trap, and then they are used for other applications also. So for here what we have done, we have studied the effect of initial cloud and temperature of the cold atom cloud and the quadruple field gradient which is used to trap the atoms, and how the phase density changes in the quadruple trap. That was studied in the reference given below. So what happens when we initially get a laser cooled laser cooled cloud? So it has some number and density and its temperature. So when we transfer the atoms to a quadruple trap, we have to switch on the B field. So that B field, switching on the B field, that B field should be such that the atom transfer is maximum, and it's basically phase density achieved in the quadruple trap should be higher, because that initial phase density achieved in the quadruple trap governs that how the further things will be done, because that will only be used for achieving BEC and all these things. So here what is done, we have theoretically calculated the phase density in a quadruple trap for a cloud of having initial number n and temperature Ti and a size sigma I. And then finally, what is the TF is the final temperature achieved in the quadruple trap. NF prime is the density in the quadruple trap. And we have experimentally for various for a same temperature of the cloud, we have switched on the various B fields and observed how the density and the number of atoms and phase density was achieved in the. So you can see in the first this in the first graph you can see the how the with B field the density changes, and in the second graph you can see how the phase density was changed with B field. So here you can see that if a low B field is applied, low gradient, low quadruple gradient is applied, so what happens, that will not hold all the atoms, and atoms will be lost because of their high energy. But if you switch on a higher gradient, then the field will impact energy to the atoms and they will be lost. So basically there is a optimum value is there which can be seen from the graphs, and we have published this result here. But this quadruple trap suffers with a problem that it's that B equals to 0 points X as a leak, because there the magnetic Zeeman sublevel slip can occur and Majorana losses may happen, and therefore it is a leak, and atoms cannot be held for longer time in that. So what happens to avoid this? So people have applied various techniques such as to overcome this problem, people have used different types of methods like time orbiting potential trap, IFE Pritchard trap,
and plug the hole, and there are a lot of things. We have used a quadruple RP configuration trap. What is done here with the quadruple combination, another conical coil was used. So that conical coil helps in moving the zero position to one side and give a non-zero field at the non-zero minima. So the losses which happens in quadruple trap, that can be avoided. And you can see the schematic diagram and the image of the setup. The glass cell is at the center, and the coils are inside a cooling jacket because these high currents are flown in the coils, so they are kept in a water cooling jacket. And this is the schematic of the coil in the left side, and you can see the field, how the field is changing. The dashed line is this one for the quadruple coil, and the other dashed line is for quick coil, and the resultant field is shown by the other curve, second curve, and you can see the it creates a minimum of 2 Gauss, and that acts as that also gives a harmonic potential and a non-zero potential. So when this was achieved, because initially when the IFE coil was 0, in the right side images you can see that how when the IFE coil current was increased from 0 to the value where quick configuration is formed, what happens, the cloud is shifted to one side. So it is basically 8.5 mm cloud was shifted, so that finally the we achieve quick configuration at a quadruple current of 23 ampere, IFE current of 19.5 ampere, and in this we have achieved a lifetime of 20 seconds in the cloud, and where evaporation cooling is performed to achieve Bose-Einstein condensation. So here is the thing, the quick trap was atoms were subjected to evaporative cooling by applying a radio frequency radiation, and finally the cloud was characterized by absorption probe imaging. So the left side was the image was the quick trap cloud, and when it was evaporatively cooled, and finally we get the bimodal distribution of the optical density, and this indicates the onset of that negative OD in the surrounding the cloud. This shows the this is a prominent behavior of BEC. Till now I have discussed the things which I have till now shown: quadruple trap and this quick trap. These all are static field traps, means the field is applied once and it is constant with time, means DC field. But what happens that there are various applications where we require like tunneling and studying coherence, or for superfluidity study. All these things we need different type of geometries like ring trap or double well or something. This exquisite type geometries are required, which are not possible directly by this type of static fields, or you have to make some special kind of arrangements for the coils or magnetic traps, or you can apply some optical dipole beams. By using them you can achieve some different type of geometry. But this RF dressing, RF radio frequency field has given an opportunity to modify the potential of the static potential of the traps to generate various kinds of trapping geometries. So you can see that when atoms are trapped in a static magnetic field, and on that RF radio frequency field is applied of suitable frequency, so it modifies that trapping geometry. You can see that the left side blue curves are bare state. Bare states means where it is due to the static field, and in the right side when an RF field is applied, the potential gets modified, and it's you can see that it is a means where double well or ring type geometries can be achieved. So here I have shown how the RF dressed state potentials for cold atoms is derived. That is VR equals to MF H cross square root of del square plus this Rabi frequency square, and delta is basically the separation between, it is a resonant frequency or sorry, detuning between the thermal frequency and the applied RF frequency. So here we have demonstrated demonstrated how the a toroidal shape of cloud can be achieved by applying a RF field. This is our experimental realization of a ring or a toroid trap for 4 rubidium atoms, where basically in the quadruple trap another RF field is applied. So that RF field initially this at the 13 megahertz it is simply quadruple trap, and when we ramp the frequency or frequency detune from change the RF frequency from 13 megahertz to 1.4 megahertz, it basically initially it is a high low RF field, and as we go on in reducing the frequency, the RF amplitude increases, and what happens after some time, that center will be made hollow, and a toroid type of geometry is formed. So it is from, you can see that from the left 13 megahertz it was a quadruple trap, and as we go on reducing the frequency, finally we get a hollow toroidal type of trap. And this RF evaporation of atoms in the quadruple trap leads to a temperature of 20 microkelvin with 2 into 10 to the 5 number of atoms. So basically nearly 50% of the quadruple trap atoms can be transferred to this toroid trap. This was published in the reference given below. And basically this work on RF based trap of cold atom was also featured on the front page of Journal of Physics B in 2016. This we have also extended this RF tracing work to time average adiabatic potential trap. Basically, there we have quadruple trap was used with a RF field. So what happens in quadruple trap? There is a lifetime problem, as I have discussed earlier. So that quadruple trap can be converted to a time orbiting potential trap, and that time orbiting potential trap was superposed with the RF field. So here another parameter was obtained for changing the shape of the cloud. Here this time average adiabatic, this type of trap which is time averaged with time average, they are known as time adiabatic, time average adiabatic potential trap, and here is the potential due to this type of trap is given. And our this work here we can see that for various parameters we can generate double well, and the upper image is shown in the 3D where 3D image is shown, where cloud was 25 microkelvin cloud was trapped in the means it is a potential trap of 25 microkelvin shown in the two positions, so it acts as a double well. And sorry, am I audible?
Yes, audible. Continue.
Okay. So here I have shown the work where conversion of a X direction double well to Y direction double well can be achieved by changing the top field. Basically, the top field parameters which I have shown earlier, BXT, BYT, and BZT. If we change those parameters, then we can modify the from double well to ring, and from ring to other direction double well. So you can see that. Now I will discuss about the traps using laser fields. Basically, in all these type of in all these traps till now,
we have trapped only one trappable state, or the MF equals to particular state which is trappable in a minima field. But here this ODT provide optical dipole traps. This provides a magnetic sublevel independent trapping, and the higher trap frequencies can be achieved in optical dipole traps, and this leads to a faster evaporation and faster condensation also. So how this trapping using laser fields is done, that as I have discussed earlier, that if in a laser field E, it induces a dipole moment P, and the energy is alpha P square. So if the alpha minus alpha P square, so alpha P is greater than 0, then the atom is trapped at the maximum of the intensity. So if we take a Gaussian beam, at the maximum of the Gaussian beam, the atoms are trapped, and if we alpha P is less than 0, the atom is repelled from the maximum of the intensity and can be trapped at the intersection of two maxima of intensity. So we have performed an experiment where you can see the setup. Here a dipole laser beam was focused at the cloud position, and they are imaged by a probe beam, and the right side images are shown the experimental optical density images of the trapped atom cloud obtained by absorption imaging. So what happens when this light is present and we performed an in situ imaging of the clouds, so the energy levels of the atoms get modified due to the AC Stark shift. So we have theoretically calculated the AC Stark shift of any hyperfine level FMF can be calculated using this, and you can see in the right side when the there is no light shift, it is basically zero, a straight line, and due to the presence of AC Stark shift, the levels get modified, and transition energy gets modified. So due to this modification in the energy levels, absorption cross section also gets modified. We have calculated how the probe beam probe beam's absorption gets modified in presence of this AC star shift, and this also leads to how the potential is formed. Here you can see this is the variation in the trapping potential for the ground state of rubidium due to dipole laser beam of wavelength 1064 nanometer for a power of 27 watt and 1 by square radius of 17 micron. And so as I have said, that effective absorption cross section also gets modified. So that effective absorption cross section results in the modification in the optical density of the image, which is formed due to absorption. And we have calculated simulated this optical density image by considering the position dependent AC star shift and effective absorption cross section due to the dipole laser beam of power 27 watt and 1 by square radius of 17 micron. The optical density image which is shown here, it is simulated for a cloud of position. It is basically shifted from the focus to slightly one side, and this results in change in the number. Basically, when we in absence of the optical beam, or without incorporating the AC star shift, the number is different when we incorporate this AC star shift. So you can see that at 27.7 watt power, the number of atoms in the optical dipole trap is 2.1 into 10⁶ with AC star shift taken into account, whereas the number of atoms is 3.5 into 10⁵ without taking AC star shift into account. This result has been published in this article, and then some other activities which is going in our group, as I have said, that trapping can be achieved in micron size wear. So we have a atom chip activity where you can where the trapping of atoms in IFE pre-chat trap has been observed, and we also have a cold atom gravimeter setup. And finally, I conclude that as I have discussed about the traps for cold atoms, where quadruple trap, quick trap, RF dress trap are discussed, and another type of traps where optical dipole traps are discussed. And finally, I acknowledge these are my group members, and I also thank the Director S.V. Nakhe and Sri Rakesh Kaulji, Associate Director MS Group, for their help. Thank you.
Thank you, Dr. Ram, finishing well in time. Now this talk is open for a few questions, and people can also ask question in chat box. So let me see if there are anything in chat box. Okay, so now Aspiram, you did most of this work on rubidium, right?
Yeah.
Okay. And why the choice on rubidium? For what purpose?
Basically, sir, this laser cooled atoms which are prepared, they are rubidium atoms. So 780 nanometer lasers are available. Diode lasers are available at that wavelength, and we have a setup of this laser cooled atoms for rubidium 87.
So if you have other lasers available,
Definitely,
you
definitely
can try many other element of different interest, right?
Yes, sir.
Okay. And let me see somebody ask. Let me see somebody ask a question. Let's see. Just hold on. From Ashar Mishra. Why Mishra is asking why a blue tuned laser is not used for dipole trapping?
Yes, sir. Blue detuned laser can also be used. Basically, there you can make a hollow beam type of things where at the minima of the minima of that intensity will act as a trapping potential. So that can also be used, sir.
Okay. So if there are no more questions, then let us thank Dr. Ram for a very good talk in a very relevant research area. Thank you, Dr. Ram.
Thank you, sir.
Thank you.
So on behalf of the NLS Organizing Committee, I would like to thank Dr. Dikshit for extending his valuable time in sharing the session. And I would also thank all our invited speakers for the excellent presentations. So this ends our day 2 session on invited talks. And the day 3 session will begin tomorrow at 9:30 a.m. Thank you.
Thank you, Dr. Padma. Thank you.